Can you hear me now?
Yeah.
Sure.
Okay.
Thank you, Dr. Smita, and also Dr. Murthy, and also Professor Chaudhary, who actually encouraged me to accept the this invitation, although getting very late actually, and I was worried about all the time because I've given several presentations in the past in India, so somewhere in the midnight. But I think Smita took care of that actually, and she tried to fix me at 9 o'clock Indian time. That's a great thing actually. So anyway, so this talk actually is about the design and development of room temperature single phase multiferroelectrics for multifunctional applications. And yes, hello. Actually I'm not the sole author of all this work. There are several contributors to this talk. One of them, actually, there are several of them. James Scott, I'll mention. Ashok Kumar, Danilo Barrionuevo, Nora Ortega, Dilson Sanchez, Shalini Kumari, Dhiren Pradhan, Karunakar Mishra, and also Professor Gopal and Srinivasan from Oakland University and Professor Marty Gregg from Queen University of Belfast. This plenary presentation, actually, I would like to dedicate to Professor James Scott, who expired in 2020 on 6th of April. Unfortunately, that he had liver cancer and that could not sustain anymore, and we actually lost really one of the best collaborators of my time, actually, right from Edinburgh, which was in 1970 till 2020. He has collaborated with me, probably the longest time ever, actually, which is more than almost 50 years. Actually, he collaborated with me wherever I went or wherever he went. We always continued our collaboration. So I really miss him very much. So I dedicate this talk to his memory. You all know actually about multiferroelectrics. They are being talked for several now, more than a decade. These are the materials which possess two or more ferroic ordering in the same phase, and they can actually, the devices can be made with low power, faster speed, and lead towards the device miniaturization. Expand to show video. I don't know why it is saying. Okay, sorry, that was nothing to do with that. Anyway, so these actually, there are various applications that some of them I'm listing here. It can be used as a multi-state memory devices. That is, you can write ferroelectrically and read magneto-optically. Electric field control ferromagnetic resonance devices can be made. Magnetic sensors, that is, it can actually sense the magnetic field up to maybe 10 to minus 8 Tesla or something like that. Actuators and transducers, it can be utilized, and microwave frame devices, because of the dual tunability results in better, efficient transfer of power. And they also work away. The last one that not least actually is multiferroelectric internal junctions and for spintronics applications. We have been working on those recently. But there are problems and challenges. There are only few single-phase multiferroelectric materials exist in nature. And in fact, at room temperature, there's only one material that has been discovered so far is bismuth iron oxide, which is in single phase. And has been thoroughly studied, and it's one of the probably most useful materials. As when we talk of multiferroelectric, we cannot ignore bismuth iron oxide. And but then there are actually, and also those materials which exist at low temperature, now that they have very weak coupling between electric field and magnetic order parameters. So these are the two problems in the multiferroelectric materials that has to be solved. So what we have to do actually is design some new room temperature multiferroelectric materials with strong magnetoelectric coupling. So in order to design those materials, what we looked into literature and seeing that PZT, which is lead zirconate titanate, makes very good solid solutions with many of its lead compounds like MNPT is very famous of that. So we decided that why not we take PZT and we join its VFW, which is a lead iron tungstate, and PFT, which is lead iron tantalate, and lead iron niobate. So, by the way, all these materials, PFW, PFT, PFN, they're all multiferroic, but not at room temperature. For example, PFW has a TC, which is 180 K, which is below the room temperature, and although the TN is above room temperature, 380 K. Similarly, the PFT has the TC 310 and TN is 180. So both of them are low temperature. And here PF and PFT is also like that actually, that it is a low temperature multiferroic. So, and PCT on the other hand is only a ferroelectric and not having any magnetic properties. The transition is very high, 6 magnetic. So if we combine PFW with PGT or PFT with PGT or PFN with PGT, we can make solid solutions of these materials, because PGT makes good solid solutions with other lead-based compounds, which is all known. So we decided to move in that direction. So we took actually a ceramic preparation technique, that is the lead oxide, zirconium oxide, titanium oxide, iron oxide, and tantalum or niobium oxide. Here we are presenting the data only for the PFT, the lead iron tantalate and lead iron niobate. So we can choose those compounds with all compositions. We have taken here X equal to 0.1 to 0.9, and similarly Y also, that is in the case of PGT and PFN, we have taken Y also 0.1 to 0.9. That is means almost every concentration we have considered in the preparations. And we did high energy ball milling at 600 RPM for 20 hours in methanol, and then actually calcined the materials at 850 degrees centigrade for 10 hours, and sintering the materials at 1250 for 4 hours. And what happens, this is the result actually. So we have X-ray diffraction, which is, I'm presenting you only for PGT, PFT, and PFN, PGT. PGT and PFW, they are also similar, same kind of materials, but because actually there's, if I'm just give you an example of these materials here, and you can see here that these X-ray effects are actually at various concentrations of X actually and Y. You can see that they are all single phase. They appear to be very single phase without any secondary phase within the detection limit that we found. These are considered excellent results because, remember, the perovskite octahedra are occupied randomly by zirconium, titanium, iron, and tantalum or niobate. So, considering that actually, and not having any secondary phase, it's a great, achievement. And we wanted to check whether there is uniformity of homogeneity of the material in that. So we chose actually the FEM technique, and we studied PFN, PGT, and we found actually that there is a really homogeneous distribution of the elements, of various elements, whether iron, niobium, zirconium, titanium, oxygen. They are uniformly distributed over the area that we selected to study. Similarly, studies were done by my colleagues actually in Belfast. We sent the samples of PFT, PGT, and what they did actually, they removed a lamella of 700 nanometer by 400 nanometer, and they studied that actually by SEM, scanning tunneling, electron microscopy. They did EDX study, and they found uniformity in all the elements actually that they were present in that material. So now coming actually to high temperature XRD studies. So here are actually high temperature XRD studies. I am giving you 2 examples here. Because it's covering the area. Okay, that's right. So here you can see that as the spectra actually will go to the higher temperatures, then we can see that in lower temperature, these peaks here doesn't look like as if it is resolved. So we have actually plotted them with high resolution here. You can see each of them has 3 peaks actually, whether taken from this one that is here at 45 around, and this is around actually 56 around. You can see the 3 peaks are there. But as the temperature increases, they become doubleted. So in other words, the 3 peaks, which actually were due to this 002, 200, and 020, there were 3 peaks that is an orthorhombic phase, and it becomes actually only 2 peaks, so that is the tetragonal phase. And similar actually the 112, 2111, and 121 reflection, that is here actually, these 3 become 2 actually at higher temperatures. And similar results were for x equal to 0.3 that were observed. So what we actually, we calculated the lattice parameters for each of these materials actually, and here I'm plotting only for x equal to 0.4 and x equal to 0.3, that there is the 3 lattice parameters that is in the orthorhombic phase becomes actually only 2 lattice parameters at higher temperatures, which is actually the tetragonal. So we have the orthorhombic phase and we have tetragonal phase. And we carried out the dielectric studies as well, and we found that there is a dielectric maximum exactly at the same temperature actually existing there. So that confirms that this is indeed a kind of a transition in this material that is available. And based on the selection rules and various other possibilities, we have assigned that in the tetragonal phase, it is P4MM symmetry, and the orthorhombic phase is PMM2 symmetry. We also carried out the Raman spectroscopy of this material, of all these materials. And here I'm typically representing PGT, PFT. I'm showing here for x equal to 0.4. And you will see that here there are these 3 spectra taken at different temperatures. That is at 300 K and 523 K and 1123 K. You can see the 3 Raman spectra are very, very different. This one actually is represented when we deconvolute it. We find there are indeed 12 peaks underneath actually this one, and that belongs to the orthorhombic. This was done at 300 K. So this belongs to the orthorhombic phase, and that's what the number of peaks that we should be observing. And then we have got tetragonal phase here because there were these 12 peaks. They reduced it to 8 peaks, and then cubic phase there are no peaks actually there. So this also actually confirms that we do have a phase transition in this material similar to what is actually observed in barium titanate. We carried out the dielectric properties of this material, as a function of temperature, and you can see that the peak position, it actually from here more or less from even higher one. We cannot study, dielectric studies in our labs beyond 650 or something like that. So you can see that it is decreasing actually as the concentration increases. This peak value decreases. So here actually you can see that it decreases from 680 K to 453 K. That much decrease in the phase transition is observed from in the case of PZT PFT. It decreases from 528 K to 340 K, and there is of course an increase in the delta. You can see the delta value is actually at low temperature, at high temperature is increased, which is normal in ferroelectrics containing iron. So now coming to the polarization hysteresis. As you can see, the polarization hysteresis actually all of them actually at 0.1, 0.2, 0.3, 0.4. I'm showing you 4 of them actually here. They showed there is a good polarization hysteresis and also remnant polarization in this material. In all of these cases, PFN PGT or PFT PGT is all there actually. The maximum values were around actually, I would say, the best values are around, in the 0.2 and 0.3 more or less. Here also, these are the magnetic, magnetization actually, and the remnant magnetization is highest actually for 0.2 and 0.3. So these are, we consider actually the most prominent features of the multiferroics, which may have better repercussions in our further experimental results. Interesting thing actually that this is a PZT PFT, that is the lead iron tantalate. Lead iron tantalate alone, it has got a TN at Neal temperature at 180 K, and you can see if there were actually impurity phase or lead iron tantalate separately without it being solid solution with PZT, it should have shown a peak around 180 K. It does not show any peak around 180. So that actually confirms as well that the separation and the phase separation does not exist. Moreover, if there are other possible phases that can appear in this, actually may appear, are at 260K, that is Fe2O3, or 120K, Fe3O4. But you can see there is no peak at Fe 260 or neither at 120 nor at 260K. That means those phases are also not present in this material. So this is all that actually validates that there is indeed a single phase material that we have studied. Here are actually the leakage current, the current density is studied. You can see that the current density is very small actually in this material, and this is PZT, PFT, this is PZT, PFN. In both cases, we were able to get very low leakage current actually. So these are, of course, these are the necessary requirements for you should have high dielectric constant, low losses, and low leakage current. These are extremely important for device. One of our, researcher, he had decided to study the magnetoelectric coupling in this material by simply studying the hysteresis with applying the magnetic field of 1.5 Tesla, and to see whether the hysteresis loop changes there. And he did find the change in the hysteresis loop, and also when it is reversible. And when it goes to minus 1.5 Tesla, then it changes completely also. And here we have plotted how the remnant polarization changes as a function of actually the magnetic field. Actually. So that shows that this material, does have magnetoelectric coupling as well. In order to, to confirm this thing, we sent the samples to Belfast, and Professor Marty Gegg, he carried out this, lateral piezo response force microscopy, and on the lamella that he picked up, it is 700 by 400 nanometers, and he applied a very small magnetic field of 303 kilo oersted. And he had the domains, actually, this is all actually total domains that he has actually collected. And of course, this is 180 degree completely opposite ones. They are here actually. And then he changed the field, magnetic field to minus 3K. And you can see that there's a considerable change. The total domains actually that have completely changed and got this one. Then he applied again 3K, 3 kilo oersted again. And he could reverse it again. So that actually confirms that there is a magnetoelectric coupling in this material. So we got encouragement by, from our ceramic data. So we decided to prepare thin films of these materials by pulse laser deposition. And we utilized, of course, as usual, the excimer laser and 248 wavelength actually, and then something like 250 to 300 millijoules. That thing, and substrate temperature was around 500 degrees centigrade with the oxygen pressure of 80 to 50 nanometers. We grew the samples on the LSMO in this case actually target, and MGO target. We grew on MGO target. And then we grew LSCO, one target we used for growing LSCO, and then the other one actually the PGTFT. Here are the X-ray for this thin films. We can see that all peaks are along 001 direction, and highly naturally. And of course, there is one small peak of 0.11 peak. This 0.11 peak is indeed only 0.01% of the most intense peak from the target. So as a result, this is the say, second, another orientation. But in general, we can see that this film was highly oriented or textured film along 001 direction. You can see everything 001. And this is the AFM image of these films, and these are really, you can see the crack-free surfaces with a roughness of about 20 nanometers. Most surprising and interesting thing was actually, our pleasing thing is this one. Actually, this material has got PGTFT. This is for 0.2 and 0.4, 0.3. You can see very high electrical this electrical polarization is actually it's as high. Remnant polarization is as high as something like 70 or 75 microcoulombs per second. And you can also see the magnetic properties. It does have a good magnetization as well, actually. So, and not only that, this loop is quite a square loop, actually, and that shows it itself that the leakage current in this material is very low. So this was very encouraging results that we got for thin films of this material. Here we are comparing the PGTFT thin film that I just showed you with the ceramic PGTFT. You can see there's a big difference. The polarization is much less here compared to the thin films, because these are oriented films and the polarization goes up quite. Here are the dielectric properties of this material in thin film form, and the dielectric constant is quite good, actually, about 1500 actually. And you can see there is a slight, there is a relaxer behavior as well in this one, because as it changes, the peak moves as a function of frequency. So this is plotted here actually, and I think there are exponent terms calculated. But this material did show some. This one, particularly this one, actually has shown. This one is practically no relaxation, very little if there is any. But this one does have relaxation. Okay. Most interesting thing in this material was actually that the coupling coefficients. This was done by Professor Gopalan actually in Michigan. This coupling coefficient is very high for that. Actually, something like about say 20. Here 17. Now that here we have plotted more. This is one typical result here. Here we have plotted all the values, and it goes up to say 20 volt per centimeter, which is very high value if observed in any single phase thin film material. I still have to find a reference for any other actually that has gotten that much. In composites you can get very high values, but a single phase multiferroic, that this is quite high. This is very encouraging results. So we also grew, seeing that we got good results for PGTFT. We thought, let's try PGT-PFM thin film. So we have grown an LSAT. So this is also highly oriented. You can see all the peaks around 001, 002. And the dielectric peak is unfortunately quite high. And as I said to you, our limit is 650 around. We cannot go beyond that actually. So, but I believe in this material, the peak is around 630 in this material, which is 30%. That is, X equal 0.3. That's one. And here are the polarization one. The loop is now very thin, and that shows that this material may have some relaxer properties. And in fact, it is obvious here. You can see the dielectric constant is changing, with the frequency decreasing, and perhaps it's peaking at different places, but we could not study in this region. Here are the magnetic properties of this material. Since LSAT actually is anyway PGT also, but LSAT is actually diamagnetic material. So as a result, the loops are like that one. But you can see that the magnetic polarization, magnetization as well. You can see that clearly in this material. The magnetoelectric coefficients also measured by Professor Gopalan in this material is not very high. There we had shown you 18 to 20 volts per centimeter Ørsted. Here the coefficient is around 0.8 for PGTPFN. Of course, the out of plane and in plane. Even if we take this one out of plane, is 1.38 or 1.4. But for PGTPFN 30, this is even worse actually, that you have some kind of oscillation type actually, and value is very small actually compared to that. So it is surprisingly that PGT-PFT showed excellent magnetoelectric coupling, whereas PGT-PFN is showing very low this magnetoelectric coupling. We did PGT-PFW as well. We got again very good films, tetragonal pure phase and highly oriented along 001 direction. You can see all the peaks are in that direction. And here are the ferroelectric, ferromagnetic, and this is very recent, taken last week. We have dielectric peak, which is slightly, you can see the slight relaxer behavior is showing up actually, but basically it's quite high dielectric constant and is peaking quite well. You can see because of the relaxer behavior, the loop is again thinned down here, and here are the magnetic properties. So it is showing all of these properties in this material as well. We have not done the magnetoelectric coupling yet. We have sent the samples to Professor Gopalan, but we are still waiting for the results. I would now like to talk to you one very different kind of multiferroic that we have prepared recently. This is actually palladium substituted lead titanate and lead zirconate titanate materials. This actually study started initiated because of the recent computational based on density function theory suggested that non-isoelectric substitution of PD4 that on the PB2 side, that is the PD4 should be going to the A side in lead titanate, that will result into magnetism in these materials. That means if PD4 replaces PB ion, that is the lead ion, then it will give you magnetic moment of 1 microboron. And if PD4 replaces the titanium, that is the B ion, then the magnetic moment will be very small. So we thought actually, why not we prepare these materials? So we carried out actually, this work was initiated by Shalini Kumari, and we actually carried out the lead in my lab. The palladium substituted lead titanate and and lead zirconate titanate. These are the two compounds that we chose, and ball milling and all the same process, we were able to dope PD with 10% and 30%. Again, it can show you the XRD studies, the ceramics. All these actually data show that we have pure tetragonal phase of the material, and with the space group of P4mm, and tetragonality ratio was 1.05. The rate-well refinement actually gave XRD patterns of PGT30 showed lead palladium oxide of less than 1%, which is magnetic. That's why we want to identify that one. It's less than 1%, but yeah. Okay, in order to understand that where is this ion going, the palladium, and what valency does it occupy? We find actually from the data here, so we had to deconvolute actually to get the ratio of palladium 4 and palladium 2. We found out actually that ratio was something like 4/3 actually, and that means that the palladium is in the A site as well, and not just with the valency 2, but valency 4 as well. So at the A site, it occupies both PD4 and PD2. B site, it is occupied by PD4. And that is what that gives you A site is the one that gives you the magnetic properties. Here are the dielectric properties. You can see as a function of temperature, we have, it clearly shows that there is a phase tension around 569 degree from the dielectric data. Actually, similar from even from losses also, you can see the peak is around 569. It clearly seen it. We have done the DSC differential scanning colorimetry, and from there also we get a peak in the spectrum around 552, which is very close to this peak actually. So since it is ceramic, so we can consider these differences. Here are the polarization hysteresis for this material and the magnetic properties of this material. So this clearly shows that this material is indeed multiferroic. We did, again, Professor Gopalan comes in picture because he is the one expert in doing magnetoelectric coupling, has got a lot of experience and good facilities. So we always send the samples to Professor Gopalan in Michigan, and his students carried out the alpha, that is magnetoelectric coefficients. They determined. They found that this material does have magnetoelectric properties as well. You can see that here. It varies from 0.3 to minus 0.2 or something like that under the magnetic field of 3 kilohertz. So we thought actually, since it does have magnetoelectric coupling, it does have multiferroic properties at room temperatures. So we decided to make the films. Let me remove this. No, it doesn't go away. We decided to make thin films of this material utilizing the pulse laser deposition technique again. And you can see here that we have again actually that highly textured films here, all 001 direction, all the peaks here. So, and the film had actually see along the 001 direction, the C parameters for 4.0425 angstrom. The thickness of the film was determined by profilometer, and it's around 300 nanometers, 320 nanometers. We have surface topography of this PGT-PD. We call it PGT-PD, that is PD substituted 0.3 and things like that. And you can see from here that these are very smooth and images of FM, and they were crack-free as well. And surface roughness was something like 5.4 nanometer. And this is the EDS studies actually that indicated homogeneous distribution of all elements actually, in this material, and that nearly is stoichiometric. The amount were determined and then found that it was very stoichiometric. We also sent the samples to Belfast to do TEM studies actually, and here are the TEM studies up here actually. So you can see the cross-sectional image of this one we have plotted here, and you can find here the peaks belonging to the there are peaks clear for PGT PD as well as LSMO buffer layers. The weaker ones of the buffer layers actually LSMO, and the other one actually is PGT. Okay, piezo force response actually that can give you also some idea about if the material is switching or not, and you can see clearly there is a good switching of the material, on applying the electric field. Here are the dielectric properties of the materials. Again, we are limited in going beyond 650 degrees. So here it shows transition temperature around 515 K, which matches with the dielectric loss peak also. Same place. So observation of this broad dielectric peak and 10 delta, around 515 K, suggesting ferroelectric phase transition around this material. It's very disturbing here that when we did the ferroelectric polarization measurements, unfortunately this material showed very leaky actually. You can see that the loops are there, it is increasing, PR is increasing, but it is not a good loop. It's unsaturated loop, and this could be due to the oxygen vacancies and some ionic conduction processes that take place here. In fact, you can see here that the leakage current is also quite high in this material. So still the work is going on that to see how we can improve these characteristics of this material. This material did show good magnetic properties. You can see here actually the magnetic moment here actually there, and here also at different temperatures. So, in conclusion, we have successfully synthesized single-phase room temperature multiferroic materials of PZT-PFN, PZT-PFT, PZT-PFW, and PZT-PD in ceramic and thin film forms, and PZT-PFT thin films with 30% PZT had shown the strongest multiferroic properties and magnetoelectric coupling of about 20 volt per centimeter, which is perhaps the highest value observed in a single phase. Palladium substituted lead titanate and lead zirconium titanate materials also showed good multiferroic properties. Evidence of mixed oxidation states of palladium ion, that is PD4 and PD2, was confirmed from XPS studies that fulfilled magnetic ordering conditions in accordance with the theoretical predictions. The existence of multiferroism in these materials systems opens the possibility to explore new family of multiferroic materials at room temperature with enhanced chemical. And that's my conclusion. And thank you for your attention. And this work was supported by the Department of Energy, National Science Foundation, and Department of Defense, U.S. Department of Defense. And for relevant publications, you can see the website speglab.upr.edu. Oh, okay. That's it. You know.
Thank you, sir. Thank you for this informative presentation. Dr. V.R.K. Murthy, can you give comments? Dr. V.R.K. Murthy. Sir, there is one question asked by Vijay Deshmukh. He says, how to know the phase of our material?
We know the phase of the material in a thin film or in ceramic. Because in thin film or in ceramic, there is no problem at all. XRD is first one of the X-ray diffraction studies is one of the techniques that is utilized. Then we confirm with other techniques. The orientation also can be determined by these techniques. The XRD is the fundamental one. And composition can be determined by various techniques like XRF, PDX, and all that.
Sir, another question asked by Praveen Kumar Panda. Sir, could you please tell me the difference between solid solution and pseudo-binary solid solution?
Pseudo
binary solid solution.
Really don't know what pseudo-binary is, but the solid solutions here is very simple because we know that the PCT has made solid solutions. There is two things actually. One is actually having a composite phase, and one is having a single phase. The solid solutions that we have made with our Balmer technique, they are indeed single phase, and that's what we have shown you by various techniques that we have studied to find that it is in single phase. Now, composite phase means actually that both the phases coexist in the material separately.
So, another question is there. What is the meaning of relaxer behavior? Does it have something to do with phase transition in the material?
Relaxer materials are known to have frequency-dependent dielectric properties, and and because of they're actually dielectric values, they change with frequency, and they have exponent different than the device relaxation behavior. They have more than one actually, practically two actually. They have ferroelectric relaxers. You see there are lots of publications on that actually. You will be seeing, and all these materials in this you find in the ceramic form, they do not show the relaxer behavior as often as they show in thin films.
Sir, another query is that I think James Raju has asked. Yeah, Raju, Dr. Raju, can you speak? Dr. Raju, you can ask that. Directly you can ask.
Sir, what I was in the case of PCT and lead tantalum, lead iron tantalate, this coupling is better. Whether it has something to do with the bonding which tantalum develops in the system?
Well, this is what very surprising because this material I just saw, and I confirmed with Professor Gopalan, couple of times actually, that please make sure that what you have done is right measurements. In fact, I'm preparing more samples now. We have sent him recently a PFW, but we haven't gotten the response yet. And I will prepare. My students are preparing again PGT PFT again. To have a second batch. We did not publish this work yet. We are still holding it actually because I would like to get confirmation of that, because this is very high value compared to any thin film that I have seen so far. Actually.
Yes, sir. Very good result.
Sir, just wanted to ask, because there are a lot of papers where PB toxicity are showing. So in that case, how this PGT-based system as a multiplier is beneficial for commerciality?
Well, if it is a really single phase and all that, it can be utilized, and also it has got very low leakage current. These materials have got very low leakage current. There was a move about 10 years ago in Europe actually that let's stop working on P and PT, lead-based compounds. But then when the time came, they just extended it again by another 10, 15, 20 years. So I believe, there is no better ferroelectric material with ferroelectric properties or piezoelectric properties than PGT, so far in this. People are working on many other compounds now. Perhaps it will be replaced in the next few years, actually. But still, that the ferroelectric and piezoelectric properties of PGT is one of the best ones.
Okay, sir. Thank you.
I have one question to ask in connection with Professor James' question. And your PZT, PFT thin film sample shows high ME coefficient. But if you look at your plot, and it shows very high ME coefficient even at zero bias speed. What is the reason for it?
I still don't understand that actually, and that's why we are holding this publication actually. We want to reconfirm it by making it again, and then I wish there were some theoreticians actually working in this area just to give some. Unfortunately, we could not find any work so far in that. It's because very complex compounds. So most theoreticians do not dare to take it over. Looks like whatever. Professor Blins used to work actually in collaboration with us. Unfortunately, that Professor Blins died 20 years ago, and since then we lost that collaboration actually.
Sir, one again question asked. He say why a particular structure has least energy at temperature in order disorder phase transition.
Order disorder system. All of these. You're talking about the ferroelectric transition.
Yeah, of course. I think she's talking about
that is because of the stability against the low frequency normal modes. Actually, the phonons. Actually. The ferroelectrics are known to go through a transition because the frequency of the normal mode actually at low frequency. As that normal modes goes to very, very low value, that shows that the structure will become unstable at that, when it goes to zero. Of course, going to zero exactly, there are not many ferroelectrics. Lead titanate is one of the best example of that, where it goes to zero. But most of the compounds like barium titanate, there's so much order disorder actually remains in the high phase as well. But there is a transition temperature that goes with the free energy actually, where it finds the minimum. It just occupies that structure.
Sir, another question is there. The Raman spectra for 0.6 PZT, 0.4 PFT at room temperature corresponds to orthorhombic crystal structure, whereas the XRD pattern is indexed with tetragonal crystal structure at the beginning slide, where series for 1 minus x PZT x PFT is shown. I am little bit confused for the crystal structure for 0.6 PZT, 0.4 PFT at room temperature. Sir, please can you clarify this?
I think maybe I have seen actually that actually, but I don't think that is correct. Actually. I can go back, let's say.
Any more?
XRD spectra. Let's see. Here with the temperature, and this is with the 0.4 and 0.3. Now here the XRD spectra, these are actually let's say orthorhombic phase, okay, and this is tetragonal phase. Here orthorhombic is the first one here. So 423 is really above just room temperature, okay. I mean just above room temperature. So this is room temperature, orthorhombic. And this is tetragonal here on the top. So it is in same way in Raman also. This is 423 and this is 573. This is a much higher temperature. So much higher temperature is tetragonal. And this is orthorhombic. And the Raman also, let me show you Raman now. Yes, Raman. You see this is orthorhombic, okay? And this is tetragonal. So it's the same. And this is cubic.
Slide 6, something confusion. She has confusion on slide 6.
Yeah, slide 6. Let me see. Slide 6, actually, I'm showing only at room temperature. Only at room temperature. So this is not actually, so this is what's supposed to be orthorhombic, yes. 0.3, 0.4. I don't know about the other ones, but this is right. But this is not with temperature dependence. Temperature dependence comes here in this slide. You can see here clearly with the temperature dependence, you have got orthorhombic and then you have a tetragonal on the above that actually. So they are consistent. And in fact, you can see here also, you can see 3 lattice parameters at lower phase, lower temperature, and 2 lattice parameters at higher temperature. So that is tetragonal. And this is orthorhombic, and even in the other one, 0.3, let's say x equal to 0.3, same thing is there here too. So they are all consistent.
And so I think Krishnamai is get satisfied by that. Yeah. Sir, okay. Sir, again the same question repeated by Shanti Ranjan. These days many countries do not wish to work on lead. What is your opinion?
This is exactly what I'm saying, that one has to stop because of the all kinds of whatever. This is true. Lead has to be stopped, but scientifically, I would say what they have decided to continue for another 10 years, they would continue. We have to find alternative. We are working on BST and BST related compounds. For all these properties, even for the microwave properties, I think James Raju might be knowing actually that we are all working on that. For phase shifter or other microwave applications, we are trying to use BST now, and it has to stop. I must say that actually, but it may take some time. There is nothing like cutoff line, like something like that. That's what must be followed. In America, there is practically no move anywhere to stop it so far.
So I think the query session is over. No queries. CRK Murthy, sir, please continue.
Thank you, Dr. Katya, for giving an impressive talk, and many people are really have been showing their interest to interact with you also in principle. So I hope it will go further in the activities of the participants in the future also. Thank you for your kindness to deliver the lecture. Okay. We, on behalf of the organizing committee, we thank you for giving this excellent talk, and God bless you, sir. Thank you.
Thank you. Thank you.
So our
Can we proceed to the next lecture or wait for some time?
no, sir, we have to purchase. So I just introduced our next speaker. Our next session is invited talk by Dr. James Raju, Professor, Center for Advanced Studies in Electronic Science and Technology, School of Physics, University of Hyderabad, Hyderabad. I welcome you, Dr. James Raju, sir. His topic is lowering the crystallization temperature of thin film ferroelectrics with laser and fabrication of tunable microwave devices. Professor James Raju is currently head of CIS EST. He obtained his PhD from IIT Madras, Chennai. His research area includes pulse laser deposition and RF sputtering of thin film, laser annealing of thin film, microwave characterization of material, bulk, thin film, nanomaterial, liquids, microwave tunability of material, tunable microwave devices, miniaturized microwave resonator, ferroelectric and piezoelectric thin film, magnetoelectric nanolaminators, microwave devices for quantum computing, flexible microwave devices. Sir is the recipient of many honored and awards. He has received Best Thesis Award, IIT Madras in 1997. Sir is a member of various professional bodies such as National Academy of Science, India, Telangana Academy of Science, Material Research Society, American Ceramic Society. He was also a member of NASI Lucknow in 2014. About 10 PhD scholars have completed their PhD under his guidance. He had completed around 9 research projects funded by DRDO, DST, BRNS, DAE, UGC, NP, MAS, and one project is undergoing. He has published more than 200 research papers in peer-reviewed journal of international repute. So we, on behalf of NSFD 2021, I welcome you, sir, on this platform, and I request you to start your presentation. Please, Professor.
Okay, fine. Thank you, Dr. Smita. In that, please, that share, please enable the share.
Yeah. Share. 1 minute. I can.
Sure. Okay. In the meantime, I thank you, Dr. Smita, for the kind words, and also I am very happy to be in this session where my teacher is the anchor, Professor V.R.K. Murthy, and also my mentor at Puerto Rico, Professor Kachar, has given a plenary talk. I'm very happy to be in a session with both of them, and now I look forward to my presentation. Okay, now the share has come. I will okay from it. Okay, fine. All right. All right. See, basically, my topic is lowering the crystallization temperature of thin film ferroelectrics with the lasers and fabrication of tunable microwave devices. Okay, that will. Since, as you know, I am at the University of Hyderabad, and I will be speaking about the issue of crystallization of oxide ferroelectrics. Then why lower temperature processing is important, and laser-based approach to achieve this result, and crystallization of BST thin films using laser radiation at 300 degrees Celsius, and then full depth crystallization of BST with the laser annealing of layers at 300 degrees Celsius, and then tunable microwave devices using ferroelectric thin films, particularly reactors, and then filters, and then high overtone bulk acoustic resonators. These points I'll be covering. And as you know, with Ferroelectrics, their characteristic feature is to give a very high dielectric constant at their phase transition temperature, and below their phase transition temperature, when they are in their ferroelectric state, they exhibit hysteresis, and above their Curie temperature, they will not exhibit any hysteresis, but the dielectric constant is still field dependent. So this paraelectric state, where the dielectric constant is field dependent, is the area which is mostly used for microwave device applications. Therefore, in the ferroelectric state, we will get this kind of hysteresis loop. In the paraelectric state, we will get this kind of a nonlinear electric field dependent polarization. It is that nonlinearity that helps to make field dependent capacitors. That means reactors. It is like this. See, if we measure the capacitance of this kind of a capacitor made with this kind of material in the paraelectric state, if we measure as a function of frequency at zero bias voltage, it will be like this. When you apply a bias voltage across it, and when you measure the capacitance with the frequency, it will be like this. That means the dielectric constant has decreased in the application of a field. That means corresponding to the capacitance is field dependent. Field dependent capacitor is called a varactor. Therefore, this BST capacitor effectively functions as a varactor. Now we have we have other kind of varactors, but the problem is most of the varactors which we are familiar with at low frequencies are reverse biased PN junction diodes. See, they even in the zero signal condition, they have a reverse current, and such current will enormously increase this loss performance. Therefore, at a higher frequency, that is particularly worse. That is why people are looking for alternatives to these reverse bias diodes, and in that way, this ferroelectric films in the paraelectric state offers a very good alternative. That is why we consider them for tunable microwave devices, because in a high frequency circuit, we have basically only three variables: L, C, and R. This R leads only to dissipation. Therefore, we have only tunable parameters are inductance and capacitance, and it is difficult to miniaturize inductors, but the capacitors can be miniaturized. That is why, if we get a tunable capacitor or a field-dependent capacitor, then using such a capacitance, we can vary the dielectric constant of such materials. Capacitance changes. When the capacitance changes, the resonant frequency of the circuit changes, or the frequency response of the circuit changes. Therefore, field-dependent capacitance is one of the few basic elements available to achieve frequency tuning in the microwave frequency range. That is why it becomes so important. And we know very well these perovskite materials in their perovskite state. They have their structure is like this, and in the in their cubic state, they lose a certain tonality, and they are in a symmetric state. Now, when it comes to this tunable micro device application, the most important material is the BST, that is barium strontium titanate. Why we go for it is, we know that barium titanate has got a phase transition temperature at 120 degrees Celsius, and we want to use this, as I mentioned, we want to use these materials in the paraelectric state, and we cannot operate it every time at a higher temperature. Therefore, instead, we want to bring down the Curie temperature below room temperature. For that, the best method is to substitute this barium with the strontium. As the strontium content increases, the Curie temperature of barium strontium titanate steadily decreases. But when the ratio is 50-50, barium and strontium, the Curie temperature is around 10 degrees Celsius. Therefore, at around 25 at ambient temperatures, they are in the paraelectric state, and therefore that is why we go for BST. We want to exploit their field-dependent dielectric constant in the paraelectric state. And see, basically, now these things are fine and very well known. Those things are okay, and we have made BST thin films crystallized at the room temperature, and with that we can make device also that I will be mentioning towards the latter part of the presentation. But what is the main issue? What is the problem is all these properties are all these things are good, but the problem is the processing temperature for this BST or PZT or any of these oxide ferroelectric films is around 700 degrees Celsius. But but nowadays, if you look at the CMOS processors with transistor dimensions in nanometers, that too nowadays they are all less than 10 nanometers. The process temperature allowed is steadily decreasing. Nowadays, more than 300 degrees Celsius is not allowed. Otherwise, those materials which require higher temperature has to be processed first, and then the rest of the process has to be taken up. And there are a number of complicated issues. Therefore, there is a real to integrate these ferroelectrics into CMOS process. It is necessary to bring down the processing temperature to a temperature something like around 300 degrees Celsius. But this crystallization temperature around 700 degrees Celsius. That is a real issue. Then the question is how to achieve this reduction in processing temperature. Because we know that this ferroelectric property is a crystalline property. Unless the material is crystalline, we won't get this property. Therefore, if you want to exploit, for example, even this field-dependent dielectric constant, if you want to get it, the material has to be crystalline. But the crystallization temperature is high. And not only that, nowadays a lot of importance is with flexible electronics. For that, the substrates are mostly polymers. And if you want to integrate these ferroelectrics onto polymers, there again the processing temperature has to be low, because no polymer will withstand higher around 300 degrees Celsius or so. Therefore, because of various reasons, there is a strong necessity to reduce the crystallization temperature of these oxide ferroelectrics to lower temperatures. So that is what we are looking at it. In fact, in our flat TV screens, it is done with that is done. This amorphous silicon is coated onto flat glass panels, and they are crystallized using a laser, using an excimer laser. But that is a semiconductor, therefore it will work. But when it comes to oxides, will it work? That's the issue. But in fact, in oxides, in a little limited way, various people are trying, but in fact, it has not become an industry standard process. Therefore, there are a number of limitations, and we are looking at how to overcome these limitations and achieve full crystallization of these oxide ferroelectrics at a lower temperature. And especially in the present day system in chip and system on package, these kind of requirements are quite high. But especially if you use a laser-based process, the advantage is where the material need to be, where the film need to be crystallized. There alone we can direct the energy, laser energy, and get the film crystallized only in that region. That advantage is there. And for that, in fact, therefore we have the process we have adopted is a laser-based crystallization process that is capable of bringing down the crystallization temperature to lower values. And the conventional crystallization methods require, we know, that very high temperature, and it also is a slow process. And also it requires high thermal budget. And this high temperature crystallization is compatible with the but this high temperature crystallization, the conventional crystallization, is incompatible with the thermally sensitive substrates like polymers and even CMOS circuits with the nanometer scale devices. But when it comes to if we use a laser energy for annealing the film, then it is possible to achieve that using lasers or short pulses, because if you use a nanosecond, if you use a laser with a nanosecond range pulse width, the power level comes into the gigawatt level. That is why, in fact, this ultra short laser pulses is able to bring in transformation. And also this heating with the laser can be localized to the surface layer. And as a result, the amount of change happening at the film substrate interface will be quite low. So often that is highly advantageous, because this while we are processing, it is the film substrate interface reactions is the one which create a lot of problems in many times. In fact, in this way, we'll be able to avoid that also. Therefore, these laser-based crystallization methods can crystallize a required region of a circuit without damaging other parts. That's the main attraction. You know, the first for barium extension titanate, first we make the PLD target. By the conventional processing, we make the we made a target of the barium extension titanate material and sintered so that it will be a very good. We achieve very good density, so that it can be a good target. And this is our laser based fabrication facility. On the right side, what we see is the pulse laser deposition system, and on the left side we see the annealing system. There an expanded beam of the laser is used to anneal the deposit film. We deposit the film at 300 degrees Celsius, and then during annealing also we keep the film at 300 degrees Celsius. And in fact, temperature can be done even at the room temperature it can be done. But the problem is at the room temperature when you do it, the film cracks, and as a result, the microstructure is very poor. That's why we are supposed to do it at a higher temperature. Then these are all the characterization techniques we use. So this is for structural and microstructural characterization. We use XRD and TEM and FESM, and then we study their optical properties. That Raman spectroscopy is quite helpful in so many ways. And in addition, this band gap studies for UV visible spectroscopy is quite critical in this, that I'll show. And then microdielectric properties using an electrical analyzer. These are things we do. And for the microwave characterization of these films, it is not a simple straightforward process. For every measurement, we have to deposit a structure like a coplanar waveguide or a circular patch capacitor pattern. You have to fabricate such a pattern, the structure on the film, and then that film coated substrate will be placed on a probe station. These are the probes. In these probes that these structures has to be probed, and these probes are connected to a network analyzer like this. Therefore, each measurement requires a patterning. That way, it is a little lengthy process and indirect process. Now, first I will show what will happen when we do the normal crystallization. That is at 700 degrees Celsius, when we crystallize the film, what happens? From that, we will go to the low temperature crystallization aspects. And see, when we do the normal crystallization, see, deposition temperature is 750 degrees Celsius. Then in this case, we have used the MgO substrate, and pulse repetition rate is 5 Hz, and base pressure is about 10 minus millibar, and valence is 248 nanometer. And see, what we can see is see, as the oxygen here, what we are seeing is this. See, here we have varied a few parameters. One is oxygen working pressure and laser fluence. And what we are seeing is at higher oxygen working pressure and this oxygen fluence, in fact, they are not getting crystallized, and they get crystallized. By the way, all of them are done at 750 degrees Celsius, and they get crystallized in a much better way when the oxygen working pressure is lower and the fluence is higher. At these conditions, they get crystallized, and that is what is being shown here. With respect to oxygen pressure, we can see that this crystallization is like that. At low oxygen pressure only, they get crystallized better. But if you keep the temperature at around 750 degrees Celsius, crystallization is assured. Then depending upon the substrate and the other processing conditions, we get either oriented film or a mixed film. In this case, a mixed film, mixed oriented film. Otherwise, it is under well optimized conditions, it is possible to get a single oriented film also. And the corresponding microstructure we can see here, and in the well crystallized film, microstructure is also well developed. And the corresponding Raman spectrum, when we see where the crystallization has advanced well, we can see these Raman peaks are also well defined. Therefore, if you take the Raman spectrum of a bulk, it will be quite similar to that. A similar Raman spectrum we can get for a well crystallized film. And this is an important aspect. That is, see, when the film is purely amorphous, when you do optical transmission spectrum, and what we see that in fact absorption starts at a much higher band. The photon energy is around 4.5 electron volt. That value is called band edge. And as the crystallization progress, we can see that this absorption starts keeps happening at a lower and lower values of photon energy. And for bulk BST, the absorption happens at 3.5 electron volt. So therefore, that 3.5 electron volt is the band gap. So initially we have the band edge, and then we come to band gap value. This band gap energy. And as the crystallization progress, we can see that the band gap value decreases from a very high value like 4.5 electron volt to the actual the bulk value 3.5. Therefore, this development of the band gap and its reduction is a very good indicator of progression of the crystallization. Therefore, the way crystallization progress correspondingly, earlier we have seen the way crystallization progress, the same trend we can see in the reduction in the band gap value. So that is a very good indicator, very good parameter to know the progress of crystallization. And as you can see here, it decreases from 4.45 to 3.62 electron. And micro dielectric properties, when you measure, see this is for the uncrystallized film, the top one, and the last one it is the well crystallized film. This is for capacitance, and the right side it is for the dielectric loss, measured from these test structures. And what we see is initially it is just a linear curve, but as the film gets well crystallized, what we see is we see a peak appearing. This is for the paraelectric film. That what happens is when we apply an electric field in the paraelectric film, they undergo a field-induced crystallization. They become once again piezoelectric. That is why they give this something like a piezoelectric resonance. They give at some frequency. That is why we get this kind of a change. And now let us see what happens when we do this process at 300 degrees Celsius in presence of laser. The process is like this, and we have this is the BST the target, and the XML laser of 248 nanometer is falling on it, and getting ablated, and it falls on a substrate, and the substrate is kept at temperature of 300 degrees Celsius. And after that deposition, we keep the film again at substrate temperature 300 degrees Celsius in another chamber, and this same beam is expanded, and need not be same beam. We use the beam from an NDR laser also, but in a slightly expanded fashion. With that, we irradiate the film again at 300 degrees Celsius. First deposition process, then annealing process at elevated temperature in presence of the laser radiation in an expanded. And see that then what happens? See there are a little background. See, with this 248 nanometer laser has got a photon energy of 5 electron volt. That is much above the band gap of BST, that is 3.5 electron volt. But we should know that initially it has got only band edge, because at 300 degrees Celsius the film is amorphous. It has got only band edge. That has got to 4.5 electron volt. Then the atomic electric field strength is 10 power 11 volt per meter, and normal light electric field strength is only 10 power 2 volt per meter. And for laser, electric field strength is high, that is around 10 power 12 volt per meter. Thereby, laser electric field can separate electrons from atoms to generate a plasma. To contain this plasma, we require nanosecond duration pulse laser shots. This process is isochoric in nature. This implies increase in localized intense pressure. Since it is pulse in nature, a pressure wave is generated in the material. And the low pressure regions, the material relaxed portions, are suitable for crystal nucleation by energy minimization. Once nucleation happens, it takes over dissipation. These crystal nuclei undergo aggregation to grow further, extending crystallization to the complete laser radiated region. The bond energies are for barium oxide bond 5.9 electron volt, strontium oxide bond 4.7 electron volt and the titanium oxide bond 6.9 electron volt. Therefore, the strontium oxide bond energy is comparable to the photon energy. So first that will create the vacancy, and there the nucleation happens, and then it will spread. Therefore, that P.H. Huang and his team, they have done it in copper. See, basically that they have presented a scheme for the laser annealing process in copper. They propose that when the laser light is incident on the material, it generates a shock wave. And when this shock wave meets a pore or defect region, the kinetic energy of the wave is reduced through the energy transfer to ions. It can trigger the collapse of this pore or defect, and hence mending the lattice in the region. So this process is called by some as lattice mending process. That in the case of BST, it can be stated like this: the laser annealing in BST can be initiated by the breaking of the SRO bond, which has got a correct energy corresponding to this laser photon energy. And there, once such a vacancy created, the lattice collapses in the neighboring region, and there it comes try to come to an equilibrium position. In other words, the healing for the initiative is amorphous. In that amorphous matrix, ordering takes place where the defect is created, and because of this, the advancement of the shock that is created, that mechanical energy will redistribute ions into push the ions to fall into the respective minimum energy position. That way the lattice structure can develop. That is basically the pressure waves excited by the laser radiation forces the atoms around a defect to fall into the what you call crystal minimum energy positions. That way, the crystallization process starts, and once it starts, and when the process continues, it extends and it becomes a pretty crystalline matrix. Or the lattice mending under the combined effect of pressure and atomic thermal diffusion at a near surface nanopore at different progression of times as observed in copper. That's what this is saying. Therefore, this process is called lattice mending under the influence of laser energy. In fact, this we have, it is getting published now in Advanced Electronic Materials, and what I'm presenting is basically this, which is going to be published soon. It is accepted for publication, not published. And the deposition conditions are like this, so that see, we have used this few silica substrates, and at 700 degree we have done it for control, because that is in situ crystallization. And this is the first one is for 300 degree crystallization case, and the parameters are oxygen pressure, substrate temperature, this precipitation rate, thickness of the film we wanted is around 600 nanometer. That is for some applications, and to get that, the number of counts of laser pulses is around 10,000, and we use laser fluence of 2 joules per square centimeter. Now, after this deposition process, when you do a cross-sectional SEM, we can see that by both process we get 600 nanometer of the film, but here it is crystallized, here it is amorphous. But now when we radiate that with this laser pulses, see, initially with the 50 pulses we don't see any perceived change. But of course, in fact, when you do TEM analysis, we can see that even after 5 pulses, there is nucleation of crystallization happening, but not appreciable enough in an XRD. But in XRD, the 250 pulses, they start appearing. But by the time we arrive at 2000 pulses, remember that the film is kept at 300 degrees Celsius. It was deposited at 300 degrees Celsius. Even at 300 degrees Celsius, when we have radiated it with 2000 pulses, in fact, a well-defined XRD pattern has developed. But what we found is that when you increase it to 3000 pulses, it decreases. Therefore, this that means there is an optimum value. If you do too much of this, what happens is it will start ablating the film again. That is why correspondingly the crystalline size and this grain size, all these things changes. So we can see that with respect to okay, at an optimal level, we'll get crystallization. That is what we are seeing here, and that is seen in other techniques also. For example, see, at a 300 degree, the film which is prepared at 300 degrees Celsius in the TEM, okay, they show an amorphous matrix. But at the 700 degrees Celsius, it shows a crystalline structure. And it is HRTM, and this is what we are seeing is here we are seeing the this pattern corresponding to a polycrystalline material. But for amorphous film, there is no pattern. And when it comes to this films which are prepared at a different number of pulse radiation with the pulses, we can see that initially with the 50 pulses, this is pure amorphous. With the 250 pulses, we can see the crystalline start appearing in the amorphous matrix, and we can see this amorphous phase formation. In the HRTM, we can see that. And at 2000 pulses, we can see that the number of crystallites in the amorphous matrix are more. Correspondingly, this amorphous, the polycrystalline the pattern in the TEM, that is also become more pronounced. And in the HRTM also we can see the lattice parameters which you can measure. It is same as that in the XRD. So what we can see is whatever seeing in the XRD, same thing we are seeing in the TEM also. And corresponding in microstructure also, what we can see is earlier we have seen that at 2000 pulses the situation is better. At the same 2000 pulses we are seeing very good, well developed dense microstructure, which gives less leaky current, because the microstructure is quite good, and that happens at and where the crystallization is better, the microstructure is also better. And correspondingly, even in the laser random spectrum, we can see that same trend we are seeing in there also. See, that means at at 2000, what do I see? This is for the in situ crystallized films which are prepared at 700 degrees Celsius. That one is well crystallized. And among other films, the best one which comes next to it is the films which are prepared at 2000 pulses. That means the films which showed better crystallization in XRD shows better features in the laser random spectrum also. And by looking at their band gap, we can see this beautiful trend. That is, see that the purely amorphous films give a bandage of around 4.58 electron volt, and after deposited films give a band gap of 3.54 electron volt. And in between these laser radiated films steadily show decreased band gap. And what we are seeing is, as the number of pulses increases, band gap steadily decreases. And at 2 pulses, it comes to 3.86 electron volt. But once you increase the number of pulses, the film quality decreases. Correspondingly, band gap goes back. It increases to 3.93 electron volt. And when we see the energy density also, what we are seeing is there is an energy density dependence also. When we use it at 60 milli, when we do the annealing at 60 millijoules per square centimeter, in fact this is the response. And at the top, the crystallization is better. There the energy density is little higher at the 66 millijoule per square centimeter. Therefore, what we are seeing is with increased annealing energy, crystallization will become better. But if you increase it too much, again it will start getting ablated. The film will start getting ablated. Therefore, there is an optimum value. And if you look at, when you looked at the cross-sectional TEM, this is what we are seeing. And see, basically what we are seeing is, see, this 600 nanometer is the thickness of the film. But when we irradiated it with the laser, only 120 nanometer thickness of the film got crystallized. Rest is still amorphous. That is an important aspect. It is, even though 600 nanometer is the film thickness, when we irradiate with laser, nothing happened at this water level. Only top 120 nanometer got crystallized. That has got enormous significance. And as a result, the microwave properties also we can see the same result. See that these films which are deposited at 300 degrees Celsius, deposited on platinum silicon, see, there is no tunability there. With respect to bias field, there is no change. But when it comes to these films which are crystallized at 700 degrees Celsius, that is in situ crystallized film, and they see with a zero field, this black line is the response, and at 20 volt applied across the film, this red line is a response, and with the 40 volt, it is this blue line is a response. and this is for capacitance, dielectric constant, and dielectric loss. You can see the similar response. Therefore, that is well crystallized. They are showing the crystalline property. But when it comes to these films which are crystallized using laser at a 300 degrees Celsius, they don't show any tunability. They behave just like this amorphous film. That means even though in XRD, laser Raman and TEM and band gap we see crystallization property, but that crystallization is not good enough for showing up in the microwave response. That means we have crystallized in an amorphous matrix. That crystals haven't grown enough. They are too small, and they are not. They have not grown enough to exhibit their crystalline property like exhibited by a Ferroelectric. Therefore, the next challenge is how to achieve full depth crystallization of BST, the laser annealing of layers at 300 degrees Celsius. And for that, the strategy we use is like this. See, okay, initially we deposit the film using the BST target by PLT, and then use the same, and then we irradiate the same laser in an expanded beam onto the film, which is kept again at 300 degrees Celsius. And then this film, the thickness is only around 120 nanometers. So we find that this crystallization progress by this process only up to a depth of 120 nanometer. Therefore, we restrict the process to 120 nanometer. We do the deposition and annealing. After that, we bring it back here, do the next deposition, another 120 nanometer thickness. Then again laser annealing, again deposition, and again laser annealing. Like that, layer by layer, we deposit and do the laser annealing to build up the full thickness of 600 nanometers. And that way, in fact, we are able, and then what is the situation? In fact, initially we found that only 120 nanometer got crystallized. This way, with the 120 nanometer thickness, 5 layers we have done. That way, we have built up a 600 nanometer thickness, and let us see what happens. Now, what we can see is the red response is for the film deposit to 700 degrees Celsius in situ crystallization, and the black line this gives the as deposited response for 300 degrees Celsius film. And but what we are seeing is this one, that this on the right side in this graph, what we see is what the bottom, the black response is basically layer by layer deposited films prepared at the 300 degrees Celsius on fused silica substrate. See, when we have a layer by layer deposition we have done, they get well crystallized, and this is the same thing deposited on platinum silicon. That's also well crystallized. And in this bottom figure, what we see is this figure A is for 1 layer, B is for 2 layer, C is for 3 layer, then 4 layer, 5 layer. 5 layer we get good crystallization. See what happens. See here, what we can see is this is at the top one is for as deposited film at 300 degrees Celsius. That is amorphous. Then this films which are in situ crystallized, that is at 700 degrees Celsius. That is the middle one. Then the bottom one is the layer by layer deposited film. Deposit at 300 degrees Celsius and annealed at 300 degrees Celsius in the presence of a laser in a layer by layer fashion, and there it is well crystallized. It is almost, see, this response, the last response is very much similar to the in situ crystallized film. Therefore, we are able to, we are getting similar response by this layer by layer deposition process. Now, what we are seeing is, when you take a cross-sectional TEM, what you are seeing is exactly same feature is seen here. See, 5 layers, we can clearly see the layers and the boundaries. And this layer by layer, they are getting crystallized. That the interface, there is small boundary layer that we can see. Here we can see the columnar growth. So that basically, effectively, it becomes a full crystallized film, and it is showing up in the this TEM response. And the corresponding microstructure is also quite dense for this well crystallized 5-layer film. And correspondingly, their laser Raman response also for this 5-layer layer by layer deposited case, the laser Raman response is also similar to that of the well crystallized case. And the band gap also, what we can see is, see, Earlier, the band gap has come down only up to 3.86 nanometer electron volt. But now, for the in situ crystallized film, the band gap is 3.54 electron volt. But for the 5-layer, layer by layer deposited case, the electron band gap is 3.56 electron volt. It has almost become same. And in fact, see, with the 1 layer 3.85, then it becomes 3.75, 3.7. 3.62, 3. Like that. Steadily we can see the band gap approaching that of the well crystallized case. For that we can see here. For it is a very beautiful response for the progress of the crystallization. And correspondingly, when you look at the microwave characterization, here we see that see the layer by layer deposited films deposited on platinum coated silicon, they show the beautiful field dependent dielectric constant. This at a 0 volt we get this black response, at a 20 volt we get that red response, and at 40 volt by DC bias we get a blue response. And similar is the case, the bottom what is shown is for the as deposit in situ crystallized film at 700 degrees Celsius. Now what you are seeing is whatever we are seeing at 700 degrees Celsius film, similar the field dependent dielectric constant or capacitance we are getting for this 5-layer deposited films prepared at 300 degrees Celsius using laser. So finally it is coming to that value. And basically, but still there are differences. For example, for in situ crystallized films which are crystallized at 700 degrees Celsius, the tuning response, the field dependent dielectric constant or capacitance change is 54%. But for these films prepared at 300 degrees Celsius by 5 layers with the laser irradiation, the response, the field dependent change in capacitance is 34%. It's approaching, but still not at approach. That means further optimization is still required. Now, briefly, I will mention about the devices which are made with these PST thin films. Okay, this requires a lot of micro engineering. Therefore, I will not get into the details, but I will briefly mention what you have done with it. And of course, for as I mentioned, this tuning is an important aspect in the high frequency engineering. To change the frequency response, this is one of the very good. The change of capacitance is required. And for that, semiconductor diode is one method, ferroelectric varactor is another method, and another method is using RF MEMS, using RF MEMS diaphragm-based capacitors. They are mechanical devices, therefore they are slow response, but they are also good. So these are the 3 approaches which is available. At the higher frequencies, in the ferroelectric varactor's importance is keep increasing. And this is ferroelectric varactor we have developed. This basically the capacitor is in this part. This is the test structure. It's a coplanar waveguide test structure in which the parallel plate capacitor is here and here you can see. And this is the layout. The fabricated one is this one. After fabrication, this is the structure. Here and here we see the capacitor. And with that, the response which you get is like this. So this is the initial 0 volt response. As this is the 2 volt, this is the 4 volt, this is 6 volt, this is the 8 volt. As the bias field increases, the capacitance keep decreasing. Therefore, it becomes a varactor. And its frequency response is like this. This is another varactor, very similar. And this is a coplanar waveguide filter developed using these ferroelectric varactors. This is the layout, and this is the after fabrication. This is on MgO substrate. After fabrication, this filter, this layout, when you fabricate, it looks like this. And this is the schematics of the test structure. And now this another important device that is possible with these ferroelectric films is by making use of their electroacoustic response, because this velocity of electromagnetic waves is too high, so high. Therefore, miniaturization of these micro devices is better if we convert them into an electroacoustic device. That means because acoustic velocity inside the material medium is 5 order of magnitude lower compared to electromagnetic wave. Therefore, miniaturization, so that any frequency remains same, but the wavelength, the velocity is 5 order of magnitude lower. Therefore, the corresponding wavelength inside the material becomes too small. Therefore, for miniaturization in the micro range, it is easier if you go for the electroacoustic route. And one of them is a high overtone bulk acoustic resonator. In this case, Therefore, here what we are using is this BST capacitor and on a substrate. This capacitor acts as a transducer that creates electroacoustic, very electrostatic resonance, and that creates waves which is passed through the substrate and get reflected back, and finally we will get this kind of a resonance response. And that see here substrate is only around 600 nanometer. Sorry, film is only 600 nanometer thickness, but the substrate is around 500 micron. That's why we get a large number of modes like this. And okay, this is a fabrication process, which I will not go into details. Then this is the clean room which we use. That is where we do the device fabrication. And okay, this is the final response we get. And once you measure the corresponding the resonances, we get a large number of resonance peaks in the frequency response. And this is the corresponding impedances. And if we look at the narrow range, this impedance variation will be looking like this. And this is called high overtone bulk acoustic resonators. It gives a large number of the sharp peaks, and some of these peaks, their QL is so high. Here the device dimension is only 250 micron by 250 micron, but some of these resonance peaks gives QL is as high as 35,000. At 1.6 gigahertz frequency, we got a resonance. We got a QL here.
I want to attend one of my collaborators. Tell me, everything okay? Do you want to sleep?
Okay, and I will finish in a few minutes. Okay. See, some of these resonance peaks gives Q values as high as 35,000 at 1.6 gigahertz. And
hello. No. Please keep your panelists. Please keep your audio off. Hello, analyst. Please. Hello, analyst. Please keep your audio switch off.
Okay, therefore.
Mommy, and then Friday, and then you.
Who is there? Sorry, James. I am just.
Okay. You want me to go to bed now?
Okay, that see at this dimension, see to get in the those who are aware of the microwave circuits, they know that getting high QL in the microwave is very difficult. Here in 250 micron by 250 micron area, we are able to get a structure in which QL is 35,000. That is very important in the case of quantum acoustic devices. They are used in quantum computing. Therefore, our ferroelectric community is able to contribute to the this quantum computing world through these high Q resonators. That it is an important point for students to note that is quantum computing is an important area coming up in which this. Okay, this is a later work which he published recently. And in quantum computing, in fact, one of the qubit this structure is based on this squid, and this squid to couple to the squid, we need this kind of a high Q resonator. Therefore, the H bar coupled to the squid becomes part of the qubit assembly, and this is gallium nitride substrate. This H bar on gallium nitride substrate. This also contributes to this. Quantum acoustic devices meant for quantum computing, and this is the high frequency characterization setup for these devices. And okay, this is basically the theory aspects of it, which will not get into that right now. In fact, basically it has more to do with these pyroelectric films become piezoelectric under the influence of an electric field, and that piezoelectric response is different from the normal piezoelectric response. These are the details of it, and these are the responses, the high Q responses which you get. See, because as I mentioned, this ferroelectric is tunable. Therefore, same response we are getting here also. Under zero bias, we get this red response. As we increase the bias field, it becomes piezoelectric. Then this high overtone bulk acoustic resonance start coming. And as the bias field increases, this resonance responses increases. Therefore, we get a field dependence response. That is why it varies like this. The right hand side is basically the corresponding impedance. And these are all over a narrow frequency range. When we expand, it will be like that. And see, this is an important aspect. There on the back side of this resonator, when you coat it with a polymer, we see the response changing from the left hand side to the right hand side. See, we see when there is a additional material coated, its response changes. Because of that, the response changes like this, and therefore it becomes a sensor. So see, basically, with more thickness of the polymer layer coated, the response changes. Therefore, this high overtone bulk acoustic resonator, this way can be used as a sensor. That is published recently in IEEE transactions on ultrasonic ferroelectrics and the frequency control. So published just 2 months back. And so in conclusions, you can say that BST thin films are crystallized at 300 degrees Celsius using a laser annealing process. The reduction of 400 degrees Celsius is achieved from conventional processes, and it is quite helpful in integrating ferroelectrics with the silicon technology, the nano regime, and also with the polymers for flexible electronics. And laser crystallization is limited to about 120 nanometer thickness. This limitation is overcome by a layer-by-layer annealing process with laser. And laser annealing did not give full crystallization, but islands of crystals embedded in an amorphous matrix is showed in the microwave characteristics of the films. And using the BST thin films, microwave reactors and tunable filters were developed. Tunable high overtone bulk acoustic resonator devices were fabricated with the BST thin films, giving Q values as high as 35,000 in an area of 250 micron by 250 micron. And H bars coated with a polymer layer gave drastic and characteristic variation, enabling H bars to be used as a sensor. And the acknowledgements are with the funding agencies, DST, DRDO, and Institution of Eminence Program of MHRD given to University of Hyderabad. And the postdoc involved with the work is Ajit Kumar. The scholars who involved in this work are Pundrikam Gaud and Ramakant. They are the physics students, and Sandeep Sharma is an electronics student. In our group, you have both electronics students and physics students. Together, they made the films, they made the process ready, as well as they made the devices. Thank you.
Thank you.
Thank you. Very nice lecture, and open for discussions.
Participants, queries, still you have not typed any queries here. Participants, please type your query in chat box. It's because I have not received any queries on this. Okay.
Can you hear my voice, Pasita?
Yeah, sir. Your voice is clear. You can.
Any question?
Because no question I have received.
Okay. Shall we cover this talk now, or wait for some time?
You conclude because there is
no. If they want, they can also consult Professor James Raju by email. That's also there, That's also they can do it. Okay. Very nice.
Sir, in fact, there is one aspect that is in India, somehow these works are not taking off. We are still mostly in the bulk.
The facilities, lack of facilities also.
It is really difficult. So much of disciplines coming together. And our current situation, the country is not that encouraging to get so many things organized together.
Very nice. You are quite helpful to people, So very thankful for your lecture, Professor James Raju. God bless you, and we'll see again,
Thank you, sir. Thank you, sir, for your blessing.
Okay, good. God bless you. Okay, thank you. So, Smita, can we proceed for paper presentation?
Yes, sir. So I again say that thank you, sir, James, sir, for this interesting lecture. Okay. So now we are going to start the oral presentation. This session though I don't have contributory, but oral presentation. The first oral presentation is going to present by Samarnika Das. The title of her presentation is Enhanced Dielectric and Ferroelectric Property of Surface Hydroxylated BZT, BCT, PVDF, HF Polymer Composite for Energy Storage Devices. So, Samarnika, you start your presentation. I will change you. I make you presenter.
It's about for 10 minutes, right?
Time for your presentation is just 10 minutes.
Okay, in principle.
Yeah. नीचे आ जाता ना तो उसको शिफ्ट कर सकते क्या? डायरेक्टली उस पर क्लिक करके हो जाएगा? एक मिनट।
Now sharing is not
या 1 मिनट। वो नीचे चला जाता ना मेरे इसमें, समथिंग इट्स गो कमिंग डाउन सो आई कांट सिलेक्ट हर। इज इट पॉसिबल ऑन योर लैपटॉप?
now it's also.
Yeah, you got, okay, you continue now, okay. अच्छा,
Okay, my sound is audible now?
yes, you can audible, you start, Smarika.
Okay, thank you, ma'am. Good morning to all. I am Smarika Das from NIT Rourkela. Today I am going to present a talk on enhanced dielectric and ferroelectric properties of surface hydroxylated VGT-VCT PVDF HFP composites for energy storage devices. These are my outline of talk, in which first of all I will give some idea regarding the importance of polymer composites, then what is the necessity of surface modification of ceramic particles, then material under investigation, our selected objectives, result and discussion, followed by conclusion and references. Ferroelectric ceramics are widely used in RAM sensor actuators and in high energy density capacitors. Here we are mainly focusing on energy density, which can be calculated using this equation. To achieve an enhanced energy density, the material must possess a higher dielectric constant and breakdown strength. As we know, ceramic particles shows higher dielectric constant, but it shows relatively small breakdown strength, and it is highly brittle in nature, which limits its application in high energy density capacitors. On the other hand, polymer shows high breakdown strength, and it is highly flexible in nature, but it shows relatively small dielectric constant, usually less than 10. So by combining both ceramic and polymer in proper ratio, ceramic polymer composites can be formed which shows high dielectric constant with low loss. It shows high breakdown strength and high energy, and it is highly flexible in nature. There are a lot of ceramic polymer composites are present, but among them, the polymer composites which show high breakdown strength and high density can be applicable to transducer, high energy density capacitor, and cable accessories. But there are some problems in ceramic polymer composites, that is, it shows high dielectric constant at higher filler section, which creates pores and voids in the material, which results into small dielectric constant, and it further reduces the mechanical strength and flexibility of the material. The mismatch of surface energy of filler and matrix creates agglomeration in the matrix, which further reduces the breakdown and energy density of the material. Along with the polarity difference between the filler and matrix creates agglomeration of the filler in the matrix, which reduces the breakdown strength and energy density of the material. So surface modification of the ceramic particle is one of the suitable approach to overcome such drawback, which minimizes the agglomeration of the filler, reduces the material complexity of the filler, enhance the dispersion of filler in the matrix, improves the interfacial interaction between filler and matrix. These are some of the different processes of surface modification of ceramic for such process. These are the stabilizing agents. Among these, we have chosen H2O2 because it is an easy process and plenty of hydroxylic group can easily attach on the surface of filler. So we have prepared ceramic polymer composite by taking HFP as polymer because it is highly flexible in nature. It shows high chemical stability which improves dielectric and ferroelectric properties. It shows high breakdown strength. On the other hand, we have chosen 0.5 BGT-BCT as our filler. It is a MPV composition of BGT-BCT around which an enhanced dielectric ferroelectric PGT properties is observed. These are the material under investigation, in which first of all we have prepared BGT-BCT, then its surface is modified using H2O2, and by using this modified filler we have prepared different polymer composites for different filler sections. These are the characterization techniques which I have followed during this work. Then it is our selected objective, in which we have prepared BGT-BCT using auto combustion technique. Its surface is modified using H2O2. Then using this modified filler, we have prepared polymer composite using solution casting technique. Then we have studied structural, microstructural, directive, ferroelectric, and vibrational properties of polymer composite. Then this is the flowchart for the synthesis of VGT-VCT using auto-combustion technique. This is the flowchart for the synthesis of polymer composite using solution casting technique. To first confirm the effect of successful surface hydroxylation on VGT-VCT, we have studied FTR, in which a sharp band is observed around 517 centimeter. This corresponds to metal-oxygen bond. This is present in both modified and unmodified. However, after modification, a broad band is observed around 3445 centimeter, which corresponds to waist-stretching vibration. This band is not present in unmodified VGT-VCT. This confirms the successful hydroxylation of VGT-VCT. To further study the successful hydroxylation of VGT-VCT and its effect on structural property, we have studied the X-ray diffraction, in which there is no crystal changes observed, but there is a inhibition. To further study the effect of hydroxylation on morphology of VGT-VCT, we have studied TM, in which we observe in unmodified VGT-VCT, the particles get agglomerated. However, after modification, the agglomeration will be minimized and the particles are well separated with each other. From HRTM image, we have calculated the D spacing and which is well matched with the XRD data. After modification, we observe that a slight decrease in D value is observed. Then this is the room temperature XRD pattern of polymer composite for different filler section. In a pure polymer, along with the crystalline peak, a broad background hump is observed, suggesting the semi-crystalline nature of the material. After the incorporation of VGT-VCT in polymer, along with corresponds to polymer, the peak corresponds to VGT-VCT are also observed with a mark in star, confirming the composite nature of the material. With the increasing filler section, this beta phase, the intensity of the beta phase increases with a decrease in the intensity of alpha phase up to 15%, and above that a reverse trend is observed. So to quantify this, we have calculated the intensity ratio between the beta phase and alpha phase and observed a maximum value for 58%. Then we have calculated, we have deconvoluted the XRD pattern into crystalline and amorphous peak and calculated the crystallinity using this equation and observe a maximum crystallinity for 15%. So after modification, we are expecting this enhanced beta phase section and crystallinity further enhance the dielectric and ferroelectric properties. Then this is the microstructure of polymer composite for different filler section. Here we can observe a smooth surface for polymer composite. However, after addition of VGT-VCT, the distinct ferrulites are observed. In modified composite, the particles are homogeneous with some amount of porosity. Further study the effect of hydroxylation, we have plotted the 15% modified and unmodified composite, which is shown here. Here we can see the particles are agglomerated in unmodified composite with no number of porosity are observed. However, after modification, the agglomeration will be minimized and it is uniformly distributed and less amount of porosity is observed. So this confirms after modification, better dense microstructure is observed, which we are expecting and further enhance the dielectric and ferroelectric properties. Then we have calculated its density of the modifier of a maximum density of 94% for 15% composite. Then we have the FTR of polymer composite for different section. These are the bands which correspond to the nuclear alpha phase, and these are the bands which corresponds to the polar beta phase, and this is the band which corresponds to the gamma phase. These bands are already assigned in the figure. Among all the phases, the scientifically beta phase is more important because it shows higher dielectric ferroelectric properties. As we observe from this figure, with the filler friction, the intensity of this beta phase increases up to 15% and above that this decreases. To further calculate this, we have calculated the beta phase section using Beer-Lambert's law and observe a maximum value for 15%. Along with this, we observe with the increasing filler section, the vibrational band, this vibrational band has slightly moved towards lower wave number region, suggesting a strong interfacial interaction that taking place between filler and matrix. So from this we confirm that after modification, a better interfacial interaction taking place between filler and matrix. From FTR study, we have proposed three interactions that taking place between modified filler and polymer, that is electrostatic, dipole-dipole interaction, and hydrogen bond formation, which gives rise to an enhanced beta phase reaction. This improved beta phase reaction and crystallicity further enhance the dielectric and ferroelectric property. For 58% composite, we observe a maximum beta phase reaction and crystallicity of the matrix. Then this is the room temperature dielectric properties of polymer composite for different filler section, in which we observe the dielectric constant of loss decreases with the increasing frequency, which is a typical behavior for polar dielectric material. To further the effect of surface modification on dielectric properties, we have plotted the room temperature dielectric constant and loss for modified and unmodified composite. It is observed that for unmodified composite, a maximum value of dielectric constant is observed for 28%. However, after modification, maximum value is observed for minimum filler section, that is for 58%. After modification, the dielectric constant enhanced due to the enhancement of beta phase section and crystallinity of the material. Similarly, a higher loss is observed for unmodified composite, but after surface modification, this loss value decreases 2 times less as compared to unmodified one. This is due to the minimization of agglomeration of filler and minimization of porosity amount present in the composite. Then we have studied the ferroelectric properties of polymer composite for different filler sections. This is the viscosity loop of polymer composite for different filler sections, in which a maximum remnant polarization for 58% is observed. As I have already discussed, we are mainly focusing on energy storage density, which we have calculated using this equation, and we observe a maximum energy density for 15%, which is found to be 28 millijoules per centimeter cube. This confirms that this material will be further used as a density capacitor. Then conclusion. Surface modified BJT with polymer composite are successfully synthesized using solution casting technique. The structural analysis confirms the composite nature of the material. Estimates confirm the homogeneous distribution of filler in the matrix. From FTR analysis, we study the interfacial interactions that taking place between modified filler and polymer matrix, which gives rise to an enhanced beta phase reaction and is further enhanced the dielectric and ferroelectric properties. And improved dielectric and ferroelectric properties observed for 58% BCT composite, and for 58% composite, it shows an enhanced energy storage density of 720 millijoule per centimeter cube. These are my reference which I have followed during the work. These are my applications.
Very nice. Very nice. Very good talk. Any questions on the particular presentation? Well, there are no questions. I think she can be contacted by email in future. Thank you, Smaranika Das, for your lecture. Can you hear me? Can you hear me? Huh?
Yes, sir. Yes, sir. I can hear.
Good. God, very nice. Good lecture. Good lecture. And good information. Okay. Shall we proceed to the next people?
Next participant. Next participant. Make her presenter. बरं आपण मागच्या कोणत्या दिवशी बनवली होती मागच्या सॅटर्डेला ना लिस्ट
प्रिया कुमारी
Yes, sir.
Proceed.
Content. Sir, how can I share my content? That option is not.
Have you seen share screen? Have you seen share screen?
No, I could see.
Yeah. You just go on share screen.
Share screen.
That option is off here.
Yeah, okay, now I can see your picture.
Got it now.
Got it? Okay.
Yes, sir.
Then content.
Okay.
Shall I start now?
All right, now good. Go ahead.
Okay. Good morning, everyone present here.
Good morning, everyone present here. I am Priya Kumari. I am studying in Central University of South Bihar, and my today's talk the topic is X-ray absorption spectroscopy and X-ray magnetic circular dichroids investigations of VICO3 films. These are my contents. We will go through these one by one, and lastly we will conclude some results. Since I am working on a multiporoid material, that is VICO3, so I would like to explain briefly on the topic multiporoid. Multiporoid is the phenomena in which a material is called a multiporoid material if it exhibits two or all the three properties of primary poroid orders in same phase, namely ferroelectricity, ferromagnetism, and ferroelasticity. Here we can see from the figure, these arrows are indicating each other. This actually indicates that they are interdependent on each other. The applications of multiporoid are used in memory device and electric field controlled ferromagnetic resonance devices. Since my work is on bismuth ferrite thin films, so I would like to present here some physical properties of bismuth ferrite films. Bismuth ferrite is one of the most extensively investigated multiporoid materials, which has 6s lone pair electron due to the bismuth, which is responsible for ferroelectricity, and partially filled d orbitals of Fe that are responsible for ferromagnetism. Therefore, shows weak magnetoelectric coupling, which means that electric polarization can be influenced by the magnetic field, and the magnetization depends upon the electric field. It shows ferroelectric behavior at Q temperature 1083 Kelvin and nearly G-type spiral antiferromagnetic behavior at near temperature 653 Kelvin. Its melting point is nearly 1098 Kelvin. Researchers found some problems in synthesis of VICO3 films. Let's see what are they. It has a narrow temperature range of stabilization for DI since it is volatile in nature, and it requires accurately controlled oxygen partial pressure. Otherwise, it will lead to the formation of impurity phase like Fe2O3 and Bi2O3. And obviously, this impurity phase will degrade the sample in following ways, like it will show low resistivity of samples, high leakage current, and unsaturated electric hysteresis fluid. Our work aim was to firstly prepare a relatively pure bismuth ferrite thin films by using chemical solution deposition method, and to study the electronic and magnetic properties of VFO films by using X-rays and extensivity techniques, and also to study the effect of vacancies and strain on magnetic properties of VFO films. These are the steps for sample preparations. You can all have a look on this. Okay, moving on. Allow me to share the experimental techniques that we opted for the VFO thin films preparation. X-ray absorption spectroscopy. It is the measurement of photoabsorption by excitation of a four-level electron into unoccupied states as a function of photon energy. From the figure, we can see that there is a transition of electron from p orbital to d orbital, and its intensity is given by this formula known as Fermi-Dirac formula, where P is dipole transition operator having selection of L is equal to plus minus 1. And moving on to principle of XM3D, when right-handed circularly polarized X-ray and left-handed circularly polarized X-ray are irradiated on a sample under applied magnetic field, we get the difference between the absorption intensities for left and right circularly polarized X-ray that we know as XM3D. Its advantages are they are element specific, that is, each element has a particular binding energy. So if we provide that corresponding energy, then we can have that element's magnetization. And also it is sensitive to local electronic structures. And moreover, XM3D can be used to investigate the spin magnetic moment and orbital magnetic moment separately. By some rule, this is the formulas for orbital magnetic moment and spin magnetic moment. Okay, moving on. Measurement. These are the following measurement conditions. This sample was prepared using 650 nanometer of thickness of DI3, which were deposited on SRTiO3 substrate, and photon energy was taken of range 700 to 805 electron volt, and the temperature was kept at 300 Kelvin, and pressure was kept at 10 to the power minus 10 torr. Since we have Fe as a transition method, so we have obtained X-ray spectra for Fe223d of BiFO3 thin films. Here we can see that there are two peaks of Fe, which indicates that it occurs due to spin-orbit coupling. And we have compared our Fe223d X-ray spectra with alpha Fe2O3 and Fe3O4. And lastly, we concluded that since the X-ray spectra of BiFO3 thin films is similar to those of alpha Fe2O3, so we can conclude that the valence state of Fe is +3 here. The difference of X-ray spectra gives us eccentricity, and here we have shown the eccentricity Fe223 spectra of BiFO3 thin films, where we compared our graph with GaFeO3, gamma Fe2O3, and Fe3O4. And from here we can see from the figure that GaFeO3 have Fe+3 ions at octahedral sites, while gamma Fe2O3 has Fe+3 ions at octahedral sites and as well at tetrahedral sites with ratio 5:3, and Fe3O4 have Fe+3 ions at octahedral sites and tetrahedral sites with ratio 1:1. By comparing these graphs, we concluded that the eccentricity spectra for BiFeO3 is similar to those with GaFeO3. So thus, we can say that Fe is at octahedral symmetry for BiFO3 thin films. Moreover, the large eccentricity intensity that we can see here, it occurs here, could be due to the annealing in nitrogen that leads to the occurrence of oxygen vacancies, which in turn compensate the bismuth vacancies created due to bismuth volatilization. And thus, the increased ferromagnetism in Fe+3 is due to the large Canting angle in rhombohedral phase. Using the parameters of sum rule, we deduce the total magnetic moment of Fe in BiFO thin films, which was calculated of value 0.19 MeV per every atom. The eccentricity peak intensity remains high down to an applied set of 0.2 Tesla, indicating that ferromagnetism exists in our sample. The lattice distortions with the off-century movements of Fe+3 octahedral sites includes the large orbital momentum that we observed in our sample. These are the conclusions that we draw lastly. And from X-ray spectra, we concluded that Fe ions in our film was in +3 valence state, and the magnetization in BiFO thin films come from the ferromagnetic Fe+3 ions. The increased ferromagnetism of Fe+3 of BiFO is mainly because of the increased Canting angle of Fe+3 spins within the rhombohedral phase. Since we have worked on the surface sensitive TEY mode, so in future we are looking for bulk sensitive TEY mode work, which is for which we require to understand the bulk properties properly. We will go for that in future. I would like to thank my project supervisor, Dr. Vijay Singh, for his guidance, cooperation, and support, and providing us all necessary facilities. I would like to thank our CSB friends, Mr. Mohammed Lutfi Razwan, and all other my MSc third physics third semester students. And we have got national and international support, and the financial support was given by UPSC VSR and SRDST for this program, and also DFC India for the financial support, and the GNCSR Bangalore for management of teaching. Thank you.
Good presentation. Where is this facility located? This X-ray absorption?
Sir, in Japan.
Okay, but compared in XPS, X-ray photoelectron spectroscopy, how much of this information is available through that technique?
Sorry, sir?
See, using XPS also you can get the ionic state and things like that.
Yes, sir.
Then compared to XPS, What is the advantage in going for this technique?
Sir, we have used DE mode, that is surface specific mode. And we have got that excess spectra to spin out the coupling.
Okay. This technique can be applied even on a film.
Yes, sir.
Now, is there any restriction on the sample size?
No, sir.
Okay.
Thank you, sir.
You have to apply for beam time?
Yes, sir.
What is source they use? Are they using this synchrotron source?
Yes, sir. Spring 8.
Pardon?
We have used Spring 8 that's the logo here in measurement condition slide. That's located in Hiroshima in Japan.
Okay.
Yes, sir.
Okay, thank you.
Thank you so much, sir. Sir, any other queries? Hello?
Dr. Smith, I think now we can go to the next presentation.
Our next presenter is Chinmay Das. Chinmay, please start your presentation. And please on your video. Hello? Hello?
Yes.
I'm audible, sir.
Yes, yes. Who is speaking? Chinmay Das or which?
Chinmay.
Right. Please carry on. Okay.
Thank you, sir. Thank you, ma'am.
Okay.
Good morning to all of you. I am Chinmay Das. I'm from National Institute of Technology, Rourkela, and today I'll be talking about a dielectric study of microwave irradiated Sanim fiber reinforced epoxy composite. So these are my plan of talk, and I will discuss this. I will cover it one by one. So this is what we call a fiber, and what we can see in front of you. This is a fiber, all kind of fiber. There is nerve fiber, hair fiber, plant fiber, animal fiber, and mineral fiber. And how this fiber is defined? This fiber is mainly defined by, or it is mainly defined by from its aspect ratio. What is this aspect ratio? Is length per diameter, and this aspect ratio leads to decides the strength of the fiber. And my special interest is on plant fiber. So this is my material of interest, and which is Sanim fiber. Sanim fiber is mainly a bast fiber. Okay, this is general information, and mainly this fiber is extracted from the stem portion of the plant. And the Sanim fiber, the main constituents of this fiber, all the plant fiber is cellulose, hemicellulose, and lignin. So all this combined together, it's called cellulosic fiber. The other chemical constituents of this fiber are pectin and lignin. So we'll discuss how these constituents affect the property of the fiber and its composite. This is the property of the fiber, and this is the epoxy for the thermo setting matrix I used for the fabrication of my composite. These are the general information. So this is the fiber property. Mainly the natural fiber is it is available abundantly, and also how chemical composition is another question, because there are so many natural fiber available surrounding us, and depending upon the chemical composition also the fiber properties varies. And another properties are moisture content, stability of temperature, strength, sunlight resistance, weight, and its price. And if we talk about the composite property, the final composite it is very cost effective. It is also biodegradable. It has good chemical resistance, offers good fatigue resistance. Strength is good, and also it offers good electrical and thermal insulation, low density, high strength to weight ratio, and finally lower pollution level during processing, because we are dealing with a natural fiber. And so this composite, we know that we all know this composite is multi-phase material and which macroscopically identifiable, and it has two biphase, like another is reinforcement and another is matrix. So why should we go for the natural fiber composite? If we direct made composite from its raw phase or from its raw position, raw state, then what kind of problem we can meet? First is high water and moisture absorption. We know all the plant fiber are very susceptible to water and moisture absorption. So this water and moisture absorption will lead to poor wettability when we combine with the matrix. And also this poor wettability will lead to the lack of poor fiber matrix adhesion, and which ultimately will have the lower durability of the composite product. The other constraints are low temperature resistance, fiber loading and orientation, and enormous variability in properties. So all this, so for this we are dealing with various modification techniques. So this modification may be physical, may be chemical, may be physicochemical, may be enzymatic. So where we are mainly aiming at that, if we modify the fiber matrix adhesion will be get enhanced, or we are aiming that, and it will may improve the different properties of the end use product. So here I have adopted the microwave pretreatment for the treatment of my fiber. Actually, we do many kind of treatment like chemical, physicochemical, but microwave is one of them. It is a physical treatment. So here we have done what we have done. We take some fiber in quantity, and we have heated it up to a different power and in different time periods. Like currently we have done 160 watts, 320 and 480 watts for 2, 6 and 10 minutes. So we'll see how it is affecting the different properties of fiber and composite. So this is the agenda of composite manufacturing, composite that we have adopted hand layout method. And in hand layout method, we have first sonicated the epoxy, and then we have degassed it 80 degrees, and we have mixed with the epoxy hardener, which is the accelerating agent, curing agent, 10:1. Then mix the fiber, and we have done the fan layout method technique to fabricate composite. This is the basic step-by-step composite fabrication. First, here actually we have taken a plastic. We have made a cylindrical mold in order to give the circular shape to the specimen, because in palletizer, since cured epoxy is brittle, so it is hard to make the whole composite in the palletizer. So we made a plastic cylindrical mold. And here we spray some silicone spray so that the epoxy removal of final composite will be easy. Then final solution is poured, and after 24 hours querying, we got a final composite. This is how it is shown. The diameter of 15 mm and thickness of 2 mm. And this is the clear final sample. So coming to the result discussion part, this is the XRD analysis, and if you can see, all the peaks looks like same, but This is good. Why good? Because this is the basic signature. If I think this peak means this is the signature of all cellulose materials. If this peak, this two peak is not coming, then this material is not cellulose. So then what is the difference? Difference is the crystalline index and size. So how we calculate a crystalline index in our part? We have chosen a Siegel's method, from which we have taken the basic. You can see the 002 plane, which is highly intense. So we have subtracted the intensity of this 002 peak, and we subtracted from this value between 101 and 002 plane, and subtracted and divided we divided it by the intensity of the highly intensity peak, and we got all the crystalline index values. And crystallite size is calculated with Taylor formula. If you can see, the values are increasing as we go, increase our power and also time, but after some time it is decreasing and again increasing. So this is not a random this is not a random answer result. This is because of why we are getting increasing crystallinity index size. That is because the amount of cellulosic arrangement in the crystalline domain. Mainly, this is a natural polymer and it is semi-crystalline material, where like our amorphous arrangement happen in the crystalline domain, and it is rearranged with the crystalline chain, and because of that we get the high crystalline size. And also, if we go for higher time, then it degrades the cellulose polymer chain and increase the amorphous cellulose content in the expense of the crystallite cellulose. That's because of that we are getting low value. But you will say if we can see, like 320 watt 10 m or 480 watt at 10 m, after decreasing it is suddenly increasing. Why it is so? Because mainly in the natural, pectin gives the flexibility to the fiber. So if I hitting at a high power or high time, what is happening? Pectin, lignin, and hemicellulosic level is decreasing. The level is decreasing. So and in respect to that, the cellulosic level is increasing. So it is rearranging again, and because of that, the crystallite size is increasing. This is from our FTL analysis. FTL analysis, you can see actually we did not see any major change in our peak. So what can we take over there? So our result was that this physical treatment did not change any basic nature of the crystalline. It did not change in the basic structure of the cellulose. So if we can see only that it is 2924 part, which is attributed to lignin content, CO stretching, that is might affected. But what we have seen, that intensity. This intensity was changing, intensity part, and it was shifting. That is because of the removal of non-cellulosic part, which is hemicellulose, which is lignin, which is pectin. That portion was removing. That's why the peak shifting was observed, but that did not change any basic structure of the fiber. So this is the FES analysis. If we can see the first picture, this is raw fiber, like it is without treatment, and other are treated. So if you can see, other fibers are looking like a splitted. It is splitting. This is what we aim. That is what is our we want. Because if there is splitting, then it is good for adhesive. It can adhere the epoxy well, and if the surface area will increase also in between the fibrils, then also it can absorb, or it can well bind with the epoxy matrix, so that the interface will get stronger, and so that we can get a good property in our composite. So this is the dielectric impedance analysis. Yes, so here the room temperature analysis we have done. So here you can see, as we go, as we raise the power time, the dielectric constant first it will increase and then it will decrease. The dielectric constant was decreasing, and correspondingly the dielectric loss also was increasing. That is because of that, because it is a polar material. So as we increasing the power, the polar group, the hydroxyl group was decreasing. So because of that, we are getting a low dielectric constant, and also the dielectric loss was increased. But higher irradiation time of microwave, it tries to degrade the cellulosic part. Because of that, the amorphous portion was creating again. It is recreating in the fiber structure. That is because of after coming 486 watt, it is again increased at the 480 watt of 10 minutes. So same goes for the dielectric loss spectrum. So So this is the conductivity. So see here also, as we increase the power, since the direct polar groups are decreasing, so our conductivity also was decreasing. That is because of the removal of the non-cellulosic component, which is not cellulosic, and also that the relaxation happened in the amorphous phase. So this is this is the impedance part of the composite study. So here also it is the result was inverse of the conductivity study.
Chinmay, you have to wind up fast. Your time is over.
Yes, ma'am, it's the last slide. Yes.
Yeah.
Or because of so now we got the high impedance because of the removal of amorphous polar groups upon treatment. So this is the Cole plot where we get a linear to semicircle portion, which is because of and it is shows the non-debye type of relaxation. This is the fiber dispersion in the matrix, and you can see the interface is getting folded in somewhere, and it is first 160 watt. It is good. It is not. We are getting no debonding here. Where the RS part is debonding, so it is also a evident of good strength of. It is actually the composite portion, FSM. And also here, finally in conclusion, okay, we have physically treated the Sunlight fiber and fabricated using the hand layout method, and the lowest value of dielectric constant may be due to the reduction of OH group and rigid interface, where it is increased and the increment is due to the reduction of the cellulose because of excessive heating. Okay, this acknowledgement. I am highly grateful to my Smita ma'am for giving this opportunity to present my talk or my work. My academic supervisor, Professor Dilip Kumar Viswe, for his guidance and help and useful suggestion. All the PhD scholars of my department for their kind cooperation during my research work, and am I ready for the presentation. Thank you. Thank you for all being here. Okay.
I have one question. So basically, how you calculated the crystallization index?
Okay, sir, I'm telling you. This is actually, so we have adopted the Siegel height method. In Siegel height method, actually, what I have done, this highly intensity part, which is 002 peak, where the actually crystalline polymetallic is highly oriented. So we take the intensity part of this, and we have taken the value between 101 like peak and the 002 peak, and we subtracted. Then we divided it again the intensity of the 002 peak. Then we got the crystallinity index.
That will give you the measure of the texture, no orientation. Will it give you the crystallization index?
Sir, actually, it is not exactly amount of crystallinity. It is a degree of crystallinity. How much percentage is present? If we want to calculate the amount of crystallinity, we go for open study. So we have to do NMR. We have to do some what is we call it is NMR study. We know that. But if you want a degree, then we adopt the Siegel height method with some height method, intensity calculation, intensity height method.
Okay. Okay. Thank you.
And there is another question: what is difference between energy density and energy storage density? Maybe I think it is not related to your oral talk, but if James Raju or VRK Murthy interested to answer this question, can you enlighten, sir? What is difference between energy density and energy storage density?
See, with respect to context, it can change. See, energy storage density generally we attribute to capacitors. That the amount of energy stored in a capacitor or some other storage system per unit volume. But the energy density, for example, in a laser beam, energy density is one thing. In a microwave beam, energy density we can define. Therefore, what I would say, energy density, when we say, generally it is more associated with the beam. But energy storage density is more associated with a battery or a capacitor, like energy storage setup. That's what I understand.
Okay, so Praveen Khadare has asked this question. I think he is satisfied. And crystallinity already we have given. So this session is over. And this session have, so VRK Murthy sir, can you conclude this session? VRK Murthy sir? V.R.K. Murthy. Can you hear me, sir?
You? 1 minute. Can you hear me now? No?
Yes, sir. Yes, sir.
Okay,
Yes,
good.
sir.
Okay, let me tell you. Today happens to be the 75th birthday of Professor Anand P. Chaudhary.
Yeah. Sorry.
Okay, can you convey our best wishes for his longevity up to 120 years of life, because Lord Krishna lived up to 120 years. So, can you convey NSFB wishes to Professor Anand P. Chaudhary?
Yeah.
Okay,
Yes,
good.
sir. Yes, sir. We organize one special program also for RNP Chaudhary.
Okay, good. Okay, good. Okay. Personally, thank you for giving me this opportunity to join this session. And then we have got inspired talks from all the people. God bless everyone. Okay, thank you very much.
Okay, thank you. So actually there is a tea break, but it's gets skipped because our second session time starts. Hello. Please make the attentive. Get unmute, so this can observe the noise. Now you make attendee mute. If somebody, what is the problem? No, whatever the attendees, oral presenter, we make panelist. I think due to that. Okay. So thank you, V.R.K. Murthy sir, for conducting the session.
Sure. Okay, sure. Please carry on.
Please make it.
Please carry on. Okay.
Yeah. So now we are going to start the next session, session 5. Again, the name of the session 5 is Material Design and Processing, and the chairperson for session 5 is Dr. Neeraj Khati. He was the registrar of RTMNU and professor, Department of Chemistry, LIT Nagpur. So I welcome Dr. Khati to take the charge of this session. Sir, Dr. Neeraj Khati, can you observe me? Sir, please keep your video on. Dr. Neeraj Khati. Khati sir, hello.
Oh, madam.
Okay, welcome. I just introduced the chairperson, Dr. Khati. Khati sir, actually there is small change because SM Yusuf sir is unable to join. He's trying, but due to he is in BARC and there is some security in his computer, due to that is unable to join the online meeting, but he's trying. So we first take the Pawan Kumar lecture and then wait whether the SM Yusuf is able to join or not. So Dr. Okay. Pawan Kumar, are you ready? Dr. Pawan Kumar? Pawan Kumar has joined, na?
Yes, ma'am.
Are you ready? Because still SM sir have problem. You are not unable to join there.
Okay.
He has joined, but he has not got the WebEx link operate in his computer due to some security issue in BARC. So are you ready? Can you deliver first lecture? Yes. And then we will. Okay.
Yeah, fine, sir. Fine, ma'am. I can start.
Okay. So actually, the Dr. Khati is a professor in Department of Chemistry, LIT Nagpur. He is earlier former registrar, and as well as the Board of Examiner Director from RTM Nagpur University. He is a good blend of education and administrator. He works as an administrator very nicely, as well as in education and research also is doing well. So I welcome Dr. Khati and just request him to conduct this session. This session have one plenary talk by Dr. SM Yusuf, then one invited talk by Pawan Kumar, one contributory talk by Hitesh Borkar, and 3 oral talks. So I request Dr. Khati to please conduct the session. The first, we are just interchanging first Pawan Kumar and then SM Yusuf is there.
Yes. Thank you, madam. Thank you. Good morning to all of you. Thank you, ma'am, for giving me this opportunity to share this session. Now, as certain slight changes that have been occurred in the program, so first of all, there is an invited talk from Dr. Pawan Kumar, Department of Physics, NIT, Rourkela. Sir, I want to give a brief introduction for others. Dr. Pawan Kumar, working as a professor in Department of Physics and Astronomy at National Institute of Technology, Rourkela, Orissa. He has received a PhD from the Department of Physics, IIT Delhi in 2004. He had been awarded a BICAST prestigious fellowship by DST at Penn State, USA for the year 2007-8. He has a research experience of more than 20 years and 16 years in teaching field. His research interests include synthesis, characterization of bulk, thin and nano-functional materials, composite systems by various synthesis techniques like solid-state reaction route, chemical route, combustion techniques, microwave processing, and more than 8 research scholars have completed PhD under his supervision. So he has been guiding 9 PhD students. He has many research projects, and the 9 research projects are sponsored by DST, DRDO, and CP, STIO, Penn State, USA, DST from 2007 to 2019. He has more than 90 publications in international peer-reviewed journals. Several research facilities have been initiated at NIT, like hydraulic press, LCR meter, corona polling unit, 4 target RF sputtering unit. Sir has been the chairman and head of various administrative committees at NIT. He had been organized various short-term courses on conference. Now I would like to request Dr. Pawan Kumar sir to start his invited talk.
Yeah, thank you very much, sir, for introducing me, and thank you very much, ma'am and organizers, for giving me the opportunity. Let me share my.
Yeah. Pawan Kumar, please make 1 minute, sir. Please. You can see.
Yeah, ma'am, please.
Yeah, have you got presenter? Can you see share screen? Because we have make you presenter now. There is share screen. You can share your screen. Share. Have you observed that cursor? Share screen cursor on your screen?
Yeah, share. Yeah, share is.
You just click on share. Then you can upload your PPT. You will have to open our PPT on desktop.
Yeah, already opened, ma'am.
Yeah. Then you after click on share, you can see your PPT there. You will have to just click on your PPT.
Okay, just a minute. I'm not able to see my PPT actually.
Sir, have you opened first the PPT?
Yeah, that is open in my screen actually.
Then it will get in share. After click on share, can you can't see your PPT window? Because after clicking on share, you can see your PPT window there.
No, that is not coming. I think I have to add or drag it. What?
You have to drag. No?
Just a minute, ma'am. Just a minute.
Yeah.
Just a minute. I think.
Yeah. Yes, your PPT is you are getting there. Open your PPT now. Just you open your PPT. Yeah, we can see. Now you go change in slideshow mode. Go to slideshow mode. It's okay.
Full screen is visible.
Yeah. We can easily.
Okay. So thank you very much for giving me opportunity to share some research work. So this presentation I will be talking about these metal modified ceramic polymer composites, particularly for high energy density and embedded capacitor applications. So first I'll be talking about the basics of dielectric constant applications for different ceramics, polymers, composites, then potential ceramics and polymer ferroelectric systems, and high dielectric constant ceramic materials other than ferroelectric materials, their shortcomings, and finally why we are going for ceramic polymer composites, and then metal modification of ceramic polymer composites. And so there will be three phases. So after each phase I will conclude actually, and there will be no as such final conclusion. So okay, so why this we are interested in this energy storage type of applications, because the present age is the age of the miniaturizations, and there we want that in a very small space, given space, we should be able to accommodate large components. So for that purpose, what we call as miniaturization, microelectronics, high volumetric efficiency, we means this the field of this energy storage means having high energy density, high power density, that becomes important. And these are the various applications of these energy storage materials. They are being used in electronic systems, mobile, cell phones, means all type of things. And these batteries and fuel cells, of course, they are for the. In the next slide, I'll be discussing what do we mean by short term and the long term actually. So here, this is this diagram tells us about various categories of materials, starting from capacitor, supercapacitor, batteries, and fuel cells. So these capacitors, they have very high power density, but their energy density is low. And the extremes, batteries and fuel cells, they have the high energy density, but their power density is low. So depending on our requirement, we choose a particular type of these materials, and if we want in between type of requirement, then we go for the combinations. And as in this presentation, we'll be talking about the composite systems, why we are going for composite systems. So now here, coming back to this energy storage property, that particularly the dielectric materials, high dielectric constant is required to, as Professor Raju was telling, that this is kept for energy storage, particularly this capacitor type of material, they are being used actually. So these dielectrics, they are being categorized in two categories, linear dielectrics and non-linear dielectrics. So, and this polarization versus electric field, this diagram, this tells us about the energy storage capabilities of these different kind of materials actually. So linear dielectrics, yeah, means figuratively their energy storage capacity is more compared to this non-linear, but their polarization is very low compared to these non-linear dielectrics, particularly compared to the ferroelectric materials. So and among ferroelectric materials also, there's what we say is that this is a typical characteristics of a relaxer ferroelectric material. They are very thin P loop actually. So among ferroelectric materials, this relaxer ferroelectric materials, the shaded portion tells us about the energy storage. Okay, so this becomes maximum for relaxer ferroelectric materials. And again, means this anti-ferroelectric materials, they have the means figuratively, by seeing this graph actually, they have the highest energy storage density in this dielectric materials. Why means like that? In the next slide I will be discussing about how it depends on this saturated polarization and the remnant polarization. So before that, this is in this presentation I'll be talking about the ferroelectric material, ferroelectric polymer composites, and I'll be discussing the non-ferroelectric polymer composites also. So this slide tells us about the various applications regions of ferroelectric materials. This ferroelectric material, they have a high saturation polarizations, and they have particular transition temperature, what we call as a TC, and the dielectric constant become maximum near the transition temperature. So this is the usual feature of ferroelectric materials. So depending on our particular type of applications, these ferroelectric materials are being used in different regions. Like for memory applications, we require high polarization. For pyro sensor, there should be large change in the polarization with change of temperature. So that feature comes near the transition temperature. And of course, for this high dielectric constant type of applications, the material, the best region is near TC, where the dielectric constant is maximum. So this is the feature of ferroelectric materials, and depending on our particular type of application, we go for particular region. So as I was talking about how this energy storage efficiency and energy storage that depends on this type of saturation polarization and the remnant polarization. So this in terms of this P loop, this efficiency is defined, the energy stored and energy loss in terms of that. So what we are seeing actually, for the maximum energy storage capability, the materials should have, as this here we can see that the material should have high dielectric constant, and of course it should have very high breakdown strength actually. So these are the requirements, and accordingly we choose or we design our materials to get high dielectric constant and high breakdown strength. So based on this only, we will be talking about this composites actually. So this is a kind of whole summary of these different type of dielectric and polymer materials in relation to this energy storage density applications. So starting from the ferroelectrics, of course, they have high dielectric constants, high saturation polarization, but they have moderate dielectric breakdown strength. So this they have this since this as I was talking about this stresses loop, the loop area is more actually in the ferroelectric materials, so their low energy density comes because of that actually, and efficiency, because of that efficiency also decreases, and if I go back actually, so from here I can tell for high energy density point of view, the material should have high PS and it should have low PR and possible S. So these are the disadvantages of these ferroelectric materials, which are somewhat overcome in case of relaxed ferroelectrics, since they have higher saturation polarization and low remnant polarization. But this disadvantages remains like their dielectric breakdown strength is low compared to the polymers that I will be talking about. Now, when we go for these anti-ferroelectric materials, so these disadvantages of ferroelectric material, they are somewhat overcome, because as per by their categorization, these anti-ferroelectric material, they have high saturation polarization and they have low remnant polarization. So that makes that high energy density efficiency higher compared to the ferroelectric materials. And but the disadvantages that there's properties, dielectric properties, the polarizations properties, they are field and temperature dependent. Okay, so now coming to this dielectric materials, particularly this rutile or alumina silicon oxide, this type of material, they have high dielectric breakdown strength, low loss, but the disadvantage is they have very low polarization value. And now means there are coming known ferroelectric high dielectric constant materials like CC2O, PF, and CNO. They have very high dielectric constant, and this dielectric properties are somewhat temperature independent. And that's what we want actually from application point of view, that the property should not vary with temperature actually. But disadvantages, they have very high loss, and hence they have low breakdown strength. Now coming to the case of polymers, their advantages, they are flexible, of course, so they can be used for the embedded capacitor type of applications. They have very high dielectric breakdown strength, and they have low loss. But again, as in the case of linear dielectric, what it was that their polarization value is very, very low actually. So with that, we might be getting what we means if we want optimum type of system for energy storage type of applications. So we have to go for the composites, which and we choose what we call as matrix and reinforcement, such that we combine the better properties of individual systems, and we come up with the required properties for our composite system. So here this what we say is that we take one of the matrix and one of the what we call as the filler particles or reinforcement, and so that I'll be talking what we are taking these particular systems. And so now this summarizes why we are going for this composite type of systems actually. This polymer, they have their own advantages. Ceramics, they have their disadvantages. And when we combine both together, and what we expect we should get means high flexibility, low processing temperature, relatively high dielectric constant. When we combine the high dielectric constant ceramic materials with the polymers, and we should get low dielectric loss because of the polymer, and of course we should also get high dielectric breakdown strength, and which means so here if we relate back for the requirement of this maximum energy density capacity with the polymer ceramic composites, these requirements looks fulfilled. So that is justified why we are going for polymer ceramic composition type of systems. So now again this tells just to highlight the importance of the ceramic polymer composites. That's this particular spacecraft that around 50% that these components are being composite in nature. So that tells us about the importance of this particular field of area actually. So now in this first part, I will be talking about kind of there are we can choose ferroelectric material, we can choose high dielectric constant material and combine with the polymer systems. So but choosing ferroelectric system with high dielectric properties, it has its advantage, it has its disadvantage. So I'll be talking about that. So in the the second part, I'll be talking about this ferroelectric polymer composites. Third part, I'll be talking about non-ferroelectric high dielectric constant ceramic with the polymer system composites actually. So okay, so now this is a kind of comparison between different properties of lead and lead-free materials. Nowadays we go for this lead-free type of systems. One of the students she completed this BZT polymer PVDF and epoxy composites combined with the CC2O finally to get the high energy storage properties. So here as one of the presentation is need not to discuss what this BZT is a very well-known system, well-known ferroelectric system, very important among the lead-free type of systems. It has very good dielectric and ferroelectric properties among these lead-free type of systems. So now among known ferroelectric dielectric type of systems, we define different class of this dielectric material based on their dielectric properties. So this basically from the applications based on the high dielectric constant. The material should have high dielectric constant, low loss, and there's a change of capacitance with temperature. That part should be as minimum as possible. Of course, the capacitance, the material should not change the frequency in the field actually. So this feature goes against the ferroelectric material, because in the ferroelectric material the dielectric constant changes like anything with the change of temperature. Near transition temperature it becomes maximum, and thus you go you move slight bit near the transition temperature, the dielectric property changes like anything. So that goes against the ferroelectric materials actually. So why we need to go for non-ferroelectric type of system, and of course these dielectric properties are frequency and the field dependent. So here this high dielectric constant, or what we call as the colossal dielectric constant type of materials, there are these the CC2O, this VFN, LCNO, this type of materials are coming up, and they have very high dielectric constant room temperature, more than 10,000, and these dielectric properties are temperature independent. That makes it very, very interesting. And of course, these dielectric properties are weak frequency dependent. So I'll be talking about that part also. This CC2O system, which is a well-known systems, very high dielectric constant values. So okay, so this I'll be and now finally coming to this polymer type of systems. There are different types of polymers are there actually, which have this PVDF. It's a unique polymer. It's ferroelectric in nature, and we can see here that their loss is low, but the dielectric property is also very, very low actually. So straight away we cannot use polymers for the this energy storage type of application. We have to combine with the this ceramics actually. So now here, as I told earlier, see that in this part means we have studied this BZT-BCT, which is MPB composition of this BZT-BCT system, and combined with the PVDF. So this overall this system becomes a ferroelectric in nature. So with the ferroelectric in nature, so this in addition to the this capacity type of applications, our composite retains the ferroelectric and the piezoelectric properties. So it becomes some it can be used for multifunctional applications actually. So this is that is the advantage of combining this polymer with the ferroelectric systems. If we purely want only for the capacity type of applications, these ferroelectric systems are not preferred actually, as I told earlier actually, because their dielectric properties are temperature dependent actually. Okay, so now we have synthesized this BZT-BCT with PVDF. These composites are being made actually, and from this XRD studies, what we have confirmed that both the phases, this BZT-BCT and the PVDF, both the phases are being retained, and as we increase our matrix is PVDF in this composite system, and reinforcement is BZT-BCT, and we are increasing the BZT-BCT components, and so their peaks are appearing, and so now this from this surface morphology study also, that we are able to see as we are increasing this BZT-BCT. Of course, I mean that what we means. I'm skipping that part actually, that we synthesize BZT-BCT. We after sintering we broke it and made it into the powder form, and then we mixed with the polymers and we made the composites. So now there's coming to this dielectric properties. If we see that with the frequency that what in this BZT PVD of composites, the properties are somewhat frequency independent in this particular case actually. When this and as this BZT component is increasing, the dielectric properties are increasing, and here what happens that we are able to, as we increase this BZT, we have gone up to 25% actually, and we have studied these piezoelectric properties also, and that's I'll be talking later on. And coming to back to this temperature dependent properties, we can appreciate that the dielectric properties are also somewhat temperature independent. Of course, since both of these phases are ferroelectric in nature, temperature dependency is there. But we have studied other ferroelectric polymer composite systems also. But compared to that, this temperature coefficient of capacitance is minimum. What we are getting in this BZT PVD of composites. And okay, so now we have fitted this dielectric properties of composite with various models, and we like there we take different types of the dimensions. We consider different shapes of these reinforcement particles, and based on that we fit the dielectric values, and this model fits well with the experimental data, and these are the various properties like the density, porosity, and we have also studied this energy band gap, this composite systems, and with the increase of the ceramic part, this density is increasing, and of course this porosity is decreasing actually. And as I was telling you that we have studied these piezoelectric properties also. We have already seen these dielectric properties. That as I was emphasizing, the purpose of keeping these ferroelectric ceramic reinforcement is that to get, in addition to the better dielectric properties, to retain the ferroelectric properties also, so that we have seen that we are able to get better this D3 coefficient is there, piezoelectric property is there actually. So this is the overall summary of this first part. Next I will be talking about non-ferroelectric and this polymer composites. So we from here we got better dielectric properties in the 25% volume fraction of the ferroelectric BZT systems, with the highest piezoelectric coefficients among the studied systems. So now in this part actually I'll be talking about epoxy CC2 first, and then we have further modified it with the aluminium to increase the dielectric properties further, and we have also studied this aluminium epoxy composites alone actually, means without this ceramic part actually. So that here this that what we are presently doing actually, this is the CC2 system.
Pawan Kumar, last 5 minutes. You just conclude fast.
Okay, ma'am. Okay. This so CC2 systems we have synthesized with the microwave technique actually. These are the various steps, and Professor Murthy sir also discussed about this importance of microwave systems. So I need not to discuss and how do we choose. It's a material specific synthesis process. So I'm just skipping due to time constraints. So okay. So these CC2 systems we have studied actually. As I highlighted earlier, it's a what we say the high dielectric ceramic material or colloidal dielectric consistent, which has very high dielectric constant room temperature, and which is temperature and frequency independent. And we synthesize this material by microwave technique, and they are being sintered at 1000, 1025, 1050, 1075, and the sinting time was 15 minutes only. So that's of course the calcination temperature also is being given. So we were able to successfully bring down the processing temperature and the time means drastically compared to the conventional process. And here we can appreciate the dielectric properties of this particular Cis2 systems, and as reported in the literature that we also obtained that in microwave synthesized Cis2 system, the high dielectric properties we are getting, but the thing is losses are relatively high compared to the ferroelectric systems. And we also studied why means in the system sintered at 1050, that we are, though there are secondary phases, but we are getting the higher dielectric properties. If somebody will be interested, I can talk about that. That's what we have studied and we have reported also. And because due to time constraint, I'm a little fast actually. So this is Cis2 system we have synthesized by microwave technique. We because in the next few minutes I'll be talking about we have combined with the epoxy composites. So these are the summary about which particular type of the Cis2 system sintered 1050 we are taking, because we are getting higher dielectric properties, and we combine the Cis2 reinforcement particles with the epoxy. This is a synthesis chart actually. So here let me tell the main part that what we are getting. We are getting this better dielectric properties. It's in the as we are increasing the Cis2 part, that we have gone up to 40 volume percentage, and the dielectric property increases, and of course the loss increases because loss is comparatively high of the Cis2 compared to the epoxy actually. And we have fitted with the different models also, and these are the electron micrographs which tells us about that this reinforcement is well homogeneously distributed among the composites. And now we have further modified. We have chosen the epoxy Cis2 composite having highest dielectric properties. Further, we have modified the aluminum reinforcement, and what we have seen that up to when the for 15 volume percentage, this aluminum we are getting the higher that shows the better dielectric properties. The dielectric constant is higher, the loss is lower, and the kind of percolation type of limit is coming actually. And we have fitted with the various models these things, and this is the micrographs what tells us about that this well distribution of reinforcement is there among the composites. And so can I continue, ma'am? Smita ma'am?
No, your time is over, sir, and SM Yusuf sir is there. And
okay, fine. So that's all from my side. Yeah, please.
Thank you very much, sir. Pawan Kumar sir, for your very good and informative presentation for the ferroelectric and dielectric composite material. It's a very nice thing that we all of get information regarding this. Thank you very much once again.
Sir, there is one question. Sir, there is one question from student. Dr. Satish, he is asking that what was the solvent used for PVDF dissolution, DMF or DMSO? What was the solvent used for PVDF dissolution?
PVDF, ma'am?
PVDF dissolution.
That just a minute. Maybe we use this DMF, ma'am.
DMF. Okay. So I think Satish are satisfied. Okay. So now, Dr. Neeraj, you can introduce the Dr. S.M. Yusuf.
Yeah.
Thank you, Pawan Kumar.
Okay, ma'am. Thank you very much.
Sir. Good afternoon, Yusuf sir. I welcome you on behalf of this organizing committee of this conference. Dr. S.M. Yusuf is working in Baba Atomic Research Center, Mumbai. Honorable Yusuf sir is a scientist and head of Solid State Physics Division, BARC, Mumbai. He is also professor in Homi Bhabha National Institute and Dean of Students Affairs. He has obtained his PhD in physics from the University of Mumbai. He was a postdoctoral fellow at Aragon National Laboratory, USA, visiting scientist at Institute of Material Sciences, Spain. He has expertise in the area of advanced magnetic materials and neutron scattering. He has guided 11 PhD students. Dr. Yusuf is also recipient of DSc Honorary in 2008, P.K. Iyengar Memorial Award from Indian Physics Association, MRSI ICSC Superconductor and Material Science Annual Prize, DAE Homi Bhabha Science and Technology Award, MRSI Medal, DAE SRJ Outstanding Research Investigator Award. He is an elected fellow of Indian Academy of Sciences and National Academy of Sciences India. He serves as Vice President of Indian Physics Association, Vice President of Indian Crystallographic Association, and President of Neutron Scattering Society of India. I welcome you, sir, and I request you to initiate your plenary talk.
Yeah, thank you so much. Yeah, thank you so much. I hope I am audible, right?
Yeah, yes, sir. Yeah.
Yes. Okay, first of all, I'd like to thank the chairperson for kind introduction, and without saying, Professor Smita Acharya for the kind invitation. In fact, I remember exactly 2 years back, she organized another meeting, and that time, of course, I could travel to Nagpur, and that was very nice meeting. And then again, after 2 years, this is another one. So she has been doing excellent job over the years, and so I congratulate her for this. And as chairman, of course, he introduced me. I could feel it that basically my whatever my status as of 2 years back, actually that is what he read out. Okay, just to tell that presently I am the Associate Director of the Physics Group of Bhabha Atomic Research Center, and also additional duty as Director of Institute of Physics, Bhubaneswar. Okay, so with this minor correction, let me start my talk. Yeah, and sorry that because from BRC we have this, as you know, the restricted facilities, so I could not connect it on time. I struggled for nearly 1 hour, and then I have come to Homi Bhabha National Institute outside BRC Anushakti Nagar. From there now I am speaking. So as a result of that, my talk has to be rescheduled after this half an hour invited talk. Anyway, so thank you so much. So let me start. The title of my topic is Structured Property Correlation in Ferroelectric Compounds. And that is what the theme of this meeting is, ferroelectricity and of course dielectric properties. So I will be touching upon this aspect, and it is, so I am starting at 12:15 or so, but I will try to finish within 1 o'clock my stipulated time, though it is 1 hour. Now when you talk about this ferroelectricity or multiferroid properties, if you take any material, and here of course we are talking about the spins which are there at the core spins, which are responsible for magnetic properties, as you know, and we have the lattice, underlying lattice, and the lattice vibration and the collective vibration gives you these phonons. And on the other hand, you can have these conduction electrons. Now, when there is interaction between these free electrons and the spins, so then electron spin coupling, and that gives various properties. By now you all know that one such property could be Kondo effect, could be colossal magnetodistance and so on. Similarly, when these electrons and the phonons they interact, that is electron-phonon coupling. So you can go to other regimes of physics, that is superconductivity, thermoelectric effect. But for today's purpose, we are restricted to this domain. Right? There is the interaction between the localized spins in an atom and ion, which are responsible for the magnetic dipole moment. So the spin and phonon, so spin-phonon coupling, that can give to the multiferricity. Of course, it can give other effects, spin-Seebeck effect and so on, which we will not be talking today. So for my today's discussion, today's talk, this spin-phonon coupling is very, very important. So I will be touching upon this part with some examples, and where I will be showing that a spin-phonon coupling is, in fact, it is there. And apart from that, looking at now, when you talk about the spin-phonon interaction, if you talk about the Hamiltonian, of course, you will have spin part, as I said, you will have phonon part, and the interaction between two, that is H interaction between spin and phonon. So if one is interested, students are there, we can see very old paper, the year when I was born, so you will get a lot of underlying physics of this. Now, when you talk about the multiferricity, so basically, as you know by now, the coexistence of two or more ferroic order in a material. Now, ferroelectricity, if you talk about that, that can have two types, type 1 or type 2. In type 1 is the improper ferroic material, and type 2 is the improper ferroic material. So in improper ferroic material, this strong magnetoelectric coupling is there, So here the magnetic ordering is induced by induced ferroelectric order, for example, TbMnO3, DyMnO3. On the other hand, if you talk about the no coupling between magnetic and electric order, so you can also have ferroelectric order in that scenario as well, due to the atomic displacement. For example, famous example is BaTiO3 or BiFeO3. So you have type 1 and type 2 in terms of the ferroic property, depending upon which regime you are. Now, the theme of this meeting, another is not only the ferroic, but the so-called dielectric. And in my today's talk, what I propose to do, I'll be mainly talking about the ferroelectricity, but of course I will do touch upon the dielectric properties, and I'll try to make a linkage, because I know particularly for students, this is always a question that they see very often, that dielectric property and ferroelectric property like two different things, there is no connectivity. And the facilities which are used, for example, for ferroic property, this is the polarization loop, electric polarization, spontaneous polarization, and on the dielectric side, one measures the dielectric constant. But I promise to make some linkage throughout my journey in another 40 or 45 minutes or so. Now, when we talk about the dielectric material, we have can have two kinds of material, polar and non-polar. And when, of course, we have the polar, then only we get this, then we can have so-called these ferroic properties, ferroelectricity. Now, dielectric polarization is defined, P is defined M by V, where V is the volume per unit volume, P is the polarization, M is the macroscopic dipole moment. Of course, here we are talking about the electric dipole moment, as you can imagine. And then P can be further written like this, epsilon naught multiplied by epsilon minus 1 and electric field E, where epsilon naught is the dielectric permittivity of the vacuum, epsilon is the dielectric permittivity of the medium which we are talking about, and E is the electric field. So it has got two parts. One is this polarization, dielectric polarization has got two parts, P alpha and P mu. And P alpha is basically this part is the translational effect, and P mu is the orientational effect. Let me clarify a little bit. When the charged particles are moving, some kind of diffusing, or moving. Okay, so translational motion is there, so that can cause polarizability. And but let us say you have a dipole moment sitting at a particular atomic or ionic site, and that can have different orientations or relaxations. So that is another part. So slowly I will be touching upon this aspect. So I wanted to introduce both the sides. See, I will not be hurrying up. When time gets over, please tell me, I will stop. But my intention is to bring some linkage throughout my journey about this ferroelectricity and this electric spontaneous polarization. So this nomenclature is required for both these purposes. Now, when I give the examples, there I will be trying to touch upon these points again and again. So first, let me start with a simple example, the spinel ferrites. You are all familiar with the ferrites. That is, for example, here it is cobalt, chromium 2, oxygen 4, but in chromium place 2 minus X, iron X. Iron is substituted. Okay, that it has different interests, but today's talk I will be putting with regard to what I want to speak on. So that is, let us say DC magnetization for this material as a function of temperature at different fields. If we, for different compositions of iron, if we plot here, what you see, X equal to 0 means purely chromium, there is no iron. It shows magnetization. This is a paramagnetic state. So magnetic ordering takes place, and this is a ferrimagnetic ordering, and then peak, and then it decreases, and so on. But you see, there is a transition here, a small transition you can see at this temperature, typically at 25 Kelvin. I will be touching upon this. But as you increase the iron concentration, for example, iron is 0.15, you see from the paramagnetic state, the magnetization, the blue one, magnetization is building due to ferrimagnetic ordering, goes to maxima, and then decreases, goes to 0, magnetization becomes 0, and goes to the other side, negative side. So this is one phenomenon we have been working over the years, and that is called the magnetization reversal phenomenon, negative magnetization phenomenon, and we have been working, and so here also we have observed that. But and of course, so this is a ferrimagnetic. We have got the microscopic understanding of this so-called how magnetization can be negative without having diamagnetism. Now, for that, see, for one particular composition, 0.15, we have done with different magnetic fields, applied fields, and as you increase the field, you see the negative magnetization decreases, and finally it becomes positive. What we expect in a conventional magnetic material, the magnetization should be always parallel to the applied magnetic field, not on the other direction. We have done detailed neutron diffraction experiment. That is what the facility we have at Bhabha Atom Research Center. And as you see, that magnetic intensity is adding upon, so that's how peaks are growing. And by doing the powerful Rietveld analysis, magnetic structure refinement, we have done for in ferrites. As you know, there are two crystallographic sites. One is called tetrahedral, and another is one is tetrahedral, and another is the something happened. Yeah, some problem. Yeah. Okay. Yeah, it's okay, right?
Yes, sir.
Yeah. So this is the tetrahedral side magnetic moment. What you see here at this temperature, it is getting ordered, but the octahedral side, it is ordering at much higher temperature. And of course, when the tetrahedral gets ordered, there is a hike, and then it is the octahedral. So this is one thing that what you see, that this is the deviation from the mean field approach. One sublattice gets ordered at higher temperature, that is octahedral, but the tetrahedral sublattice gets ordered at lower temperature. And when you take these two sublattice net moment, that is the green one, and green one shows the peak and so goes to 0 and then negative. So this is what is seen in the DC magnetization. So powerful microscopic neutron diffraction study, it explains that the observed that so net magnetization can be negative that is using this microscopic Newton diffraction technique. So I will not elaborate that because my purpose is slightly different in this talk. And then, one point I like to go back, what I just said. So this is what we are talking about, explanation of this, which is happening at this kind of temperature. But in the previous one, I have showed data much lower temperature, and you see around 25 K. See, negative magnetization is happening at this temperature, okay? Around 50 or 60 K. But at much lower temperature, around 25 Kelvin, there is another transition. Now I will be touching upon this lower tension temperature, that is 25 Kelvin. Actually, what happens, that is what I will present at 25 Kelvin or below. At this temperature, there is a spiral magnetic ordering. Until this temperature, this is a spinel structure, that is a ferrite structure, ferrimagnetic structure. But here, the spirality takes over. And that is what I am going to talk about. And that 5 Kelvin data, so here we see the extra magnetic Bragg peaks, which are representative of spiral spin ordering. By doing Newton diffraction we get, and we have calculated the tetrahedral side, the angle what is making, and the octahedral side, there are again two octahedral sides, B1 and B2, and what is the angle variation with this composition. Now if we summarize this, it means that the A side, that is where cobalt 2 plus is sitting, and in the B, that is A is the tetrahedral side, B is the octahedral side, we have chromium is sitting, but there is a two octahedral sides, B1 and B2, and you see that with respect to 001 direction, this moment is forming a angle. This is called canted angle, and here for the B side also it is like this, but this is a spiral. So this represents essentially a spiral structure, spiral magnetic structure. And you all know that in the literature, this kind of electric polarization, spontaneous polarization and spiral magnetic structure, they are coupled, and spirality dictates this kind of electric polarization. So that is what we are trying to address, how the spiral structure, spiral magnetic structure, and the polarization. Now for polarization, we have measured this pyrocurrent IP as a function of temperature. You see around same temperature, 25 Kelvin, you see this peak. And from there we have calculated the polarization in this inset as a function of temperature, and you see at this around 25 Kelvin, this polarization, spontaneous polarization occurs. So there is a one-to-one correspondence. This spiral magnetic structure which builds in around 25 Kelvin, and there the spontaneous polarization occurs. Okay, and so similarly, for not only for one sample, we have done also for other sample. And but interestingly, so this is as far the the ferroelectricity is concerned. Now the linkage now I am establishing. This is the ferroelectric property. This is a spontaneous polarization, and here is the dielectric measurement. Dielectric constant also shows this sharp change at the same temperature where the spiral magnetic structure sets in. So this is what we are here to publish this. And so in this example, basically we showed that how the spiral magnetic structure and the ferroelectric spontaneous polarization and the dielectric constant variation, how they are coupled. And in fact, we are doing little more quantitative analysis. We know the spiral angle, like what I just showed here. Spirality, spiral angle, how it is changing, and with that we'll be quantifying how this electric polarization is linked to the spirality. So that kind of detailed measurement we are almost finishing, we'll be publishing very soon. Now I go to another example, that is the hexagonal LuFeO3. This was done in collaboration with Professor P.S. Anil Kumar from IISc, and it was in 2018. This is kind of the hexagonal structure, and here you see the lutetium is sitting here, iron is sitting here, iron is FeO5 environment. Now this material is showing this kind of polarization at room temperature at room temperature. So this is showing ferroelectric properties. Now, in terms of magnetic, and also in the literature, the same sample when they studied in terms of thin film, there also you see this polarization loop is there. That was published in literature. Now we have done, so that means so far I said this LuFeO3, it is a ferroid material where there is a spontaneous electric polarization. Now by doing neutron diffraction at 160 K 6 Kelvin at BRC, what we show here that here there are no magnetic peaks, but at low temperature magnetic peaks are appearing. So there is a magnetic ordering, magnetic Bragg peak, okay? And we are showing the detailed analysis. As a function of temperature, you see how the magnetic Bragg peaks are appearing, how the magnetic intensity is appearing, and from there how the magnetic intensity is a function of varies. So there is the parametric state, the magnetically ordered state. So that means here what I plot here basically the magnetic moment which is derived from the ordered magnetic moment derived from the neutron diffraction. And so this is the parametric state, ordered magnetic moment is 0. When there is a magnetic phase transition at the nil temperature Tn, this magnetic ordering takes place, then magnetic moment grows and it goes and saturates like a balloon function. What we expect, the temperature dependent building up of magnetization. But what is more interesting, so that means so far what I said, this material is showing ferroelectricity, this material is showing magnetic ordering. So two things are already established. The third thing I am going to establish that not only magnetic ordering, not only ferroelectricity, but there is a structural change as well at the magnetic ordering temperature. So that this is the crystallographic A, this is the crystallographic C, and this is the unit cell volume. See one-to-one correspondence. When there is a magnetic ordering, so at that same temperature, it is, at the same temperature, at the same temperature, you see there is a crystallographic variation of A lattice parameter, C, and a unit cell volume. So that means, and of course, if you look at the magnetic structure, this is a bit complex. I will not go into that, which we have solved, which is called non-collinear 180-degree antiferrometric spin structure with magnetic ordering temperature 130 Kelvin. This is the temperature where magnetic ordering takes place. So this is a system where there is a structural phase transition or structural distortion rather. Structure remains hexagonal, but structural distortion, crystallographic structural distortion coupled with magnetic phase transition. So magnetostructural coupling is very much there. At the same time, this is a ferroic material. So all three ingredients are there in this compound. And if I show a little bit more, which I just showed you, on the other side you see even the specific heat data, you see there is a kink here at that temperature. You see the dielectric constant, here also you see the peak, and you see the magnetic susceptibility derivative also peak. So magnetic susceptibility, dielectric constant, and heat capacity all have this interlinked property, coupled property, where you have the structural kind of change as well as magnetic ordering takes place. So a coupling between lattice, electric and magnetic degrees of freedom so plays an important role in achieving the multiphasic ordering in this compound. So this is what is the conclusion. Now, if you see that, now this is I have already talked about. So basically, a little bit more understanding we have got. The slide rotation of this FeO4. I told you the iron is sitting in FeO4 environment. So rotation of the FeO4 trigonal bipyramid about the 102 axis breaks the inversion symmetry, and that is responsible for the ferroelectricity along the C direction. So this kind of information comes by doing detailed, powerful microscopic neutron diffraction experiment. That why do you get ferroelectricity? Where is the inversion symmetry breaking? Because of this distortion of this trigonal FeO5 trigonal bipyramid about this axis. So all this information, if you want to extract, you need to use powerful neutron diffraction technique. Now another one, excuse me, just so another example now I give, that is TBMNO3. Yeah, in the literature, this it is showing what you see here at 15 Kelvin, the electric polarization. So that means it is a ferroic material. Of course, this is a thin film form of the sample, no problem. We have also studied this in the bulk, and this is a neutron diffraction experiment you see at room temperature for different compositions of TB. And so DC magnetization shows that there is a magnetic phase transition. You see that here also in a large scale you can see there is a magnetic phase transition. And you know the Raman scattering, this was in collaboration with Anushree Roy from IIT Kharagpur. And this Raman scattering is very good technique to study the spin-flown coupling. And in fact, we have done that. And we have plotted the Raman shift and the line width. And you see at this temperature, please see that. At this temperature, where there is a magnetic phase transition, you see this sharp evidence of spin-flown coupling. So, as I said in my introductory slide, the spin-flown coupling is very, very important because the magnetostructural coupling, see, when you do diffraction, neutron diffraction experiment kind of, you see magnetic ordering, you see structural either phase transition or structural ABC variation or volume variation of the unit cell volume variation. So that means there is a magnetostructural coupling. That is what the static property. But if you do Raman scattering like this, so there you measure again directly spin-phonon coupling, as you know. So this kind of technique, neutron diffraction in one hand, Raman scattering other, and then of course you have this bulk DC magnetization for specific heat, this kind of. So if you put together, you get to know the spin-phonon coupling, magnetostructural coupling, magnetostructural correlation, how they are responsible for this multiferric property, magnetic ordering, ferric property, and so on. Now I give one example from molecule-based magnetic material. See, molecule-based magnetic material we have been working on for several years, and this is different from the conventional inorganic materials. And this inorganic materials, as you know, so far I showed perovskites or ferrites, but here you see the building block. For example, the Thane group, and this is another is the oxalate group. So these are nothing but all this. See, red one is oxygen, the blue one is carbon, green one is nitrogen. So this is the building block. So building block, and what you have here, the magnetic elements, iron here, for example, Fe1 and Fe2. Crystallographically, two unequivalent sides, one for iron 1, another for iron 2, and they are separated quite large. As you know, if you talk about the magnetic X-ray interaction, 5.51 angstrom is a very large separation to have any kind of Heisenberg X-ray interaction, direct X-ray interaction, and so on. So here you see the magnetic atoms, magnetic ions, magnetic moments, they are breathed by this organic ligand. Here it is oxalate. This is all this carbon, hydrogen, nitrogen based, or then again if forming like a chain where this phenolphthalein group is also coming. But the magnetically, when you see the magnetic atoms sitting at two different crystallographic sides, one called delta, another called lambda. So there are two crystallographically inequivalent sides. And why this is very, very important. This polar property, eventually I'll be showing you that they are showing electric spontaneous polarization, of course magnetic ordering. And here this, this different chirality, this crystallographic symmetry is very, very important for magnetic elements. Okay, we have been working on, and as you see, these are all examples from our work in this kind of magnetic materials over the years. And here it's not updated over the last 2 years, but I'll be showing some data from the recent study. Okay, Now, for example, if I take this particular example, the iron and chromium based, system, and we have done Newton diffraction experiment, we have got the crystal structure and so on, monoclinic crystal structure. And then, as I was saying, I showed you so far this unit, this is the building block. And if you put together one after the other, it becomes a chain. So actually the crystal structure is like this kind of chain-like structure. This is the building block. Okay, like we have the unit cell for inorganic case. You can say this molecule-based magnetic material, this is my building block. And if you repeat that, then it becomes this full chain. And these chains in three-dimensional sense give you the entire compound. Okay. Now, for one of the composition, let us say x equal to 0, means chromium is not there. So you see, as a function of temperature down to 15K, I am showing the data here, how the dark peaks are evolving. And if you take the difference pattern, 2K temperature minus 15K temperature data, that means 15K in the non-magnetic state, 15K or 16K, 17K, it is the non-magnetic. That means it is like X-ray diffraction. That means only dark peaks due to the atomic periodicity. Okay. So the difference pattern is the purely magnetic intensity. So it tells you this whether it is 0 or 0.1 or sample, you get the difference pattern. That means it is purely magnetic. So purely magnetic data, and we have done the analysis and got the, for example, magnetic structure here. So from this difference pattern, this is kind of magnetic structure. Here iron 1 and iron 2, they are you see antiparallel, but not exactly. There is a slight canted. That's why iron 1 has got all three components along A, along B, along C. And then iron 2, the another crystallographic site, iron 2 has also got all three components and A and B and C. But you see that this is plus, this is minus. So that means almost they are antiparallel. This is C component, this is minus, this is plus. Okay. But B component is both are plus. B component is ferromagnetically coupled. So this kind of magnetic structure, canted antiferromagnetic structure with a nil temperature 11K, that is what is established here, And for this, you need to do only Newton diffraction. I hope I am very much audible, right? I am very much audible, I hope. Yeah, thank you so much. Thank you so much. Then, see, when you talk about this kind of molecule-based magnetic material, you also need to understand the quantum chemistry. And what you see here, this is my magnetic atom, one side, this is another magnetic atom, and how this organic ligand, how they're coupling and how they exchange interaction, whether it is ferromagnetic or antiferromagnetic, how they are propagating through these organic ligands. Okay, so I'll not go details of that. So symmetry and what kind of orbital symmetry in between you have, that will dictate the magnetic ordering. Here, as you see, both are almost antiparallel but not fully. And this is the magnetic structure as I just explained. And if you plot the order magnetic moment for iron and chromium as a function of chromium substitution, you get, as I said, both A, B, C component of the order moment and different variations. So let me summarize so far on this system what I wanted to tell you. I wanted to tell you that this is organic material. There are magnetic atoms like iron or cobalt. They are there and they are breathed by organic ligands, carbon, nitrogen and oxygen made of that. But these are magnetically ordered at low temperatures. So magnetic ordering is there from Newton diffraction. I just showed you magnetic structure, very complex structure. And DC magnetization also shows the magnetic ordering. So magnetic ordering is there. This is the hysteresis loop at 1.7 K. And I must tell you, the hysteresis loop, you look at this Tesla unit and how much is the corrosivity, nearly 3.6 Tesla corrosivity, very, very hard magnet, very, very hard magnet, even very difficult to achieve this kind of corrosive field from the inorganic magnets. So this is one point I like to say. So far I have established that there is magnetic ordering of this molecule-based magnetic material at lower temperature. Okay. Now So this is again chromium. This is cobalt based, again showing magnetic ordering. So again it is showing hysteresis. I will not go into details of that. Large hysteresis. Now let me come to the polarization side. So magnetic ordering is established. Now what I need to show you, what I will be showing you, how this same compound is causing electric polarization, spontaneous electric polarization. So for that, my neutron diffraction data are very, very useful, because neutron diffraction data and quantitative analysis tells us all these atoms, whether it is magnetic or non-magnetic, where they are located, what is their position. I can calculate bond angle, bond distance, and so on, as you see. And by doing all these things, basically this is one tensile metal, which is, let us say, iron 1, sitting in this octahedra formed by oxygen, nitrogen, and another M2, another magnetic atom, which could be iron or chromium. It is again octahedra, but these two octahedra, as you see, they are distorted octahedra. And how we have plotted it, what I get from the neutron diffraction data analysis. So basically we are plotting two octahedra where the magnetic atom is sitting at the center. But these are not the regular octahedra, this is a tilted, distorted octahedra. And these two octahedra, how they are coupled by this carbon. Here, the carbon atoms are in between. So this is what is the beauty of this central point of this ferroelectric polarization. And if I quantitatively calculate distortion, how much is it distorted, this octahedra? So I'll be calculating this way, the octahedral distortion. So the distorted octahedra of these two magnetic atoms, M1 and M2, that is F1 or F2, or chromium 1 and chromium 2, or mixed of iron and chromium in one side, and mixed of iron and chromium other side, or even manganese 1 and manganese 2. So this distorted octahedra is the central part. So that comes from by doing powerful neutron diffraction experiment, we get to know the microscopic crystal structure, the crystallographic distortion, and so on. And using those extracted values, how much it is distorted, and that is what octahedral distortion with this scale I am plotting with the chromium substitution. So this is at two different crystallographic sites, lambda and delta, which I just talked about. And using this experimentally determined octahedral distortion, theoretically I am calculating how much electric dipole moment is expected out of this octahedral distortion. So please listen to my language very carefully. By doing neutron diffraction, I find out the octahedral distortion, that is what is here in figure A. Using this octahedral distortion, I calculate theoretically how much electric dipole moment should be sitting in this site, M1 and M2 site, and of course how is the variation with the chromium, that is what is plotted. So fact is that the octahedral distortion is leading to the dipole moment, spontaneous electric dipole moment at these two crystallographic sites, and those two sites, as I already told you, those two magnetic sites are also giving you the magnetic ordering, because I told you this is already magnetically ordered state. So that means the M1 and M2, the tensile metals, where they are sitting, they are in one hand, they are magnetically ordered, there is a magnetic dipole moment. At the same time, they are also, the electric polarization is also sitting there because of this structural distortion, octahedral distortion. So, and this information comes from crystallographic data analysis, okay? And that is magnetic structure comes from magnetic data analysis by neutron diffraction. And this is what is very powerful. Now, as I just said, and now this is the theoretical. Now experimentally, I measured the polarization in this microcurie, and this is what is the results, okay? Of course, one may talk about how much the leakage current density and so on. That also we have shown here. But for 0.5 sample, leakage current is high. But for the parents one, x equal to 0, it is small. But you see the loop. So that means This is an example that in one hand it shows magnetic ordering, and that is canted antiferromagnetic ordering. The two magnetic sides are, one is that lambda side, another is the delta side. Two crystallographic inequivalent sides where the metal atoms are sitting. And there also you get this spontaneous electric polarization due to the crystallographic structural octahedral distortion, which is a theoretically calculated dipole moment from this experimentally derived distortion. And this is the experimentally direct measure electric polarization loop. So see how beautifully, and we have published very this year, rather last year only. So how beautifully we can explain the origin of electric polarization in this kind of magnetic material, where the magnetic elements, tension metals, are coupled, bridged through the organic ligands. So that's why they are called molecular magnetic materials, oxalate or friend group. And how this structural distortion at the crystallographic side, I repeat particularly for the students, how the structural distortion at the octahedral side, how that leads to the theoretical dipole, electric dipole moment at both the sides, and that gives you the experimentally measured electric polarization. Similarly, for other system, also, see that top portion is not going. Right? It's always sorry, no. I'm clicking, but this is okay. So yeah. So then it is another example that in the similar compounds that are oxalate friends. So there also you see the title of the paper itself tells you from my group only, room temperature ferroelectricity in one dimensional single chain molecular magnet. So we see the ferroelectricity, okay, and so this kind of, and also we explain similar way how this between two iron or between two manganese, manganese based and iron based, how the ferroelectricity is. So I will not elaborate that, okay. Now another probably just a few minutes, I'll give few examples without elaborating that we have observed ferroelectricity, but I will only talk about the magnetostructural coupling is there, and that will tell you that these are potential material for looking for ferroelectric properties. In fact, in literature that has been done. So this is one piece of work. I was very happy to collaborate with Professor Sena Rao and his group. So this, here is a Newton diffraction, as you see, diffraction patterns. But you see a room temperature diffraction pattern, 5 Kelvin, low temperature diffraction pattern. And if you see the plots, as you see, as you decrease the temperature, how the magnetic back peaks are appearing. So magnetic ordering is taking place, You can see that magnetic back peak is not there, by intensity is building a lower temperature. So this is when you go from, along this direction, actually temperature is decreasing, okay. Here I have shown two plots at two temperature. Here you see the back peak, it is almost very less, and by here intensity is growing. And this kind of magnetic structure it has. Yeah. Now, what about some problem? Yeah, this is one extra thing is coming. 1 minute, 1 sec. Okay, somehow is forward. Okay, so this kind of magnetic structure, there are iron sides, iron 1, iron 2, iron 3, iron 4, 4 sides, and I will only trying to tell you that there is a DC magnetized, you see the magnetic ordering, depending upon, which composition you are looking at, there is a magnetic ordering, and at the same time there is a structural, you see the unit cell volume, there is a 1:1. So around 210 is the ordering, and you see around that temperature, depending on the composition, here is a 250 for this one. So the unit cell volume changes. So there is it only tells the magnetic ordering and structural changes. They're interlinked. So magnetostructural coupling is there. So one can look at the spin-thrown coupling and one can look at the multifluidicity and the dielectric constant properties. I will not elaborate into that. This is another example. This is the geometrical frustrated antiferromagnet we have worked on. There are two kinds of arrangements, triangular layer and kagome layer, where these cobalts are forming triangular lattice or the kagome lattice. And this one, the golden one is the kagome and blue one is the triangular layer by layer structure. And there also we have done neutron diffraction. And this is the magnetic ordering taking place on 110 Kelvin. You see the magnetic bragg peak, how they are developing as you decrease the temperature. And you see the corresponding structural changes. You see there is a one-to-one correspondence. So this example again tells that magnetic ordering and structural distortion, structural bond angle, bond distance changes, they are again linked. So magnetostructural coupling is very much there. So one can, so in fact, recently we collaborated with Professor Anushree Roy in IIT Kharagpur, and we have done the Raman scattering, but I will not do, this result is just submitted to, in fact, in PRL. Referee reports already received and revised and sent again. And here, I will only touch upon this point that there is a spin-thrown coupling, very interesting spin-thrown coupling also we have observed here. So, whenever you see this kind of magnetic phase transition coupled with the structural, some kind of structural change, you should look for the spin-thrown coupling, you should look for the multiphasic properties, and so on. So, possibly very last example, as I said, I should be completing by 1 o'clock, though I started late. The magnetic-electric coupling from this is again a ferrite system, lithium-based, okay? And we have been working on, we have already published a paper on the magnetic structure point of view. I think that is in Journal of Applied Physics in 2019. And this is the second paper we are working on. In this system, the interest is that, again, magnetization as a function of temperature, you see the magnetic ordering takes place, magnetization builds and goes to 0, and then again becomes positive side. So this is the called magnetic compensation temperature. I have discussed that magnetization becomes 0. That is called magnetic compensation. But what I want to bring to your attention, that the magnetic compensation and magnetic ordering, if you look at this temperature, see this temperature, see here, these curves, for example, this one for 1.1, when you decrease the temperature, how this transitions and how this is called impedance spectroscopy study, Z prime and Z double prime, how they are interlinked with these two tensions, which is more evident here. You see the peak frequency, we get two peaks in the Z double prime. This is the impedance spectroscopy study. Okay, F1 and F2 we get, and F1, and this is for F1, this is for F2, and F2 it shows a change at this T compensation, where we see the compensation, okay, at this temperature, 423, okay, and where the magnetic phase transition, magnetic ordering takes place at this temperature, 583, there you see this F1, shows that change as well as at the T compensation. So, what I mean to say, in this case, what you see the magnetic phase transition, either it is paramagnetic to ferromagnetic or the magnetic compensation, there if you do this impedance spectroscopy study, you see one-to-one there is a interlinked. So magnetoelectric coupling is very much established. So magnetic and electric coupling is very much established from this example. That is what I'm trying to bring to your attention. Of course, we have done very detailed study. In this case, by doing this kind of analysis, Cole plot, many of you know, and when you plot this, here we show that there are two kinds of conduction. One is the ionic conduction, Ti, and another the electronic conduction, okay? So two kinds of, from this impedance spectroscopy study, we see there are two kinds of conduction process, the ionic conduction and electronic conduction, and we are able to separate out. See, if one does, for students, again I am telling, if you do only DC resistivity study, if you don't do the impedance spectroscopy study, if you don't measure Z and Z prime, you will not be able to separate out these two contributions separately. What is the ionic part, what is the electron part? Because this kind of circuit analysis is not possible from DC conductivity study because frequency is 0. But with this frequency dependent study, it tells you that with temperature, how much is the electronic conduction, how much is the ionic conduction. Not only that, we get more powerful information here. What I am plotting here, the dielectric constant, this is the real part, this is the imaginary part. And as a function, with temperature, I will only make one conclusion here, because to start with, I said that I would like to give this interlinked. From dielectric constant measurement, how will you get information whether ferroelectric polarization would be there or not? This is one case. This is one case where this dielectric susceptibility is not showing any peak-like structure, any peak. So if dielectric susceptibility does not show any peak-like thing, so it only means there is no spontaneous polarization. Okay. Now, if the spontaneous polarization is there, then it may show ferroelectric ordering at lower temperature, may or may not. But you need to have this polar. You need to have the spontaneous polarization at the local site. So this tells that there is no peak. That means there is no spontaneous polarization. But if even the peak is there, that may be dynamic in nature. So it may not lead to ordering, like a magnetic case. For example, you have dipole moment, magnetic dipole, but it is a paramagnetic, it can remain down to 0 Kelvin temperature paramagnetic, may not go to magnetic order state. Similar thing can happen. But since peak is not there, so you can rule out that there is no, this material will not show any, if you do the electric polarization measurement, P loop measurement, you will not get any hysteresis loop. That is what I am trying to tell you. So in other words, here we have this so-called, from this impedance spectroscopy, we get to know only the conduction due to electronic and ionic, but there is no polarizability. So this another system, but I can stop here. This is Na2Mn3O7 kind of layer system also we have been working, and here the sodium, and this kind of materials are important for battery application because sodium has got ionic conductivity, layer structure. And we have done the detailed impedance spectroscopy, and from this analysis, what we again see that this is the DC conductivity, and here I'm plotting the AC conductivity sigma prime, and what you see as a function of temperature. Again, I show that this is the frequency. This is the frequency, and this is the temperature activated conduction processes, and there is again. This material again will not show any ferroelectric loop, okay, because there is no peak. So this is what I just, because here you see it is a linear behavior, I do not say get any peak-like structure. So here is a correlated hopping only we are getting. So with this, let me summarize my talk. So in this today's talk, basically the forum, as you know, ferroelectricity and dielectric properties. So what I said initially, when there is a spin phonon coupling, the spin phonon is the, as you know, the lattice vibration, underlying lattice vibration, and some of the atoms can have this spin because, for example, iron, cobalt, nickel, examples which I told, sodium, they are having a non-zero spin due to Hund's rule, and then spin and phonon coupling, whenever it is there, that can lead to multiferroid property, which I showed in couple of examples. The spin phonon coupling, this is another name could be the magnetostructural coupling. Structural means lattice and magnetic moment. So magnetostructural coupling, and in dynamic sense it is spin phonon coupling. From Raman I showed you, from Newton diffraction I showed you magnetostructural coupling, and from polarization, electric polarization measurement I showed you the opening of the hysteresis loop. And then on the other side, by doing the impedance spectroscopy study, the complex impedance, we have the real part and the imaginary part of the impedance, and the dielectric constant where epsilon is related to the impedance impedance of Z star by this. This is my dielectric constant. So if you do the impedance spectroscopy study, you get to know about the dielectric constant. And dielectric constant can also has two parts, the real part and imaginary part. And I showed you that by doing the dielectric constant, many cases, I see that dielectric constant has some linkage wherever there is magnetic phase transition or magnetic phase transition or structural distortion. In some cases, I showed that this dielectric constant does not show any peak-like effect. That means that ruled out that this can lead to this ferroelectric polarization opening. So this is the connectivity I wanted to establish because this is very, very important. I hope I could do that. And so with this, let me thank all of you for your kind attention. And of course, special thanks to Professor Smita Acharya for her kind invitation. And I really love to speak. And 2 years back also, I delivered similar talk at, of course, that time I could physically come over to Nagpur, beautiful place, and the historical university. As you know, even our many ministers are from that university. For example, Honorable Mr. Gadkari also from that same university. Thank you so much.
Thank you, sir. Sir, some questions from the participants. Can I ask you, sir?
Yeah.
Sir,
yes, please.
Yeah, Soib Abbas asks, how local valency of a compound affect the ordering and disordering, and what are super exchange interactions?
The second one is super exchange. What is the first part?
How local valency of a compound affect the ordering and disordering.
Okay. How the local valency affect the ordering or disordering?
Yeah.
Yeah. See this, for example, you are, let us say, talking about iron, let us say, Fe2 plus or Fe3 plus. Now, if, say, from bonding point of view, if you see that, chemical sense, if one side is supposed to have Fe3 plus, but if there is a, for example, okay, I'll put it this way. One example I showed you with regard to ferrites. I showed you that tetrahedral side is only one, but octahedral side has two parts, distinct. One is B1 and another B2. So this is a good example that there is a, what is called charge separation, basically a charge ordering, which you know in case of CMR perovskite. So B1 and B2 has occurred because of this valence difference, oxidation state difference. Okay, this is one part. So that means B1 and B2, this kind of order structure with splitting of the octahedral side took place because of this different valence state. Okay, number one. Number two, your super exchange. Yeah, super exchange interaction is one when the magnetic dipole moments, they do not interact by direct overlap. What is there for a Heisenberg exchange interaction? For example, if you take 3D elements, the 3D lobes, they directly overlap, and then you get the magnetic exchange, okay? The cooperative phenomena, magnetic ordering. But let us say you have magnetic ions, two magnetic ions sitting, and in between you have oxygen, okay? Oxygen. So then they can also magnetically interact. That is called the super exchange interaction via these oxygen orbitals, oxygen p or oxygen sigma orbitals, and depending upon which orbital is there, the super exchange interaction sign and strength can be different. Okay.
Okay, I think satisfied. Then second question asked by Vaidai Deshmukh. She said, "Sir, what precaution or things a researcher should carefully take up while taking measurement of dielectric property of material?"
Yeah, see, dielectric property precautions means, see, first of all, you have to see the making connections, that is always one is tricky part. So that part you have to take into account. And particularly we have done some experiments at higher temperatures. So temperature stability you have to see. And when we apply the voltage, whether your setup is able to give the uniform electric field over the entire sample, depending upon what is the sample size. So these are the precautions you need to take. Okay. But according to my measurements are very simple. It is VI and I, voltage and current measurement by at a given temperature or changing frequencies. Okay. So measurements are that relatively straightforward, but data analysis is more, I'll say more elaborate. But of course, it can give lots of information, as you could see, by doing the data analysis of the impedance spectroscopy, and whether you want to see the dielectric constant or or Z prime, Kolkol plot and whatnot. Okay.
So, thank you, sir. Thank you for such a comprehensive explanation and lecture. And I say, as a host, I say that thanks to Dr. S.M. Yusuf, sir. He promptly responds to my email and he easily accepts my invitation. So thanks very much, sir. Now, RMP Chaudhary, sir, are you want something to say?
I have to say, RMP Chaudhary, Professor Yusuf, I am meeting you for after a long time, and I'm really very happy for excellent your lecture for all the participants and for the newcomers.
Thank you. This is my pleasure, because
I say thank you very much, because we have interacted for many times. We have interacted since last I think 30 years or so, but recently we have not met. I left IIT 10 years ago. I am in Bhubaneswar, so still I like to continue our relation. So thank you, Professor.
Yes.
And we will continue.
Thank you. So,
thank you.
And hope we'll be able to meet soon.
Yes, sir. Yes, Professor. Yes.
Thank you so much.
Thank you. Thank you for giving a nice lecture, an excellent lecture, outstanding lecture for all of us. Thank you.
Thank you.
Dr. Khati, please conclude the lecture.
Yeah. Honorable Yusuf sir, thank you very much for giving so nice lecture on structural correlations in multiferroics. You have explained with whatever the work you have done, whatever the work you have published, and the innovative different layers of the different materials and their dielectric properties with other electrical properties over there. So it is very informative, outstanding, nice, and this is giving to new insight to the researchers, to those who are working in this particular field. So I would like to request on the part of my university, Nagpur University, you will be having a very good relations, and you will definitely help our university for various type of the research projects. And once again, very much thankful to you for so nice presentation and lecture. Thank you very much, sir.
Yeah, definitely. I'll be happy to. I have been serving in different committees, so I'll be happy to, whether it is BRNS, CSIR or DST, wherever possible, I'll be happy to help, because that is what our duty by serving in any committee, to help the country, where the country overall there is a scientific prosperity, and particularly smaller places, they should get funding so that science spreads all over. And I'll be happy to serve my duty in that regard. Thank you.
Thank you very much, sir. You always help us. Yeah. So now there is one contributory talk. Sir, Dr. Khati, you can start.
Yeah. And the next is the contributory talk from Dr. Hitesh Borkar, Department of Physics, NIT Warangal, and his topic is effect of eliminations and cations, reordering on dielectric, ferroelectric, and energy storage properties of lead-free electroceramics. He is presently working as assistant professor in Department of Physics, NIT Warangal, Telangana. Received PhD degree from NPL New Delhi with specialization in condensed matter physics, ferroelectric photovoltaics. He has been postdoctoral fellow at Department of Physics, Indian Institute of Technology, Bombay. His research work includes synthesis and characterization of ceramics and oxides at bulk and nanoscale, ferroelectric materials for non-volatile memorial applications, impedance and dielectric spectroscopy, photovoltaic devices, photovoltaic materials, high energy density capacitors, lead-free piezoelectric materials, electrocaloric effect and energy storage phenomena in polar materials. He has about 22 research publications in peer-reviewed international journals, one book chapter, and one international and national patent. I would like to invite Borkar sir for your contributory talk.
And sir, I want to say one thing about Borkar. He is alumni from our department, sir.
Oh, so nice. So nice to see you for contributed that.
Yeah. Am I audible, madam?
Yes.
And my screen is visible?
Yeah. Your screen is also visible. No problem. Proceed, Bob.
Firstly, I would like to thank the NSFD organization and especially Professor Smita Madam to giving opportunity to present our over here in the NSFD 2021. And along with, I would like to thank my supervisor, Dr. Ashok Kumar from CSR NPL, New Delhi, India. So he provided me immense knowledge during my PhD program. So due to him, I can be here. I am here right now, and so I am telling my contributory talk basically based on the effect of illumination and cation reordering on the dielectric ferroelectric energy storage properties of lead ferroelectric. Okay, so to reduce bandwidth, I have to stop my video. Okay. Before starting this one, so basically I will be today focusing on the basic phenomenon of photoferroelectrics. Okay, so the outline of my talk will be like that. Startingly, I will just introduce what is the basic phenomenon of photoferroelectrics. Then I will be started give the motivation of this present work and objective. And after that, I will be go a little bit amount in material processing and characterization. Then I will end up with the significance and the summary of future scope of this one of the present work which I am going to show it to you. Okay, so now basically what is the photoferroelectrics? Okay, so till now we have been discussed or we have been listened the different kind of ferroelectric ceramics material, just like ferroelectric, antiferroelectric, paraelectric, and different kind of ceramics also, and the different kind of combination composites like ferroelectric polymer and different composition like ferroelectric with magnetic material also, magnetoelectric phenomenon also we have been discussed. So right now I will be taking you in the advanced part, basically commonly known as the photoferroelectrics. Since these photoferroelectrics have been discussed and have been give the word previously before 15 years, but right now within in 2012 they have been discussed the things like that. Okay, they have been demonstrated that above band gap photovoltaics. Okay, and there is a possibility to enhance the photovoltaic effect at the nanoscale level or at the fundamentals level with relating to the domain wall. Okay, so which increase the efficiency with respect to your bulk level also and with respect to your nanoscale level also. Okay, so with this point of view, all these properties enhances the ferroelectric material, which potentially have been very bright future in the field of solar cell energy conversion. Okay, so keeping these things into mind, okay, so keeping in these things to mind, so we have been concentrating on the material which shows the strong polarizability, the material which is having the narrow band gap, and there should be coupling between the phototronic effect and the ferroelectricity. Phototronic means photon with electron related effect, and basically the photoferroelectric and ferroelectricity. So before discussing one more phenomenon, I have to discuss one of the major point over here. That one is basically the electrical poling. Okay, so if we are going to the unpoled state, okay, this is the one of the unpoled state and this is the one of the poling state. If we go to the unpoled state, okay, so there are you may not get the proper ferroelectric due to the domain pinning and different types of charge trapped in between your grain and grain boundary, and you may observe that you may feel that during your measurement of ferroelectricity there are so many oxygen vacancies, free oxygen vacancies present on your surface or within your grain or grain boundaries. Okay, so with this, taking all these points into consideration, we need to pole the system in such a way that all these effects has been neutralized. So there should be no domain pinning also, trap charges also, the whatever the oxygen vacancies are present in between your grain boundaries, that should be neutralized. Okay. So on coming to the photoferroelectric, so basically, if we are going to see in this one particular diagram, okay, so to study the photoferroelectric phenomenon, generally we are having the structure like metal, insulator, metal. Okay, just now I have said it like that. Ferroelectricity. What is the ferroelectric material? Ferroelectric material are basically insulator material. But to study the photoferroelectric phenomenon, we should have the material which is having capability or which is having band gap near to whatever the photon generated, whatever you are generating the photons, that much should have your photon kind of energy. Okay, so with this point of view, you should have the narrow the band gap. Okay, with this point of view, if you are having this one is the year for ferroelectric material, on that you have to put one transparent electrode. Let's suppose the indium tin oxide, which is one of the best transparent absorbing material. Okay, so on the base you may have the different kind of electrodes, just like silver, platinum, and all these things. If you are going to take into nanoscale level, then under the illumination process, there are two conditions you may find out. Okay, so built-in bias also and depolarization during the positive cycle of whenever you are applying the positive bias, cycle of polarization measuring, and when you are going to measure in the negative cycle, so it may have the depolarization effect which include your biasing voltage. Okay, so if you see this is one of the basic ray diagram. When your light is incident, when the light is having energy with respect to band gap of whatever the material you are going to use the photoferroelectric phenomenon, it should have the energy with respect to that one. And when the light incident on its Fermi level energy, and when it's incident on Fermi level energy, it will break that charge particle, and that breaking charges will take part into the conduction basically mechanism. But there is a one point of consideration also you may take it into very seriously. That one is the basically microscopic correlation. You will never know at microscopic level what will be happen. Okay, for that to study that microscopy, you have to perform the PFM or different kind of photon kind of experiment you have to perform to study the microscopic correlation. Okay, so I will not go into that particularly microscopic correlation. I will take it to show how the ionic and electronic conduction take part to enhance or take part into the basically being commonly known as the photoferroelectric phenomena. Okay, so motivation of present work is the material. It may exist the multiphases also. It may not exist the multiphases also. It will not. But our whatever the material which I am going to show you right now. Okay, whatever the material we have been studied, it exists with the multiphases, that is one of the tetragonal and one of the orthorhombic. Okay, this is the beauty of the material which we have been fabricated. Okay, and another very beauty of this ferroelectric material, if it is linear dielectric material, if it is ferroelectric material, if it is relaxer material, if it is your antiferroelectric material. Okay, so they are having their different kind of beauties in the different kind of applications. So today I will discuss the things about the relaxer ferroelectric material, which is having two possibilities. They are having capability to store the amount of energy, although antiferroelectricity material, they are having more capability. But since we are in this particularly talk, we have been concentrating on the relaxer material, and the relaxer material, including the photo-induced charges, we are commonly called this material can be behave as the multifunctional material. Okay, so basically what happened in the photo-induced charges? Okay, since if we are considering this one is we are having one particular dipole. Okay, upon incidence of the irradiation or whatever the illumination light you are going to use, the light must have the once again I am repeating, the light must have the energy with respect to that material. Whatever you are going to use the photoferroelectric phenomena. Okay, so if it is having hole and electron, they are making one dipole. The light, what it will do, whatever the light you are irradiating, it will break the hole and electron into the separation. That will basically we are commonly known as the photo generated charge carrier, and that will be pass into consideration to generate the photovoltaic in the ferroelectric material. And what is the photoferroelectricity? Now again, the photoferroelectricity basically when this is if you are going to see the normal black one, black graph with respect to electric field and polarization, this is measuring of ferroelectricity. Incident, the light with respect to your band gap with respect to energy, what are the light you are using, it should be matches with the band gap of that your material which you are going to use. So on the basis of that, you will get enhancement in the ferroelectricity of that material. You can clearly see over there. If your incident the white light, whatever the room temperature, room ambient temperature, whatever the light you are going to use, under that condition, the ferroelectric also enhances. When it is exactly matched with your band gap of material, the incident light, it will enhance the much more. If you are saying this is around 6 and this is around 18, so it will, you may conclude that it is enhances around 180% than under the dark condition. So this is the basic phenomenon or basic study of photoferroelectricity, and this is the one of the photo-induced charge. How the photo-induced charge carrier generated. Okay, so this is the basic phenomenon of motivation, basic behind this one particular. Okay, so the objective of this present work is to study the photo control ferroelectric properties on the basis of that. So basically, the one of the multifunctional material is one of the PZT. So we are not going to into the late portion due to toxicity. So we are mainly concentrating on the environmental friendly material, which is BaTiO3. So on the BaTiO3, we have doped on the A side lithium and bismuth cation. Okay, since we are using lithium and bismuth as cations, because lithium and bismuth both are optically active material and they are having very much tremendous application in the non-linear optical properties. Okay, so therefore we have to study the ferroelectric and dielectric study to tune the polarization under the illumination of light, and we have to study what is the effect on when we are going to measure the temperature dependent, all the different kind of properties. So in the with this point of view, we have been synthesis lithium bismuth dope BaTiO3 on the A side, okay, by the solid state reaction route. And the beauty of this one material is having the two phases. One is the tetragonal, one is the orthoropine, which is in the percentage of 60 to 40. 60% is included into tetragonal and 40% is included in the orthorhombic crystal structure. This is at the only at your simple surface level, or we can say on the bulk level. If we go to see in the nano level to see the microstructure, you can clearly see over here that there are two phases coexisting each other. Okay, if you are calculated very carefully, this is the SAD pattern, transmission electron microscopy micrograph. If you are clearly see this different kind of phases coexisting, there if you are going to measure very carefully, so you will came to conclude that they are having the tetragonal and orthorhombic crystal structure with respect to you. This is at the microstructure level. Okay, and if you are going to see at the secondary electron micrograph, this is confirmed that this material is having very compact in nature due to, and you will capable to calculate the different kind of grain size energy and the different type of area. If you are going to see again, if the figure D, you will clearly visible the different kind of chemical inhomogeneities are there. Okay, different chemical inhomogeneities are there that will be you are related to your relaxer portion. Okay, since the relaxer material is having different kind of polar nanoregions. Okay, previously lecture we have been seeing the different kind of polar nanoregions we have been seeing and we have been discussed so far. This is at the microstructure level. Okay, means it confirms the different type of crystal structure. First one is the tetragonal and orthorhombic, and here the chemical inhomogeneity which reflect your the formation of different kind of polar nanoregions. Okay, so with this point of view, we have been calculated the dielectric measurement with respect to this is dielectric measurement under the three different conditions: first, second, and third. In the first condition, we have been measured the dielectric measurement. First, we have been cooled our ceramic up to the 77 Kelvin. Okay. After that, we have been started measurement around, let's suppose, minus 100 degrees Celsius. We have been carried out the measurement. This is the measurement we have been carried out from the room temperature. This is the dielectric temperature dependent dielectric measurement we have been carried at the under the illumination of the laser light of having wavelength 405 nanometer wavelength with the having energy density 25 milliwatt per centimeter square. Okay, so if you are having, I have been already show you that. Okay, since we are concentrating on the relaxer portion, this is having the frequency dispersion. And okay, to see the frequency dispersion, we are having clearly see the frequency dispersion. Okay, this pattern which clearly indicates that this pattern of increasing the frequency and decreasing frequency phenomenon is clearly convey that this material, okay, lithium bismuth dope barium titanate oxide, which is having the relaxer type of nature. Again, if you are going to check the measurement from the room temperature, if you are going to see, and under the illumination of light, the frequency dispersion and the phase transition temperature is dispersed. You can clearly see with these three different conditions. And although the loss tangent is very, very less, so that this material is basically, you will call it as a ceramic. Okay, so on the basis of this first, second, and third graph, you may conclude that this material which behave and under the illumination of light, it will act as a dispersive kind of a phenomenon you will capable to see, or you will capable to see under the illumination of light. And since this material shows the relaxer type of nature, so we have to fit it with our experimental data with the Vogel-Furcher relation. It again, all the parameters shows it is having it satisfy all the Vogel-Furcher relation within our experimental list. Okay. Now, if we are going to see the impedance characteristic of this at these two conditions, first one is at the room temperature, dielectric temperature dependent dielectric measurement, and another one is the temperature dependent dielectric measurement under the illumination of light. You can clearly see that under the dark, the impedance parameter of this one, and under the illumination of this one parameter, you can clearly see the order of the impedance parameters, or the impedance, we may say that resistivity is reduces under the under the illumination of 405 wavelength. Okay, and
Hitesh, 5
yes,
minutes last time.
Yeah. Okay, yes, madam. I will going into conclude. Okay, so under the you can clearly see the photo-induces phenomenon to study the ionic, to check the why we are doing the impedance measurement, to check the ionic and electronic correlation or electronic conduction. So on the basis of under the illumination of light, you may clearly see that the electronic part take much more conduction, much more than the your whatever the impedance you are measuring in the dark measure. Okay, so these are the fitted parameter. I will not go into the into detail. Okay, so again I will take it into this picture very carefully. So under the illumination, you can clearly see the resistance, bulk resistance under the illumination and without the illumination. You can clearly see under the 360 degrees Celsius, you will see the bulk resistance you will having the 78 mega ohm, whereas and the same temperature you will have the 10 mega ohm under the illumination of light. It means that there is a conductive electronic part, take it into more condition under the when you are going to compare with the dark. Okay, so similarly we have been performed the AC conductivity into the dark also, and AC conductivity into the under illumination of the light. It is again confirmed that it is having, if you going to see the sigma conductivity, it is reduces under the illumination of light. And if you are going to see the activation energy. Now, what is activation energy? The minimum quantity of energy which is required to get it into the react to whatever the processing you are going to do. Okay, so under the illumination, there are activation energy very, very low, and under the illumination of light, activation energy again reduces by 0.5 electron volts. So it is confirmed that from this experimental data, you will conclude that under the illumination of light, the ionic and electronic part take it into the more more prominently rather than the ionic portion. And if you are going to see again the temperature dependent dielectric under the dark and under the illumination of light, it is again confirmed that it shows the photoferroelectric phenomena which I have been discussed earlier. Okay, it is the prominent result which shows the photoferroelectric phenomenon. And since this is the relaxer material, the ferroelectric is having very slim kind of, so we can capable to use this kind of area capable to store the different kind of amount of energy. So at the 60 we can say at the 60 field, okay, 60 kilovolts, we can capable to store the amount of energy 0.8 joule per centimeter square, and the charging discharging efficiency is also very high, around the 95% if we are going to see. And to confirm the charge neutrality, or to confirm the we can say the valency of that material, so you can capable to see over here bismuth is coexistent in the two phases, bismuth 3 and bismuth 5. So due to this, you may capable to see the electronic conduction is more, and this is into the portion of 60 into 40. So, and since I have already mentioned, if you want to see or if you want to study the photoferroelectric phenomena, your material should have the narrow band gap. So this material is having on the basis of Kuebeler-Monk function, we are capable to calculate, or we are greatly achieve the band gap around 2.76, which is well enough to absorb the different kind of visible light. Okay, so significance of this work to produce the internal field distribution, how the internal field distribution is responsible for the electronic distribution, and this demonstration will add the additional degree of freedom so that you can capable to see the ferroelectric phenomenon under the illumination of light. So with this point of view, you can tune your ferroelectric, dielectric and optical properties by cation reordering also, and by narrowing your band gap also. So the basic application of this one particular, basically lithium bismuth dope, is electrocaloric effect also you can check under the with respect to changing ferroelectricity under the different kind of temperature. Okay, ferroelectric photovoltaic also you can check, and this may be alternative to organic inorganic solar cell also. And the photoferroelectric phenomenon can be very useful to design the novel photovoltaic memory application. And there are so much random or so much tremendous applications in the field of optronics field. So with this point of view, I am concluding this my talk basically on the photoferroelectric phenomena. So I would like to thank you all, and thank you for the kind attention. And if anyone have the doubt, they can ask.
Here, as a light source, are you use laser or ordinary?
Yes, madam. We are basically we have to use the monochromatic source of light, and if it is good if you are using the laser source, because it is having coherency. So it is very useful to get it the band gap within the limit of your material, whatever you are going to use.
Okay. So you are taking that in room temperature, at room temperature or high temperature also it is possible by light source, because that experimental arrangement I can't imagine. You want
yes, madam.
There, and then you are taking giving ferroelectric characterization. So what type of experiment?
So all this experiment setup has been with the Dr. Ashok Kumar sir in the NPL. So we have been set up one device, so you can simultaneously illuminate the light also, and simultaneously with the temperature dielectric and ferroelectric properties also.
But it is room temperature or high temperature?
It is at a room temperature also, room temperature as well as the high temperature. This is the high temperature ferroelectric measurement we have been carried out. We have been make a instrument one schematic, or we have been fabricated one kind of device in a such a way that you can capable to induce light also, and you can capable to measure the dielectric at the various temperatures also simultaneously.
Okay, but due to the temperature effect, the beam is not get distorted or intensity not get.
Madam, for that we have been taken care of all the precautions. We have been focused our light by using different kind of lenses. 2 lenses we have been used to focus. So in that way, the light should be focused on the sample itself, where the sample we have been placed on the ITO surface so that light can get it absorbed. So on the basis of that, we have been fabricate or all the setup. If you need in detail, we can show you later on how we have been doing.
I should have to visit Ashok Kumar lab because I am a little bit excited. His yesterday lecture as well as your lecture also. So
yes, madam.
Okay, chalo, good, Hitesh, nice presentation.
Okay. Thank you, madam.
Thank you, Hitesh.
Okay, thank you, Hitesh, sir.
Oral presentation, sir. Oral presentation.
Yeah. Thank you, Hitesh, for your so nice presentation on lead-free electroceramics and very descriptive things you have explained. Now the next is the oral presentation that is from Mr. Vikash Kajraj, NIT Kurukshetra. The title is Preparation of Spinal Structured MnCO2O4 Microspheres for Energy Storage Devices. Vikash.
अभी और चल रहा है तो क्या करें खत्म हो गई अरे उसका जवाब
there is your voice is not clear. Just check your audio because Vikas.
मॅडम त्यांना अनम्यूट करायला सांगा मॅडम म्यूट आहे ते
Okay, you unmute. Vikas, you unmute yourself. Can we unmute him?
Hello.
Yes. Now we now
yeah,
we
okay.
unmute. Okay. You start.
Hello everyone. I am Vikas Kajraj. I am research scholar in Department of Physics, NIT Kurukshetra. So the title of my presentation is a preparation of spinal structure manganese cobalt oxide microsphere for energy storage device. So that the flow of my presentation will be as I will start with the introduction, then experimental work, and then result and discussion, and in the final concluding remarks. So the introduction. So supercapacitor is a device which stores energy by the separation of charges. So the supercapacitor can be broadly divided into three major categories like EDLC type, pseudocapacitive type, pseudocapacitive type, and hybrid type. In EDLC type, there are no Faraday reactions. Only the energy stored because of the charge separation, like mostly observed with the carbon-based materials. In pseudocapacitive type, there are energy stored because of the Faraday reaction. The Faraday reaction may be intercalation or electroabsorption of the ions. So it is observed mostly by the metal oxide and conducting polymers. So the third one is hybrid type. Hybrid type is the combination of these two types of material. So one is symmetric supercapacitor. In symmetric supercapacitor, these two electrodes are same type. But if they are EDLC type, then they have mostly the same material. But in asymmetric supercapacitor, one is EDLC type. Both are EDLC type, but the material is different. And the third one, which is hybrid type, in the combination of these two types. So I prepared manganese cobalt oxide microsphere by the fissile solver thermal method. I prepared the precursor carbonate precursor and then calcined it at 500 degrees centigrade for 2 hours. This is converted this to spinel manganese cobalt oxide. So it shows the Axardi pattern of the manganese cobalt oxide calcined at 510 degrees centigrade. It shows the diffraction pattern is well matched with the JCTS standard pattern, and it shows the cubic structure which has space group of FD3M. It has mean crystallite size around 20 nanometer, and it shows the lattice parameter of this. So it shows the same morphology of the manganese cobalt oxide, which is calcined at 510 degrees centigrade. It shows the low magnification, and this image shows the high magnification. These microspheres are mostly in the range of 1 to 2 micrometer. So So it is the EDX mapping of these microspheres, and it shows the homogeneous distribution of manganese, cobalt, and oxygen atoms. So further, we use this material for the electrochemical studies. I have used cyclic voltammetry in the potential range of 0 to 1 volt. In electrolyte, I have used 1 molar H2SO4. So it shows the CV with the scan rate. So as the increasing in scan rate, the current is increasing, and the shape of the CV is almost same. So it shows the stability of the material at various scan rate. So it shows the variation of specific capacitance with the scan rate. So as the increasing scan rate, the specific capacitance is decreasing. Now it shows the galvanostatic charging discharging of MCO electrode, manganese cobalt oxide electrode, and this is in the potential range of 0 to 1 volt, and it shows at various current densities. Now this shows the variation of a specific capacitance at various current density, and at higher current density, like almost 10 times, the specific capacitance is able to retain its 72% almost. So we have prepared a asymmetric supercapacitor device utilizing this MCO electrode and EDLC type activated carbon. So activated carbon we have utilized in negative window, and MCO we have used in positive window. So this shows the CV of these two electrodes in the respective voltage range. So this shows the CV of this hybrid device at various scan rate. Now the specific capacitance we have calculated is around 130 at scan rate of 10. So as the scan rate, variation of scan rate is increasing scan rate, the specific capacitance is decreasing. Now it shows the galvanostatic charging discharging of asymmetric supercapacitor device, activated carbon and MCO electrode at various current densities. So the specific capacitance it observed is around 90 farad per gram at current density of 3. Now this shows the cyclic ability retention of our device at 1000 for the 1000 cycle, and it is able to retain 80% of initial specific capacitance after 1000 cycles, and it is able to hold its 100% Coulombic efficiency. Now this insert shows the first 10 cycle, and it shows the last 10 cycles. Now the charge transfer resistance we have calculated by the EIS. So it shows with the cycling, it shows slightly increase the charge transfer resistance. So now it shows the energy density, Aragon plot, energy density and power density of the device, and it shows around 32 watt per kilogram power density of 2.4. Yeah, okay. So this is the conclusion. So this manganese cobalt oxide sphere has been prepared by thermal method and calcination done at 500 degrees centigrade, and it shows the cubic phase, and it shows microsphere in the 1 to 2 micrometer, and the specific capacitance calculated 273, and it shows the energy density of 32 watt hour per kilogram, power density of 2.4 kilowatt per kilogram. Thank you.
This talk is open for questions, and I think no queries is received. So second participant, Muzaffar Iqbal Khan.
Yes, ma'am.
You are converted into presenter. Just start your video. And share your presentation.
Hello. Hello.
Yes, sir.
Presenter start, sir. You are busy, so I just let him start.
Okay. Good afternoon, sir. Hello, sir. आवाज आ रही है? Hello.
Yes, yes, it's clear. It's clear. It's clear. You start.
Myself is hello.
Your voice is audible. You start.
Okay, ma'am. Myself is Zafar Iqbal Khan, Research Scholar, Department of Physics, University Nandan Bogran Garhwal University, Uttarakhand. Today I am going to talk about my presentation, Dielectric Properties of Hydrogen Bonded System Dihydrogen Phosphate Type Ferroelectric Crystals. Outline of my presentation is introduction, model Hamiltonian, gain function method, calculation and result, discussion and conclusion, application part, acknowledgement and references finally. In introduction section, in figure first right hand side, dielectrics are basically classified into two types, centrosymmetric and non-centrosymmetric, which are piezoelectric, and piezoelectric are further divided into two categories, non-piezoelectric and pyroelectric. And pyroelectric are further divided into non-ferroelectric and ferroelectric materials. And right hand side Venn diagram shows that the ferroelectric is a subclass of pyroelectric, and further pyroelectric is a subclass of piezoelectric, and finally we can say that the ferroelectric is a subclass of a dielectric material. Basically, ferroelectrics are those materials which show flexible, spontaneous electric polarization, and their particular properties are high dielectric constant and faster to cover. According to their phase transition mechanism, ferroelectrics are divided into two types: order disorder type and displacer type. In order disorder, I am discussing the cesium dihydrogen phosphate crystal. Cesium dihydrogen phosphate is a KDP type ferroelectric crystal, and its phase transition temperature is 154 Kelvin, and its best characteristic is that it is a monoclinic crystal structure in both ferroelectric state and paraelectric state. And in figure third, I represent the crystal structure of CADP at room temperature. In theory, model Hamiltonian gain function method. In this paper, basically this paper is a theoretical, and we use it to sublattice pseudospin lattice coupled mode model Hamiltonian by modifying the third and fourth phonon and harmonic interactions, extra spin lattice interaction, and direct spin interaction, and applied electric field used for the study of the dielectric properties of a CDP crystal, and in which is shown represented in equation first. This is our whole model which we use to study the dielectric properties of for CDP crystal. And in equation first, the term in equation first, omega is the tunneling term, tunneling term, and J and K are the both respectively the proton coupling constant with different sublattices and the proton coupling of the same lattices. And this A and B are the A is the normal position coordinate, and B is the B3 and B4 are the third and fourth phonon and harmonic interaction terms represent in equation first. And this equation represents the describe the well-known interaction of the pseudospins with polar phonon, which makes the two potential well for proton motion non-equivalent. This term is this term represents, and this term is used for when a crystal above TC is non-symmetric, and we use this term to make crystal symmetric. And this BIZ is a direct spin coupling term, and is a electric field term which we use, and use the dipole momentum. And with the help of model Hamiltonian, we use this method which is called gain function method, which was proposed by Zobare and shown in equation second. Equation second, where in equation second theta is a step-known function which is well known, and this first angular bracket represent the grand conical assemble, and square bracket represent the commutator and anti-commutator, and this notation is represent double angular notation is represent for the gain function notation. And hello.
Last 2 minutes.
Differentiating this equation twice, we get equation fourth, and further by taking the Fourier transform of equation fourth, we get using it into a Dyson form equation, we get equation equation 5, and in equation 6 and P omega is a response function which is represented in equation 6 and 7. By using the symmetric decoupling scheme method, which is equation 8, we solve this equation 7 because this part contains the higher order gain function, and after solving the gain function symmetric decoupling equation finding gain function which is represented in equation 9, this equation, and in this equation is the integral, and this is Conan frequency, and this is the pseudo spin frequency, and this P omega is the response function which is further obtained in equation 10 and equation 11. And with the help of mean field approximation, we obtain this pseudo spin frequency, which is equation number 12, and where A and B is described in equation 13, 14, and 15. And with the help of a symmetric decoupling scheme, we obtain the response function which is represented in equation 16, which contains the higher order gain function as shown in equation 16. And to solve higher order gain function from equation 16, which contains in Z, X, and Conan gain function, with the help of symmetric decoupling scheme, we firstly evaluate the Conan gain function and gain function with respect to X, and which are represented in equation 18 and equation 20. And finally, substituting the value of gain function, Conan gain function, and function with X and Z in equation 16, which is the response gain function, and which is finally obtained in this equation, which is represented in equation 21. We call this equation as response function or polarization operator. And further, we resolve this equation with the help of Dirac delta equation, which is represented in equation 22, and which is divided into two parts. One part is the real part, and another is the imaginary part. This real part is called the shift, and this imaginary part we call this width of the width for the CDP crystal, and which is after calculating we obtain in equation 23. This is the shift part of the CDP crystal, and this is the width part of which is represented in equation 4. And further in equation 24, we evaluate this delta with the help of this Dirac delta property, which is represented in equation 25. And with the help of response function, which are substituting in equation, which is substituting in previous equation, which is representing in equation 9. This equation here. After solving the P omega response function in equation 9, we obtain the soft mode frequency, which is represented and finally obtain the gain function in equation 26. And in this equation, this term double tilde omega square is represent the modified pseudo spin frequency, and which is further described in equation 25, which is also a part of pseudo spin frequency plus 2 omega del omega. This is the shift part of the calculation, and further we obtained the substituting shift part of the value, which obtained equation 26, which obtained equation 28, which is the final form of a modified pseudo spin frequency, and the final gain function 26 previous equation, which can also be written in equation 29. And in this part, this omega hat is the soft mode frequency, which is obtained in equation 30, and this is here. This is the shift part of the calculation, and this is the Conan part. After substituting all these values, we obtain the soft mode frequency, which is represented in equation 31st, and which is responsible for the phase transition mechanism for ferroelectric crystal CDP. And dielectric constant last tangent property for CDP crystal, according to the Jobara was proposed, the susceptibility is related to the gain function, which is represented in equation 32, and further we know dielectric constant, dielectric relative permittivity is related is by the equation 33, and by using equation 33 and 32, we obtained and gain function method in previous equation. We obtained the dielectric constant, which is represented in equation 34. and separating dielectric constant into real and imaginary part. And we obtain the expression for loss tangent, which is represented in equation 35. And numerical quotation as well. We use the various model parameters, which is represented in table first, and set the value of n and mu and electric field E equal to 0 in equation 34 and 35, and match with the experimental data of Levesque et al., which is represented in equation first to 3. And this is here by setting the various model pattern, we obtain the total shift and total width of the CDP crystal. And this is the software token, dielectric constant and loss tangent property for the CDP crystal. Here we share that initially as we increase the temperature, the value of the software frequency decreases, and further after crossing the TC, and it is increasing, and the dielectric behavior as the initial increases and it is not maximum.
We have only last 1 minute.
In conclusion, discussion in respect to using a two-sub lattice model by adding extra interaction test, we found the software frequency dielectric constant loss tangent property. By setting the model parameters, we obtain the dielectric loss tangent property as shown in figure 6, 7, 8, and well compared with the static experimental data of Levesque et al. This model theory may also be applied for the similar order disorder type KTP, RBS-PO4, and PSF-ASO483, and its application CTP is highly thermal stable, so it can be used for glass optical ceramic applications. They are typically in thermal solution in water in use for advanced electronic or lightweight structure etc. Acknowledgement also are grateful to Professor P.D. Smith for discussion and the Department of Physics at Cambridge University for supporting and facility in the work with polymer research which we are used. Thank you all for listening to my presentation. Hello.
Thank you. Thank you. Madam, next guest.
Any questions for this? Okay. Sir, our next oratory is Rishi Roshan Bharadwaj from Department of Physics, Central University of South Bihar, and his title is Unconditional Magnetization of Fe3O3 thin films grown on Si111 substrate studied by soft X-ray magnetic circular dicrosium. So, Rishi, you are present now?
Yeah.
Start your presentation.
Yeah, I'm audible, ma'am.
Yeah, there is small change. Kati sir, there is small change because timely they interchange there due to their exam issue. So in place of earlier whatever we have given, this student have exchanged.
Okay. Hello everyone. I am Rishi Bharadwaj, MSc student of Central University of South Bihar, Gaya. I am presenting today's topic on a topic of X-ray circular dicrosium. 1 minute. Something. Hello.
Yes, Rishi, you are correct. Proceed.
Okay. Something else.
Relax. No problem.
Okay, 1 minute. This. What this is? Okay, 1 minute.
No problem.
Yeah. These are my content. Okay. Some. These are my content. So firstly, I discuss about the structure of Fe3O4. Fe3O4 have cubic inverse spiral structure with mixed valency state of Fe3 plus and Fe2 plus. In such a way, 8 Fe2 plus and 16 Fe3 plus occupy in position of tetrahedral and octahedral site of the oxygen atom. Here 32 oxygen of -2 state and 24 Fe ions are present here. Here also, we all know in inverse spinal structure 8 Fe2 plus ions and 8 Fe3 plus ions equally pair at B side, and they mutually antiferromagnetic coupled. So the net magnetization here due to the A site which is where Fe3 plus are present on the tetrahedral position. So next slide I will shown about some significant feature of Fe3O4, which significant feature of Fe3O4. So it has high Curie temperature as compared to any ferromagnetic material. So and it has also property there half metallic. Half metallic means a spin aligned in one direction. It behaves like insulator, and a spin aligned in one direction. It behaves like conductor or semiconductor. I mean, their band gap is low, and when electron aligns in one direction, their band gap is high. So for this reason, they use in spintronics, and also the reason why they use their large spin polarization because of only one kind of electron with identical spin orientation at the Fermi level. And due to this reason, their high spin polarization and their high electron conductivity as compared to any other transition oxide material room temperature. And they diverge the technical application in the area of magnetic recording, such as like CD, DVD, and batteries. We all use lithium-doped lithium-ion batteries in mobile phones, cell phones, and biometric. So in this case, Fe3O4 is used as an anode, chargeable anode, and their biomedicine and their energy technology. It's much more useful. So it's high their magnetic and electric properties. So I used Fe3O4. So our aim is to understand the electronic and magnetic property of chemical solution on Fe3O4 in film on Si substrate. So why I do it? Previously, people used MBE or PLD, but here we use chemical solution deposition, which is very easily available. We all know in India there are few centers where MBE are available. But this chemical solution grown technique, deposition technique is very cheaply. Even it does not require any vacuum. It works in non-vacuum. So these are my experimental method and principles. So firstly, I use X-rays. X-rays is X-ray spectroscopy. Here the proper absorption of excitation of the core level electron into unoccupied D state as a function of energy. So this is the IH mu. This is the photo absorption intensity. This is the transition dipole operator, which is ±1 here. Next is XMCD. So whatever XMCD. XMCD is the difference between the absorption intensity of left and right circularly polarized light. And this is some enhanced property that makes different branches. So the first one is element specific. Element specific means we can know particular element in even at 10 nanometer thin films. We know about which type of impurity present there. And second one is sensitive is local structure. We also know about the local structure even at 10 nanometer, even at 5 nanometer. Here the XS it works in two modes. First one is here the XS it works in two modes. First one is total electron L mode, total fluorescence mode. Here it is the sensitivity is 5 nanometer and their sensitivity is 100 nanometer. So this is the right circularly and this is left. This is the XS graph and this is XM3 for general. So next is some rule by which we can obtain by orbital magnetic moment and spin magnetic moment. These are the usual symbols, and these are my samples measurement conditions. So SI substrate in 110 direction, Fe3O4 grow of 53650 nanometer. And here Y uses photon energy of 625 to 805 electron volt, and the temperature is 300 Kelvin, and pressure is -10 to the -10 torr. So these were all done at BL6A in Japan. So this is the last part of this my talk. That's the result in this part. So here the excess peaks of left circular polarized and right circular polarized. Here the two peaks of L3. L3 is the 2p 3/2, and L2 which is the 2p half. And my samples excess graph matches with this Fe3O4, which is also my colleague Priya Kumari at in same university, same classmate, my classmate. and it does not match this graph and this graph only matches with this, and this matches is clearly shows that Fe3O4 grown on Si substrate in 100 direction. And what I just get, the observed experimental data of XAM do not suggest that Fe2 plus ions or Fe3 plus ion metal, while similar, it's simply that theoretically matches with us. And next slide, this is the XMCD graph. This XMCD graph, whatever I get, that's the Fe3 plus and Fe2 plus, which I already discussed in octahedral position, and this peak also shows up with experimentally, with theoretically, literally, and this tetrahedral position, and this in octahedral position, which matches with this. I also compare with this. These material gamma Fe2O3, Bi Fe3O3, and Ga Fe3O3. Okay. So the last point is that here the antiferromagnetic coupling of Fe3 plus and Fe2 plus, which also matches with our theoretically. And here what I do, firstly, here I deduce the magnetic field 3 to 0 Kelvin. But what we saw, there is some magnetization present in the sample. This suggests that the magnetic spin remains high down of light 0.3, indicate that the ferromagnetic exists still in the Fe3O4 thin films. And this is the temperature dependence I do, temperature dependence magnetization. In the temperature dependent magnetization, you saw that after 300 Kelvin, it's 152, and this after this you saw that there is changes there. There are changes of their magnetic spin or moment. This is due to the transition of metal to insulator at 120 Kelvin. So based on that data, we believe that the magnetic transition temperature of the Fe3O4 part is not generally effect. So finally, we conclude that the magnetic spin is 1.9 Bohr magnetron Fe and orbital moment 0.09 Bohr magnetron in TUY mode of XMCD at Cape, Japan. And our Fe3O4 thin film observed that the weak magnetic dependence of the magnetization, and for Fe3O4 thin film of the ferromagnetic exists in Fe3O4 thin film because of there existing remnant magnetization at low temperature. So in future work, I do the defect induced in Fe3O4 thin film are required to control their magnetization. Any type of defected, and we control magnetization by some dose impurity like nitrogen, and so on. These are my national. So I'm thankful Dr. Biraj Singh, which guided me and provided all necessary faculty. I also thanks to my CUSB friend Mohammad Mufid sir, and these are my national collaborator, and these are my international collaborator. For financial support, UGC BSR and SERB DST, and for program also BST India for the financial support of PNCSR CSR Bangalore for managing director. Thank you.
Hello. From where you are taken XME-DCD?
Yeah, Japan. From Japan.
Japan. Okay. In which
Japan?
form? Okay.
Yeah.
In which form you have used your sample? Is it thin film or a powder?
Thin film. I only thin film. Okay. Yeah.
Okay. Good.
Any question?
Okay, good.
Any query? Hello. Any query?
Anybody from participants? Any queries? Okay. So, Dr. Khatti, you just conclude the session.
Yeah, ma'am. Thank you. Today we are having a great session on material design and processing, where we have started with the talk of Dr. Pawan Kumar, who has very well explained the things related with the ferroelectrics over there. Then we are having Honorable Yusuf sir from Park, Mumbai, who has very nicely explained all the ferroelectric and dielectric properties of the material, and how the layers that are formed over there, and how they are synthesizing the new material over there. I am very much thankful to him for sharing his knowledge with us. Then we are having a participatory talk from Dr. Hitesh Bokar, and then oral presentation from Vikas Muzaffar, and then from Rishi. So I am very much thankful to all of you, and I am also very much thankful to my colleague in the university, Dr. Smita Acharya, for giving me opportunity to chair this particular session. And thankful to all the organizers of this national conference. Once again, thank you to all of you. Madam, over to you now.
Thank you, sir. You have nicely organized this session. It is one of the very heavy session actually, but you have cooperated. So thank you very much. And now there is a lunch break. But before we go to the lunch break, today our one of the founder member of NSFD, Dr. RNP Chowdhury's birthday is there. So I want to just share a small slide for him. Dr. RNP Chowdhury, are you there? Dr. RNP Chowdhury?
Yes.
Sir, for you, my your grand student, my student have make a small slide. Just take.
What time? What time then?
So, sir, 1 minute. I will show you that slide. Okay, yeah. Arpit, have you make me presenter?
But you can go for lunch. After that, you can do it.
No, sir. Just a small slide. Actually, I want to show before the start of this session, our first session of today, but this is get skipped somewhere. So I am sharing 1 minute, sir. I have to go take
सोनू
1 minute, sir.
वीडियो दे दो, ये वीडियो ऑन कर अभी. हैप्पी बर्थडे बोलेगा ऑन कर. ठीक है. देखो
आप बोलते हैं our beloved RNP community, sir.
It's not clear, madam.
Yeah. Sir, actually, sir, is it why not?
यहाँ भी म्यूट.
Hello, sir, can you hear me now?
Yes.
Sir, have many happy returns of the day, sir. Sir, that voice is not clear.
Yes, clear. Now it's clear.
Sir, actually this I want to show at the start of the day, but just somewhere I skipped. So this students have prepared for you. So again, once again, very happy for your future life.
Thank you very much. Thank you, madam.
Okay, sir, we will join again at 2:30 sharp. because already we are going.
Great.
And sir, we again organize small functions for your birthday felicitation up to 6 o'clock after poster session, sir.
Poster session. Okay. Okay. Thank you. Thank you, madam. Okay. I think we can go for lunch.
Okay, sir. Okay. So we stop here and we will start the next session just at 2:30 p.m. Okay. Thank you.
Yes,
Thank you very
yes,
much,
yes.
Khati sir.
Okay.
Thank you, Arampi Chaudhary sir.
Okay. Thank you, madam.
తాము అనుభవించే బాధ విలువ అమ్మవారి బాధ కంటే ఎక్కువ, అలాగే సమాజంలోని బాధల కంటే ఎక్కువ. కరుణ పూర్తిగా ఇంకిపోయింది ఈ సమాజంలో. ఎప్పుడైతే
Okay, sir, good afternoon. Sir, good afternoon. Kiran sir, good afternoon. और सर कैसा है इंदौर में? हाउ आर एवरीथिंग देयर? सर अभी तो थोड़ी ठंडी बढ़ गई है फिर से. हाँ जी, ठंडी बोलो, ठंड फिर से बढ़ गई है. गुड आफ्टरनून स्मिता मैम.
Yeah, welcome you, sir. Welcome you in NSFT platform, sir.
Ma'am, I am attending all the presentations.
Yeah, sir. Actually, I can't hear you. 1 minute, sir. Hello, sir. Welcome you, sir, in NSFT platform.
Thank you, ma'am. Ma'am, I am attending this whole event. I missed a little bit of first lecture, but I am attending the whole event. It's very nice, and you organize very nice speakers.
Okay, sir. Thank you. Thank you very much, sir. Sir, actually, for this session, the chairperson is Sanjay Dhobre, but he is somewhere in the traffic jam. So I just start the session. He will join us somewhere in between.
No problem, ma'am. You can chair the session. There is no formality. You can start the session. It's absolutely fine.
Yeah. So our
Pankaj sir is there. I think Pankaj sir is the speaker for this session. I think first speaker.
Yeah, Pankaj sir is the first speaker, and you are the second one. So are the Pankaj joined here? I just speak.
Yeah, ma'am. Yeah, Pankaj already joined.
Yes, madam. I am here.
Okay, sir. Welcome, sir.
Thank you, madam. Thank you.
Yeah. So for this sessions, there are 2 invited talks and 3 oral presentation. And the chairperson for this session is Dr. Sanjay Dhobre, but he is somewhere in the traffic jam, so I can start the session. He will join in between. So the topic of Dr. Pankaj Sachdev is origin of ferroelectric polarization in cubic phase of HF dope BaTiO3. I will just read his brief CV. I introduced you with Pankaj Sachdev. Sir is currently working as associate professor and head in the discipline of physics. He received his PhD in 2007 from UGC DAE CSR Indore. After completing PhD, Sir joined Bhabha Atomic Research Center in 2008 as a scientific officer D, applied spectroscopy, where he set up the state-of-art coating facilities for optical and neutron layer application at BARC. In June 2012, Dr. Sachdev joined the Indian Institute of Technology Indore as an assistant professor, where he is involved in research, teaching, and established a material research laboratory which work on the physics of highly correlated electron system, quantum confinements in nanocrystalline system, and scientific instrumentation development. Sir has expertise in development of scientific instrument and to search for the novel experimental technique and or methodology for material characterization. He has published more than 90 research papers and also supervised PhD scholars. Dr. Sachdev is having a strong hold on various important sample characterization technique and working as a referee for various scientific journal of AIP, IOP, elsewhere, MRS, Village Major. Sir was a member of American Association for Advancement of Science in 2018. He had completed 2 research projects funded by CSIR and BRNS. So we welcome you, sir, and I just request you to start your presentation. I just changed. Yeah, you are already presenter. You are presenter there, so you can see the share of screen.
Yes.
Have you seen the share?
Yes, madam. Yes.
Yeah. Okay. Now you are sharing.
Yeah. So is it visible to all of you, these slides?
Yes. Yeah. The slide is not open, sir. Yes.
Okay. Thank you. Okay, so let me first thank Dr. Smita for giving me an opportunity to present my research work here. And to be very honest, Nagpur is definitely my parental home, and I will be happy to give the seminar topics, seminar talks, etc. in the Department of Physics at Nagpur University. And in fact, this particular topic of ferroelectricity is definitely is one of my strong interests, and I have happily accepted this particular invitation. Thank you, madam. Thanks very much for giving me an opportunity to present my work here. So before I start my presentation, I would like to say something about my institute. So I am working as associate professor in the Institute of Technology Indore, and I am happy to share with you the recent ranking published by Times Group, the World University Ranking. And in the World University Ranking, actually the IIT is ranked 55th place, and it is number 3 best institution in India. So I am very happy to share this particular news. In fact, whatever results I'm going to show here, these results are produced by these bright students. In fact, among these bright students, 2 students are from Nagpur University, from the same department, which is basically organizing this event. One, this Minal Gupta, and second is Nishchal Pardi. So these are from the Nagpur University. And the rest of the other students, actually the present work is basically is done by Dr. Achal Sati. And I will be presenting her results only in the present talk. Okay. So the plan of my talk will go as follows. I will just say something about the ferroelectricity in general. What are the observations beyond obvious, means beyond our normal understanding. I will also convey you how the disorder can lead to ferroelectricity. And I will share some of the recent results, followed by analysis and the open question. So when we talk about the ferroelectric material, we basically search for the electric dipole. Okay. In fact, what happens is that when these electric dipoles interact in such a way that each dipole remain parallel to each other, then we say that the sample is ferroelectric in nature. Okay. If the direction of these 2 dipoles is opposite, then we say that it's anti-ferroelectric in nature. Okay. So if you are looking for the electric dipole, then you must have a non-centrosymmetric unit cell. Okay. So if you are looking for the primitive unit cell, then it must be a non-centrosymmetric. That's what the obvious understanding conveys us. Okay. But if you look into the literature, okay, if you look into the literature, then you will realize that that this particular obvious understanding of the ferroelectricity doesn't hold true in all situations. Okay. And in some cases, you will have a centrosymmetric system, which is experimentally, which will show the ferroelectric PE loop, and that particular experiment is correct. Okay. It means that it's not the artifact. Okay, it's not the experimental artifact. That's what I wanted to convey you. Okay. And that is essentially due to the local symmetry breaking. And what are the examples of this local symmetry breaking? If you means those who are working in this particular field from long time, they are aware that, for example, take the example of strontium titanate, SrTiO3. SrTiO3 is a cubic structure, PM3 in space group with a cubic symmetry. But there are some results which confirms that if you have an inhomogeneous strain present into the sample, then that inhomogeneous strain. Sorry. Hello. I think someone is talking in between. Please mute yourself. Okay, thank you. So, if you look into the crystallographic symmetry of the strontium titanate, it's essentially the cubic one. But if you could introduce an inhomogeneous strain, okay, then that inhomogeneous strain may result into the ferroelectric polarization. Okay. And how to introduce inhomogeneous strain? One of the example is shown here. You can have a substrate which is a soft enough, it means that you can bend the substrate. And when you bend the substrate, then you can have a strain along this particular direction. Okay. So you basically introduce strain into the actual sample. And by producing the inhomogeneous strain, you can basically produce the local dipoles, okay, into the sample. Other than that, there are some centrosymmetric systems, means for example, the charged order manganites, okay, where you have the complete localization, I will say. Complete localization means the Mn plus 3 means, for example, you take the example of PRCA MnO3, where you have Mn is in a mixed valence state, and when the Mn plus 3 remains in plus 3 state, Mn plus 4 remains in a plus 4 state, and assume that this particular distribution is non-coherent for a time being. Okay. So in that case also, you can get something which is a ferroelectric polarization into the sample. Okay. So this is called so here the dipole is existing due to the near neighbor due to the presence of Mn+3 and Mn+4 ions, mixed valency of the transition metal ion into the sample. Okay. And due to local symmetry breaking into the distribution by somehow, okay, by some means, you can basically introduce the finite value of the electric dipole. And when you have such electric dipole, then these individual dipoles can interact coherently to give the ferroelectric polarization into the sample. Okay. The other example is the means the ferroelectricity in Fe3O4. Just before my lecture, there was one more talk on extensity of the same sample, Fe3O4. So in this case also, you can observe the ferroelectricity when you basically somehow break this the long range coherency by introducing some local disorder. Okay. So what is the message? The message is the following: the strain, or means either you have the inhomogeneous strain which is present into the sample, or you have charge ordering. It may give rise to ferroelectricity. But if you look into these particular things, you will realize that you see this particular paper in Physical Review B or this in PRL. So you will realize that these require the complete localization of the strain fields or these transition metal ions. Okay, it requires the complete localization, I will say. What does it mean? It means that the value of the strain at a given point P doesn't change with time. So the strain is localized. Okay. So now the thing is that you can basically produce such field by introducing disorder into the lattice. Okay, you bombard your sample with the argon ion, or you do some type of doping, okay, into the sample. So that will basically create disorder into the lattice. And all these examples which I have given, okay, earlier, these are somehow basically introducing the structural disorder, okay, local structural disorder into the sample. Okay, so what we thought that let us take a cubic system, for example, barium hafnate, BaHFO3, and then dope Ti in that. Okay. In fact, we have done vice versa also. Means we have to take BaTiO3 and dope HF into that. I will be showing those results here. Okay. So then, why BaHFO3? Because obviously it's a cubic system, it's a centrosymmetric system. I want to just dope Ti because in the case of Ti, the +4 oxidation state is most stable one. So there is a very less probability that the Ti will change its oxidation state, and the same with the HF. So I just wanted to create the structural disorder, and because why I am expecting structural disorder here, because you know that if you look into the ionic radius of the titanium +4 state with 6 oxygen nearby, okay, then you will find that there is a huge ionic radius mismatch, and this particular ionic radius mismatch will basically produce random strain field. Okay, so then what we have done is that we have prepared the sample, we have checked the sample using X-ray diffraction followed by the Ritzel refinement, and then we have basically performed the ferroelectric PE measurement for this sample. Even though you can see some loop here, but it's an incomplete one. So you can see that the line is more or less straight here. Okay. So it means that the pure BaHFO3 is showing as good as a paraelectric nature, okay, which is expected for the any cubic symmetry sample. Okay. As soon as I dope 5% of titanium, as soon as I substituted HF with the titanium, just by 5%, you can see the double hysteresis, which is the signature of essentially the antiferroelectric nature of the sample. Okay. In fact, these results are unpublished, and we are analyzing this data in a more sophisticated way. We are performing some more experiment on this. In fact, long back, when I was a PhD student at UGC Indore, one of my colleagues, Dr. Shahid Anwar, he was working on the BATI HFO3 type of material. Here, we have shown that when you substitute hafnium at the titanium site in BaTiO3, after very close to something like a 12%, the sample, these BaTi HFO3 shows tetragonal to cubic phase transition, and these samples remains cubic at least till up to the 40%. Okay, and that was basically the means Dr. Shahid has studied the sample only up to 40%. In fact, one of my students, Dr. Achal Sati, she have prepared the similar samples here, okay, at the Department of Physics in IIT Indore, and we have carried out the diffraction experiment on these samples, and we have confirmed that when you dope, when you basically put HF, substitute HF, then this is for the pure barium titanate, and this is for the 21% dope, 21% substitution. And you can see that this particular peak, 002, it's basically merging into the single one. So it means that it's a form tetragonal to cubic type of transition basically taking place. And we have confirmed this. And you can see that these are the refined parameters and the corresponding C/I ratio, which suggests that the sample is basically going from tetragonal to cubic type of structure. Okay. So when we have performed the ferroelectric measurement on these samples, you can see here that the BaTiO3 and rest of the other samples, okay. So these samples are essentially, means if you talk about the first two samples, these are essentially the tetragonal one. But if you look into this sample, which is the cubic one, okay, it is showing the ferroelectric loop. It's a very good ferroelectric loop. Similarly here, and even for the 30% dose, 30% HF substituted sample. Okay, it means that the sample is showing the ferroelectricity. In fact, to confirm that the ferroelectric polarization is real or not, there is something which is called Pund measurement, means positive up, negative down. It's one of the method to confirm the ferroelectricity is really intrinsic to the sample. It's not due to the extrinsic effect such as dielectric loss or something like that. And these measurements also confirm that whatever measurements we are doing, it's up to the mark, and this confirm the observed ferroelectricity in these samples. And now we really want to understand what is the origin of this particular ferroelectricity. Now, if you just see recapitulate whatever we have discussed in the very initial slides, that strain gradient induced polarization in SRTO3. So we just wanted to know that whether the strain is really responsible to for the or this random strain field, to be very precise, is really responsible for the observed ferroelectricity in this sample. So what we have done is that we have analyzed the data using Williamson-Hall type of analysis. For that, first we have basically extracted the value of the FWHM as a function of 2 theta, and then we have plotted the Williamson-Hall plot. Basically, Williamson-Hall is basically one of the methods to measure the value of strain which may be present in the sample along with the particle size, or to be very precise, structural coherency. So you can see here the Williamson-Hall data for one of the samples, and it's showing really very good linear fit. And from this linear fit, we have extracted the value of strain and the structural coherency, which is shown by grain size here. So you can see that the strain systematically increases with HF substitution into the sample, and the value of the structural coherency is systematically decreasing. Okay, so it means that the strain may basically play some role into the observed ferroelectric nature of these samples, or to be very precise, random strain field. So we thought that suppose means now if you look into the X-ray diffraction studies, from these X-ray diffraction studies, just by looking into these graphs, unless you analyze the data very carefully using Williamson Hall plot or something like that, it's really very difficult to analyze, very difficult to convey that the sample is having the local, I will say, symmetry breaking, because the X-ray diffraction is really probing the global symmetry of the sample. Okay, it's not probing the local symmetry of the sample. But if you are familiar with the Raman measurements, then you will realize that Raman measurements are really very much powerful to probe the local symmetry. Okay, and that is qualitatively, not quantitatively. Yeah? Please keep this in mind. If you are very good
Pankaj sir, your voice is not coming.
now is it clear? Hello?
Yes, sir. Now it's
okay.
Yes.
Okay.
What happened?
Pankaj sir,
There is some problem. Internet problem.
yes, sir. Sir, your audio is not coming.
No, I think he is trying to do something in the lab. There is some problem.
Pankaj sir? Pankaj sir, your voice is not coming.
There is some problem in the network in the our house.
Yeah.
They are
Some
trying
problem
to.
with network.
They are trying to.
Yeah, Dr. Dhoble is also joined here. Welcome,
Yeah,
Dr.
madam.
Dhoble.
Thank you, ma'am. Thank you. Sorry for late.
Yeah, it's okay, sir. It's okay. I have started the session and
Yeah,
Pankaj
very
sir
good.
has joined, but somewhere his network problem is there.
Yeah. Hello.
Hello, Dr. Pankaj.
Hi, madam.
Network problem is there in your place?
Sorry, madam.
Some network problem is there because we are unable to hear you.
No, I have very good connection, madam.
We can't hear your voice.
Your voice is not clear, sir.
Okay.
Yeah.
अभी याद आया, थैंक यू, अभी याद आता है.
Now it is okay.
Is it okay now?
Yeah, it is.
Okay.
ठीक है, thank you very much.
Okay. Sir,
Pankaj sir, you do one thing, you can switch off your video, then you will get a good data.
अभी इसका हैप्पी बर्थडे और हैप्पी मैरिज डे पे मानी नहीं लगता है, तो सही है, तो सही बात है. सबसे ऊपर है ना, इससे सबसे ऊपर
RNC चौधरी को
नहीं है भी, बात सही है.
Okay. So is it now? Am I audible to you now?
Yes, sir. Continue.
Okay. Yeah. Thank you. So, so the thing is that when we perform the Raman spectroscopy, only the phonons at k equal to 0 will contribute. Okay. So now if you just increase the structural disorder, okay, or decrease the structural coherency, then you will realize that those phonons which are not at k equal to 0, they may also participate into the Raman. Okay. So so that's what it's written in this particular paper. So you can basically get either the second order Raman scattering, or you can get the forbidden first order Raman scattering into your Raman spectra if you basically increase the structural disorder. Okay. So as I said, the phonons which are not at k equal to 0, they may contribute for the Raman spectra. Okay. And this is well known to the scientific community. So therefore, what we have done is that we have looked into the Raman modes for these samples, and you can see that even the sample is in the cubic phase. These samples, the x equal to 0.15, x equal to 0.21, x equal to 0.27, x equal to 0.30, all these samples are showing very good Raman activity. And you take the other example, means the other end, when we look into the BHFO3 substitute with TI, you can still see the very good Raman modes here. Okay. What does it mean? It means that if you can break the local symmetry, then you can basically probe this particular local symmetry breaking very easily just by looking into the Raman spectra. Which is very difficult in X-ray diffraction unless you analyze the data with this for the strain model. Okay, but that too will not basically give very clear-cut idea. So what are the conclusion? Conclusion is that when you have a static disorder in the sense the disorder is not moving with time, okay, or moving in space, okay, then that static disorder, structural disorder, may produce the electric dipole. And when you increase the density of such electric dipoles, local dipoles, these dipoles may interact ferroelectrically or antiferroelectrically, giving rise to some signature in your PE hysteresis loop. And the analysis of the diffraction data in the form of strain may be useful to understand. But what I want to convey is that the Raman spectroscopy appears to be very, very sensitive to probe the origin of polarization, which is essentially the local symmetry breaking into these samples. And as I said, examples can add much more to this to understand much more physics to these samples. Okay. So with these, I think I hope I am able to convey you a few results. Okay. I would like to thank you for your attention, and I will be happy to answer the questions, if any, by the audience and by the students. Hello. Hello.
Sir, there is one question from the participant. Hello.
Yes, madam.
He's asking what is the reason for breakage in PE loop.
Breakage in the PE loop. Actually,
yeah.
Okay. That's a very good question, I will say. Let's see. The thing is that when you look into the PE loop, let me just once again go to that particular slide. Okay, this one. Okay. So let's see. The thing is that in principle, this particular PE loop should be complete. If you look into this particular barium titanate also, there is a slight breakage into the PE loop. So if you see the breakage, it means that there is some type of loss activity is present into the into the sample, and in fact, what happens is that when you perform any experiment, not only the PE measurement, you will have to ensure that that when you basically put the sample, okay, before you put the sample, there should be complete, or before you start the measurements, the total charges on both the side of electrode must be properly neutralized. Okay, for that you will have to ensure that you have basically short circuit the sample before measurement, basically both the electrodes. You just short both the electrodes before measurement. Or the thing is that you will have to also ensure that the corresponding voltage between the neutral pole and the ground pole in the 3-pin socket, which you are using for the PE measurement, that is less than 1.5 volts. If you are sure that all these things are done before measurement, then you can. It is expected that this particular loop should be completely closed. But as I said, if there may be some intrinsic loss which may be present in the sample, that may also contribute to this non-closing of the PE loop. Okay. In fact, Dr. Kiran Kumar, who is the next speaker, he is expert on these measurements. He can shed more light on this.
Sir, another question. The question is from Samariknath Das. What is the difference between local symmetry and global symmetry?
Okay. So when I say, let me just go to the one of the slide. Yeah. So let us see. Take the example of this. I hope you can see the my cursor. Okay.
Sir, the slide is not appearing.
Slide is, thank you. Thanks. Slide is
okay. Let me. Oh God. Thank you. Just a second. I'm trying to go to that particular.
So you can explain already, no problem.
Let me let's see. When you talk about global symmetry, essentially the symmetry of I will say 5 micron by 5 micron by 5 micron of a unit of a crystal. Okay, so that's basically the global symmetry. Means if you look into the X-ray diffraction, the critically if you basically perform X-ray diffraction in your lab, you can see the footprint of the X-ray on the sample. So the footprint of the X-ray of this sample will be something like 1 mm by 5 mm. Okay, so whatever the diffraction you are getting, okay, so it's from that particular region. Okay, and in that particular region you will have so many unit cells, or so many, I will say, grains to be very precise, and each grain consists of maybe 1 micron to 5 micron. Okay, so when we talk about the global symmetry, I am talking about the symmetry of that particular grain, which is very large in the sense which consists of so many units. So that is called global symmetry. And when you talk about the local symmetry, it's the symmetry around one particular atom. Means, for example, you take the example of exaph. So when you perform exaph, you will perform exaph at a particular age. Means, for example, in the case of BaTiO3, you can sit on the titanium age and you can look into the near neighbor distance and near neighbor number of the oxygen ions when you sit on the titanium age. Similarly, you can sit on the barium age and perform the similar. So this is called local symmetry. Okay, and if there is any and to break this local symmetry somehow, the qualitative signature of that particular local symmetry also basically appears into the Raman spectrum. This is what I just wanted to say.
Sir, there is another question by Praveen Kantane. He asks, what is the reason behind observance of two peak in Raman spectroscopy in BaTiO3 in cubic phase?
No, it's not a peak, to be very frank. It's basically the hump. Means if you look into the, I'm not sure whether you will get this slide or not. Means what I will do is that I will share this slide with the Smita Acharya madam. And if you look into these particular this particular Raman spectra, I don't know what's the problem at my end, but I am unable to change the slides. Okay, I can change the slide on my computer, but it's not getting.
I think it's not
seen.
It's not
here
shared
actually. So let me just. I'm just trying to go to that particular. Okay, but if you just look into the intensity of that particular barium titanate Raman spectra, then the intensity is very, very poor. So it's essentially the hump. You believe me, it's a hump. Okay, so it's not a really a peak in the real sense, I will say. And there may be some still, when I say that it's a sample in the cubic phase, what happens is that if you look into the phase transition of the barium titanate, it's a first phase transition. So there may be few unit cells which are still in the tetraploid symmetry, which may present in the sample. So that may also give rise to some peak. But to be very precise, as far as the spectra which I have shown, it is essentially a very broad hump, because the intensity of the Raman spectra is very, very small. Okay.
Sir, only one small question for you. You are a very good expert in the field of the ferroelectric polarizations. So just to advise the young researcher, what is the advanced topic for in ferroelectric cubic phase compound? So new researcher is try to work in this field. So please advise some new researchers.
Okay. So thanks, sir. Thanks for your question. In fact, as far as this particular field of ferroelectricity is concerned, let's see. This means if we could somehow increase the dielectric constant of a material, then obviously you can miniaturize the size of the capacitor. Okay, which is one of the very important element in any electronic circuit. Okay, so in order to miniaturize these capacitors, one need to search for high K materials. And how to increase the dielectric constant? You can basically let's see, if you look into the existing literature, then PbTiO3, lead titanate, is one of the very good material. But since the lead is not really good for the environment, so the people are searching for lead-free material. And in the case of lead-free material, if you engineer your system in such a way that you get the high value of polarization, either engineer your system for a strain or due to structural disorder, or you can think of some more innovative ideas. Okay, so anything which is a lead-free and which is of high K, high dielectric constant, so that is going to serve the purpose. Okay. In fact, these materials are not only used as a capacitor, but these materials are also used as a insulating layer in a case of you know that these Intel chips, whatever we are trying to make. So in the case of MOS, so this semiconductor layer between the transistor and the electrode, that is also basically fabricated using this type of high K material. So when you do anything which is of high K, okay, high dielectric constant, it will basically help you in getting the more appropriate postdoctoral position into the industry or into the any academic institution. Those who are basically working in applied type of material.
Thank you, Dr. Pankaj Sadhguru, sir. As the chairman of the session, I'm really thankful to you. And on behalf of this conference, you are one of the sources from the IITs. You are advised all the students on the topic and explain everything about the physics phase except for the Thank you, sir. Now,
sir, 5 minutes. Dr. Dhobde is joined us. So I just want to brief introduce the doctor.
No, madam. I'm just this colleague of the department. Don't have any introduction required.
No, sir, because Dr. Dhobde is proud for our university as well as our department because he is just ranked world 2% scientist for high citation indeed and high number of publications. So it's really proudable moment for our university as well as our department. So I take the privilege to introduce Dr. Dhobde. Sir is presently serving as a professor in Department of Physics, RTMNU. He is one of the well-known renowned researcher in India. He is the director of Inter-Institutional Computer Center, RTMNU, chairman of Luminescence Society of India, Vidarbha chapter, vice president of Luminescence Society of India. Sir has been awarded the India's Top Faculty Research Award 2018. He has a teaching and administrative experience of around 26 years. Sir has more than 1,700 publications in national and international journals, which is really creditable. A conference proceeding, author 19 books, 15 chapters, and editor of 3 international publications. He has guided more than 60 PhD scholars. He has completed around 7 research projects sponsored by UGC, BRNS, RTMNU, NRP. Sir is the reviewer of more than 27 international peer-reviewed journals. And
thank you.
Is very wide. Just I conclude. Sir, I am concluding. His research area includes synthesis and spectroscopic characterization of quantum dot for solar cell, preparation and characterization of thermoluminescence radiation, dosimetry phosphorus, preparation and characterization of inorganic and organic lamp phosphorus, development of optoelectronic materials, synthesis and luminescence, studies of phototherapy, lamp phosphorus, development of devices for measuring luminescence. So this list is endless, sir. So it's our privilege to have you, sir. So I request Dr. Please conduct the next session, sir. Please conduct the next. Okay. Yeah, sir.
For outstanding contributor to Professor, I must congratulate him from my heart. Thank you, Professor.
Sir.
Doing a lot of work and a lot of contributions. Thank you, Professor.
Thank you, sir. Thank you, sir. So now continue this session. And second invited speaker in the session, Dr. Kiran Singh from Department of Physics, NIT Jalandhar. This topic of invited topic is structural correlation in the enhancement of ferroelectric property of SR2 GeTiO3. Dr. Kiran Singh is presently serving as assistant professor in Dr. B.R. Ambedkar National Institute of Technology, Jalandhar. He obtained his PhD degree from Barkatullah University, Bhopal, MP. His research interests include functional oxide materials, and he has around 73 research publications high reputed with high impact factor and 17 conference proceedings. Sir had been on several distinguished positions, scientists at the UGC BE platform, and he is also visiting fellow in a number of countries. Now I'm invited Dr. Kiran Singh for please deliver your invited talk. Welcome, Dr. Kiran Singh. Please continue, sir.
Thank you, sir. Can you hear me?
Yeah. Yes, sir. Yes, sir.
Okay. So very good afternoon to all of you, and I'm very much thankful to all the organizers, especially Professor Smita, for giving me this opportunity to share some of my research work with this very renowned Society of Ferroelectric Materials. So, okay. So, can you see my presentation? Because I'm using first time this one. Okay.
Yeah, sir. Yes.
Okay. So, thank you very much. And I am working in the field of ferroelectric and multiferric material. Basically, multiferrics is my best choice. I have contributed in many ways in the field of multiferrics. It is not only the measurement or investigation of multiferric materials, but I have also contributed significantly in the development of multiferric facility, because you all know that the measurement required for multiferric is not available commercially. Recently, some people try to sell that, but the cost is very high. So today I will talk about structure correlation with the ferroelectric properties of strontium dope barium titanate, and I will also take the advantage to explain our new results on new multiferric, that is Mn2O3. It is a very old compound, but we have discovered firstly the multiferricity in this very common materials. Okay, so as there were many interesting talks related to the basics of dielectric, let me make it full screen actually. Okay, so there are many talks on the basics of dielectric, basics of ferroelectric, and basic of multiferricity. Yesterday there was very interesting talks, and today also, and recently Dr. Pankaj talked about barium titanate. So I will not bore you more related to the basic properties, but I will try to explain you how we can proceed to perform the dielectric as well as the multiferric measurement properties. Okay, so as you all know that material science, lot of interest is going on, and it is not only one field, but you can see that we are using material science in every aspect. For example, in your mobile, battery, computers, even in textiles, data storage, medical application, and in transport, and certainly in electronics, we are using the material science. And in all these advancements, somewhere we are utilizing dielectric materials. I hope you know that you are using dielectric materials in your everyday life. In the morning when you are going to your kitchen to light the gas, that time you are using the gas lighter, and that gas lighter also has dielectric material, that is the piezoelectric material. And I hope that you all know how that gas lighter enlight your gas. If you are not aware, please go to your kitchen and see that how there will be spark when you press the gas lighter knob. Okay, and I hope most of you are using automobiles. For example, you are riding scooty or bike. Then please think how the buzzer of that indicator works. It also has a capacitor. Just try to open that buzzer. You will find it in 30 rupees. Go to a mechanical shop and you ask them, okay, give us the buzzer. And if you open that buzzer also has piezoelectric materials. So, and more importantly, I would like to mention here that these dielectric or piezoelectric materials are also used as clean and green renewable energy sources. I don't know, you are from Nagpur, and I heard that in the Nagpur railway station, one engineer put the device where you can dance and produce the electricity. I don't know whether it is true or not, but the concept is true. I have developed this device in my office, also at here as well as at Indore, that you can produce the electricity by applying the mechanical stress. Okay. So without putting much stress on you, I would like to explain the outline of my talk will be, I will talk about the dielectric and multiferrics. Basically, I will discuss with the instrumentation required to perform such measurements. Then I will briefly discuss about the ferroelectric property of the strontium dope barium titanate. Barium titanate is a very old system, as Dr. Pankaj already mentioned, that people are looking for the lead-free materials, and hence the barium titanate again got the intention, because here you can have the possibility to have high dielectric constant, as well as you can enhance the ferroelectric properties. So I will demonstrate you that, okay, with strontium doping, there is enhancement in the ferroelectric properties of barium titanate. Not only that, I will also try to explain that why this strontium dope sample shows high ferroelectric properties. Then I will cover the multiferric properties of Mn2O3 and new multiferrics. If time permits, I will also recapitulate other multiferric materials where we have contributed, followed by conclusion. I request the organizer, please, you can stop me at any time if you feel that, okay, I am taking too much time. You can remind me before 10 minutes so that I will stop. I will cover the topic as per the time available. So yesterday you already listened about the phase transition, but there were a lot of equations. It was explained very nicely by Dr. Dilip. But today, so you know what is a phase transition. What is a phase transition? Phase transition is nothing, but it is the transformation of a thermodynamic system from one phase or state to the another. And you already know the phase transition. You already know that water having three states, you can find it in solid, liquid, and gases. Can you see that, or do you try to notice that what is the difference when the water is in the solid state and when it is in the liquid state? If you want to correlate it at the molecular level, then you can see that molecules of water, when it is in a solid form, is more order than as compared to the liquids. So it is basically related to the ordering of the molecules. So, but when we talk about the phase transition in solid state, then we are not talking about the transition from solid to gas or gas to solid to liquid and liquid to gas, but we are mainly focused on the transition from solid to solid phase transition. Okay, so you already know that the phase transition can be governed by the change in the temperature as well as change in the pressure. So is there any other way by which we can have the phase transition? Okay, you don't have to answer this, I will answer this. Yes, there are the ways by which you can have the phase transition. You can have the phase transition with the application of applied field, and it can be magnetic field or it can be electric field. Then you can change the composition of the material, and all these things led to the change in the phases of the parent compounds. Okay, so you already familiar with two types of phase transition. So there are two types of phase transition, first order phase transition and second order phase transition. Okay, I will not go in much detail, but I will try to give you the correlation of the structural property with the physical property of the materials. So you are all familiar with the allotropes of carbon. Carbons are having two allotropes. One is diamond and another is graphite. If you look at the crystal structure of the diamond, then you can see that this carbon atom is covalently bonded with this four another carbon atoms, and diamond is having the hardest property, so it is a very hard material. But look at the graphite. In the graphite, each carbon atom is shared with this three other carbon atoms in the plane, and that is forming the covalent bond, whereas the fourth carbon atom is having the bond in the C direction, and that is forming the weakly van der Waals forces. So hence, in both the cases, the constituent atoms is carbon, but due to their structural properties, they are having different physical properties. So the message is that the physical properties or the properties of the material mostly depend on the crystal structure of the material, and hence it is very, very important to understand the crystal structure of the material, whether it is a ferroelectric material or whether it is a multiferric material. If you know the temperature dependent crystal structure, or if you correlate the crystal information with your physical properties, then you can understand the microscopic origin of all those properties. Okay, so yesterday Dr. Pradhan talked about this first order phase transition and second order phase transition, and he discussed about the latent heat is involved, and you know that at the first order phase transition there is discontinuity of the order parameter, whereas in case of second order parameter there is heat. Or you can say that in case of first order phase transition, latent heat is involved. And how you can find out the latent heat? For finding the latent heat, you have to perform the heat capacity measurement, and then from that you can find out the latent heat. But sometimes it is not easy to extract the latent heat. Then what is the way? Is there any way to say that whether the phase transition is first order or second order? Or how you can distinguish that there is a transition, or if there is a transition, then whether it is a first order phase transition or second order phase transition? The answer for that is you can take the help of transpose measurements, and these transport measurements are useful to give you the idea. I am repeating, giving you the idea. It is not the confirmation. It will give you the idea whether there is first order phase transition or not. So here I have written the term the thermal hysteresis. By thermal hysteresis, I mean that if you perform the transport measurement, or for example, in case of semiconductor sample, you are performing the resistivity as a function of temperature, and in case of dielectric, you have to perform dielectric measurement as a function of temperature. But for thermal hysteresis, you have to perform the measurement during cooling as well as warming, but the condition is you have to follow all the same conditions. For example, you should not change the ramping temperature, or means ramping temperature means you change the temperature in the same way during cooling measurement or in the warming measurement. You have to perform the controlled cooling and warming measurement. And if you are seeing the thermal hysteresis, then that is the indication that there is possibility of first order phase transition. I would like to mention one more thing here, that the thermal hysteresis can also arise due to instrumental artifact. So you have to take care of that one. Okay, so I assume, so this is the indication, this is the example for NdSrMnO3, this is the 50% strontium dope NdSrMnO3. So in this figures A, you can see that you can find out one red curve and one blue curve. So red curve is, this is the resistance as a function of temperature. Then you can see that red and blue curves are overlapping to each other in this temperature range, and at low temperature also. But if you see in the between, it is not overlapping. So let me see if I put the pointer. Okay. So, okay, I am talking about in this region. If you see that in this region, this blue and red curves, they are not overlapping to each other. So this is known as the thermal hysteresis. If you do the derivative of this one, then the transition during heating and during cooling will be at the different temperature. So I hope you understand what is the meaning of thermal hysteresis. If in any sample, if you have this type of feature, thermal hysteresis, then this is the first signature that your system can have first order phase transition. Because I can understand that in university or in many institutes, for example, here also at NIT Jalandhar, I don't have much research facilities. But we have the possibility, for example, you can approach UGC-DA Consortium for Scientific Research Indore for temperature dependent measurement, or you can approach RRCAT, or you can approach any people which is having this facility by showing these results. That okay, I have the thermal hysteresis in this one, and I want to know that whether there is a structural transition or not, then definitely they will entertain you and they will perform the measurement. Okay, this is the scenario for a semiconductor material. But if you have a similar thing you can see in the magnetization measurement. I don't know how many of you are aware of the magnetization measurement, but I believe that there are talks related to the multifluidic materials, then the audience are familiar with the magnetic measurements. So by performing the magnetization measurement, you can also get the idea if there is a first order phase transition or not. So I hope that you are familiar with the zero field cool cooling curve, field cool cooling warming curves, and field cool cooling curves. If you see the hysteresis between the field cool warming curves and the field cool cooling curve, then that is also giving you the signature that this material can have the first order phase transition. I will not put more time on this one now. So these transitions are, I talk about these transitions are the thermal hysteresis as a function of temperature. Means you are increasing the temperature and decreasing the temperature performing the measurement, and you are seeing the thermal hysteresis. But there are certain material also, for example, here in this case, you can see that here this is the MH curve, and you can see that there is some abnormal behavior in these MH curves. It is not like a ferromagnetic. So you can see that if you see this curve, then you can have field-induced phase transitions. So such type of behavior is known as the field-induced phase transition. And in previous talk, Dr. Pankaj also showed such results for polarization versus electric field, but these are the results with magnetic field, magnetization versus magnetic field. So in this system, you can see field-induced phase transition and a certain temperature. So here your temperature is same, your temperature is constant, but you are changing the magnetization by applying the external magnetic field, and you can see that there is field-induced transition. So now I want to ask you that we all know that when we apply the magnetic field, then we are changing the orientation of the spin, or we are aligning the domains if it is a ferromagnetic sample. But now my question is, can we change the crystal structure of the material by applying the magnetic field? So I will show you such beautiful results in the coming slide, but now I will explain you that you already know about when you have the choice of measurement depends on the type of material, on type of material you are working. If you are working on a dielectric material, then you cannot perform the DC resistance measurement because all dielectrics are insulator. Then what you have to do, you have to perform temperature dependent dielectric, and during cooling and warming, then you can see that, okay, for example, this is the case of barium titanate, and barium titanate has three transition. It is cubic at higher temperature, then from cubic to tetragonal, and then tetragonal to orthorhombic, and orthorhombic to rhombohedral transition. And you already know that the direction of polarization is different in different temperature regions as per their crystal structure. So in this figure, if you see carefully that we have seen the hysteresis during cooling and warming in this orthorhombic to rhomboidal transition as well as tetragonal to orthorhombic transition. But there is some mistake here. It is also a hysteresis at cubic to tetragonal transition because it is a first order phase transition. Okay, if someone has any question or if they want to ask the question, you can ask me. Okay, so I talk about that, okay, isothermally we can have the magnetic field induced phase transition. So I will directly come that at the UGCDA Consortium for Scientific Research, we have the research facility where you can perform the X-ray diffraction in the presence of magnetic field, or you can perform as a function of temperature and magnetic field both simultaneously. And Dr. Lalla is the in charge of this facility. He is the expert of all these instruments, and I was fortunate that I got the opportunity to work with him at UGCDA Consortium of Scientific Research Indore, and we have developed this facility where you can perform the X-ray diffraction measurement in the presence of magnetic field. So briefly, I will, for more detail, you can go to this paper, but I will explain you that, okay, you just see these things that, okay, blue curves and the red curves. And this blue curves are related to the high temperature phase, which is tetragonal, but when you apply, and the low temperature phase is orthorhombic FFM. But when you apply the magnetic field, then you can change this low temperature antiferromagnetic phase to a high temperature ferromagnetic phase. Means it is not only the alignment of the spin, but we can change the crystal structure of the material by applying the external magnetic field. So okay, so this is the setup, and it is working very well from 2 to 300 Kelvin, and you can do the diffraction measurement from 0 to 8 Tesla. So here are the few results. You can see that how we can tune the crystal structure of the material by applying the external magnetic field. It is not with temperature and pressure, and I hope this is the first results in this conference. I am showing that we can tune the crystal structure even by applying the magnetic field. But the choice of those samples should have the property as I have shown in the previous slide. There should be magnetic field induced phase transition. Okay, so I will skip this. So now I will come to the application of dielectric measurement in the material science. By performing the dielectric measurement, what you can do in the material science, you can find out the phase transition. You can find out the dynamics as Professor Yusuf mentioned in the afternoon talk, and you can also find out grain and grain boundary contribution. You can find out the conduction mechanism. But when you are working on the magnetic materials, then you can find out the correlation of the dielectric transition with the magnetic ordering, and then you can investigate whether this material having the magnetoelectric properties or not. Okay, so now come to the instrumentation required for the dielectric measurement. For dielectric measurement, one basic thing is you need a LCR meter. Okay, and if you want to perform the measurement only at room temperature, you don't need a temperature controller. But if you want to measure, if you want to establish the facility for low temperature, so you need a temperature controller. And this is an insert. It is a homemade insert. We have made this insert at UGCDA Consortium for Scientific Research Indore. And we have this liquid nitrogen debar. You need one vacuum pump. And by having this facility, we can measure the dielectric constant from liquid nitrogen temperature to a high temperature. High temperature you can go, this setup is going for example, 420 Kelvin, but you can go for a higher temperature also. So by having these basic facilities, you can develop your research facility at your end. And but the thing is, students should have the zeal to develop the research facility, because by these you can measure all these 16 parameters. And sometimes students are asking that how many number of points we can get from this frequency to this frequency range. It is up to you. You can write your own program, and you can take as much as data points you need. So this is the basic requirement for the dielectric measurement. If anybody need any help, you can contact me. Okay. And if you want to go for the multifluoric and magnetoelectric property measurements, then because it is related to the magnetoelectric, and most of the multifluorics are showing interesting property at low temperature, so you need the low temperature measurements. And because you want to explore the control of the dielectric property or dielectric polarization with the help of magnetic field, then you need the magnetic field also. So you need a PPMS or any magnet. So I can understand that getting a magnet is not an easy task, but if somebody has the magnet, they can develop this facility. So first thing what you have to do if you want to explore that this material is a multifluorics or not, first you have to perform the magnetization of that measurement, and the second thing is that material should be insulator. And then you measure the dielectric as a function of temperature, but the condition is you should measure the dielectric as a function of temperature at different frequencies. Because in the previous talk you saw that there are some Relaxer also, so Relaxer Ferroelectrics are also there. So if you have the frequency independent behavior at the magnetic ordering temperature, so this is the first signature that okay, you have the coupling between the dielectric and the magnetic ordering parameters. So another thing what people are doing, people are performing the dielectric in the presence of magnetic field to explore the magnetoelectric or magnetodielectric property. So these are the results for copper chromium oxide dielectric materials. You can see that okay, when I increase the magnetic field, then what is happening to the dielectric constant below this transition temperature 25? It is decreasing. But if you notice here that the transition which is at 25 Kelvin, it is quite robust because this material is highly insulating, and this transition temperature is not shifting by the application of magnetic field even at 14 Tesla. So what it tells us? It tells us that this material is strongly interferomagnetic, and we are unable to switch this transition temperature with this 14 Tesla magnetic field. So from this type of measurement are useful if you want to show that if the transition temperature is shifting or not. But if you want to probe that correct magnitude of magnetodielectric, then I recommend that you should do isothermal magnetodielectric measurement, and these isothermal measurements give you a lot of other information, not only the correct magnitude of magnetodielectric. See in this one. In this one you can see that your dielectric constant is changing with the magnetic field. Okay, but you don't know how it is behaving. It is behaving linearly or it is behaving coordinately. Or okay, if you fit it, you can find out the trend whether it in which way it is varying. But if you see that this is the isothermal measurement, you fix the temperature, you ramp the magnetic field in the positive direction, come to the zero, go to the negative direction, it should give you the butterfly loop. In this picture, you can see that there is some hysteresis around the 5 Tesla. What it tells us? It tells us that this material can have magnetic field induced transition. I will cover it if the time permit. Okay. Then for ferroelectric measurement, there are two ways. You can measure the PE loops and you can measure the pyroelectric measurement. And these are the PE loop related to the banana skin. I hope that you all are familiar with this one. So while taking the PE loop, you have to be very conscious. And I don't know whether you people are familiar with the pyroelectric measurement or not. In the pyroelectric measurement, you can do the pyroelectric measurement by using the electrometer. And you apply the electric field during cooling. And while warming, you measure the current, but the best way to measure is the charge. Okay, so in this way you can measure you can prove the ferroelectricity, but this is only for one side. If you change the Pauling electric field, if you are able to switch the electric polarization by reversing the Pauling electric field, then by pyroelectric measurement you can confirm that this material is a ferroelectric material. Well, okay, so you can ask me that we have the PE loop, why we have to go for the pyroelectric measurement. Pyroelectric measurements are much sensitive than the PE loops, and all the multivariate which show the ferroelectric properties at low temperature, it is really, really dangerous to apply very high electric field at low temperature inside the magnet. So you have to be very conscious when you are performing the PE loop inside the magnet. But pyroelectric measurements are quite safer as compared to the PE loop. But you need the expertise how to perform the pyroelectric measurement. I will show you the comparison of pyroelectric measurement as well as the PE loop. How much time do I have, sir? Okay, sir. Thank you so much, sir. Yeah. So I want to address that. Okay, what is the strength when you do the dielectric measurements? So, for example, in case of copper chromium oxide, this is the magnetization curve. It is almost linear, and from this one you can conclude that there is no field-induced transition. Similarly for silver chromium. But I have shown you this curve, the magnetodielectric measurement. Here you can clearly saw that there is field-induced transition, and this field-induced transition can be seen in case of magnetodielectric. So what I want to say that sometimes magnetodielectric measurements are really very, very sensitive for field-induced phase transition, which you may miss in the magnetization measurement. Similarly, in the spin chain system, if you see that, for example, in this 2K, if you see the magnetization curve, you can see that there are 2 transitions, but our dielectric results show there are 3 transitions. If you, for example, if you check the curves for this 12.5 Kelvin, let me put the cursor here. I am talking about this plot. If you see the magnetization, you are unable to see any transition. But if you do the derivative, you will see there is some field-induced transition. But when you compare these data with magnetodielectric measurement, you can see that there is a clear-cut transition here, and you have this one. So what I want to say that magnetodielectric measurements are really very, very sensitive for field-induced phase transition. Okay. We have talked about the hysteresis, and this is one sample. You can see that, okay, this is the dielectric as a function of temperature from 100 Kelvin to 300 Kelvin. You can see that dielectric constant changing from 9 to 12. The change in dielectric constant is very, very less. But if you see it more clearly in this range from 110 Kelvin to 160 Kelvin, you can see the variation in the dielectric from 9.30 to almost 9.40. So the change in the dielectric is at the first decimal. And in this 0.1 change in the dielectric for this wide range of temperature, if you see that, you can see the clear hysteresis during cooling and warming. Whatever the data I am showing, these are the data from the setup which we have made by ourselves. We have used the electronic component and all the other things, temperature dependent property we have measured on our prepared samples. So if you do the temperature dependent measurement of this sample, so you can see that higher temperature you are having the 1 peak, but at low temperature you can have the 3 peaks. So there is a structure transition from cubic to orthorhombic. I will not go in detail that why there are 3 peaks in case of orthorhombic and 1 peak in case of cubic. I hope you know about this, because in case of orthorhombic, A is not equal to B, not equal to C. Okay, I will skip this because, okay, now I will talk about this strontium dope barium titanate. So you already know the basic property of barium titanate, that there are three structure transition or three-phase transition. When we dope, I will focus basically on this 80-20%, 20% strontium at the barium side, because so you can see that if you see this curve, you can see that there is a clear-cut enhancement in the dielectric property of the strontium dope material as compared to the pure barium titanate. So from this, you will be very happy that, okay, these are peaks are frequency independent, and okay, it is showing the long range ordering. Of course, it is showing the long range ordering, but there are certain things which are you cannot extract from the real part, then you have to go through the tan and delta. If you see the tan delta, you can see that there are certain additional features which you cannot notice in this real part of dielectric. For example, in this region, if you see that there is a frequency dispersion in this one. So you have clear-cut frequency dependent in this range, along with this long range 3 transition, which is at 335 Kelvin, 250 Kelvin, and 185 Kelvin. So what is the origin of these? Okay. So I have here in this figure, I have shown you only the warming curves, but in this one you can see that warming and cooling curves, you can see the clear hysteresis, and this frequency dispersion can be analyzed, and you can find out the relaxation time of the materials. Okay, so what I want to say that in case of strontium, 20% strontium dope barium titanate, there are 3 clear-cut phase transition, but in addition to these 3 clear-cut transitions, there is some relaxation type or sub-relaxation near the transition temperature from this in this range from 280 Kelvin to 300 Kelvin. So, and I have also demonstrated you that the dielectric constant of this strontium dope sample enhanced. So why it is enhanced? We already know that barium titanate is tetragonal at room temperature, and in the previous literature for strontium dope also people believe that, okay, it is tetragonal. Of course it looks tetragonal, because if you see this one, this is very well fitted with the tetragonal phase. But if you zoom this, then you can find that, okay, this peak is not coming in this tetragonal phase. It is a very big peak, but it is there, still there. I will cover it in the next slide. So now we have to look that, okay, is it a single phase, or it is a multi-phase, or it is a impurity. So we have checked that, okay, this peak is not related to any impurity. Then we already know that in dielectric we have the relaxer type behavior near room temperature. Then we have looked for this glacier tilt and other things, and we find out that it is not a pure tetragonal phase at room temperature, but it is a combination of tetragonal as well as the rhombohedral phase. Okay, from this diffraction, we want to say that 20% strontium dope sample is not having pure tetragonal phase at room temperature, but it has some precursor of rhombohedral phase also. So now this is a P-loop measurement. The dielectric constant enhanced significantly. When we perform the dielectric P-loop at room temperature, then you can see that in case of a strontium dope sample, there is significant enhancement in the ferroelectric property of the barium titanate, which is our desire. Actually, we want to enhance the ferroelectric property of barium titanate. Okay. So now with this setup, if you have this setup, you can design your insert and you can make the temperature dependent measurements. These all temperature dependent measurements are again performed by our insert. We have it is made by ourselves, and you can see that the P loop at different temperature, it is showing very nice P loop, and you can also see the variation of the polarization at different temperature. If I extract the saturated polarization from this one, then this is the temperature dependent polarization behavior of this one, strontium dope. The interesting thing is at the transition temperature, you can have the clear-cut change in the polarization, and this clear-cut change in the polarization is related to the single crystal of the barium titanate. So we can say that our prepared sample is very, very good, and all these measurements are consisting with the single crystal. So now some people, so these are the pyroelectric polarization measurement by using the P loop. But if you don't have the P loop, then how you can do? You can perform the pyroelectric measurement by using the electrometer. And then you can find out the electrocaloric effect also. And this is the heat capacity measurement, which is again performed on the homemade setup. And in this one also you can see the three clear-cut phase transition, and you already know that, okay, we can find out the electrocaloric effect, which is related to the change in the polarization with temperature and the heat capacity. So by performing this, we have said that, okay, in this strontium dope samples, the delta T is equal to 0.2 Kelvin. So this sample also shows good electrocaloric effect, which is also a good thing to work in this area. So, okay, so we were talking about this peak at this one, at room temperature, we have seen this peak. So now we have performed the temperature dependent measurement. Interestingly, you can see that, okay, at 250 there is no peak, but at 280 you can see there is appearance of this small peak, and at 300 also, and the intensity of this peak is keep increasing, and it is completely vanishing at 350. So what we have that it has a correlation with the relaxation behavior, and the relaxation behavior is related to the combination of orthorhombic and the rhombohedral phase. Okay, then we have performed the temperature dependent Raman to establish the correlation with the vibration modes. So in the Raman also you can see that some peaks are disappear as we increase the temperature. I will not go in much detail, but we can establish the correlation with the dielectric, ferroelectric and the lattice vibration. And we have discussed the origin of enhancement of ferroelectric properties of barium titanate. So I will so I will skip this basic of multiferric, but I want to share you this slide and okay, why the ferroelectric and the ferromagnetism are different, and why it is difficult to have multiferric materials. So the basic difficulty is for a ferroelectric material, what you need the sample should be insulator. But when we talk about the magnetism, we need the unpaired spins. Okay, so what is the choice? The frustrated magnet is the most suitable magnet. Most choice where you can find out new multiferric materials. Here I have listed some of the material which is showing the multiferric and magnetoelectric coupling, and some are mentioned with the black font and another are the green. The other are with the blue. So all these blue compound, these are the compound in which we have discovered the multiferricity first time, and other people has followed us. So I have contributed, for example, AgCr, S2O, CaCr2O4, and in the spinel Fe and nickel chromium oxide, Fe, V2O4, it is the spin chain system, DYO3, and this is a very famous compound where I was doing the postdoc, gallium, vanadium, and sulfate. It shows that not only the oxide, but sulfate can also be the most suitable candidate for multiferricity. And if you yes, sir. Okay, sir. I will conclude now. I will not go for the other properties. So this is a system where instead of germanium they have put gallium and they have observed the fermion in the multiferrics. So with this one, I will skip all these things and I will just show you that in case of Mn2O3 we have proved that in the literature it was assumed that okay, it is a cubic at room temperature, but with the help of synchrotron radiation we have proved that it is not cubic but it is orthorhombic at room temperature. And then we have proved that it is having hysteresis during cooling and warming at 25 Kelvin, because earlier people are believing that it is having only one transition, but we have shown that there are two transitions, but instead of these two transitions, in case of Mn2O3 there is a tail-like feature above the magnetic transition, and in case of neutron diffraction also they have seen there is this 100 peak persist up to 100 Kelvin. So this is the material which is insulator, and no one has performed the dielectric measurement or multiferric measurement on this sample, and we have performed the dielectric measurement and we have seen the strong correlation with the at the magnetic outing temperature. And then if we do the derivative, and this transition is independent of magnetic field up to 8 Tesla, and then as I have shown that there is a tail-like feature in the magnetization, this tail-like feature is also persist in case of dielectric measurements. And then the beauty of this one is this tail-like feature, the polarization started from this 105 Kelvin, and you can control this polarization with the application of magnetic field. So this shows that Mn2O3 is the new multifluorics. I will not go in much detail, but from crystal structure, I will tell you, if you see the crystal structure of this one, Mn2O3 as a function of temperature, then you can find many interesting features. And then you can see the change in the lattice parameter at the magnetic ordinary temperature, and you can see the change in the bond length at the all transition temperature. And this is related to, we have fitted the data by using the PCAB symmetry and PCA21 symmetry, and if you see, you can see the difference. So this is the most suitable space group for the low temperature. So we can say that it can has the non-centrosymmetric space group at the low temperatures. So this paper Mn2O3 from the German group, it is published in the Nature Communication in the 31st July 2018. But our results published. We have also submitted the same work, this work, to the Nature Communication, but they said that we have already having the same paper, and our paper is online on 29 January. So in this way, we have missed this Nature Communication. But the good thing is we are competing with the renowned group across the world, and we are doing good in the multifluoric field. So these are some of the other results. There is another class of multi-glass. I will not go in detail, but just a brief, as in the relaxer, or the spin glass, and you have the relaxer. So in one system, you can have both together. This is known as the multi-glass. So with this one, what I have taught you, I have taught about the phase transition, why it is very, very important in case of ferroelectric and multifluorics, and I have talked about the instrumentation of ferroelectric and multifluoric and structure correlation, and I have also mentioned that you can find out the new multifluorics in a frustrated magnet, or not only the oxide but the other non-oxide material can also be a suitable candidate for multifluorics. But the thing is, they should be insulator. And these are my two students who contributed a lot in the development for this research facilities. I would like to thank all my collaborators for performing all these measurements, helping me, for example, in the synchrotron, Archana Sakdev, Manvinder Singh, and Dr. Sinha from RLCAT, and my collaborator at a different organization. And thank you very much for your kind patience. Thanks. I will be happy to answer your questions.
Thank you, Sir. I am very happy. You have the two questions for participants. Sir, change of magnetic in the HRD measurement can be done on bismuth ferrites as its multiferrite. This is of Bushra.
Let me go to my platform so that I can see you. I don't know from where I have to go. Can you see me?
Yeah.
Okay, I don't know how to come back. Okay. I saw something, yes.
Okay, we can see.
So, for example, for this field-induced phase transition, I have shown you the results that, you should have the change isothermal field-induced phase transition. If in case of bismuth ferrite, there is no magnetic field-induced phase transition. So I don't think that in case of bismuth ferrite, you can have the change in the crystal structure by the application of magnetic field. It is also related to the magnetostriction, maybe, but I don't know in case of bismuth ferrite, because I have not seen any field-induced phase transition in the magnetization.
Sir, again one question for the same person. What is the reason of not saturation of PE loops in the field?
It depends. If you have this, so you are talking about, sometimes you will not have the square loop because you have some paraelectric behavior also. So you have that. You cannot have such saturated P loop. But in fact, the saturation you should not have saturated P loop, because the slope of the P loop tells you the dielectric constant of that material.
So next question from Vijay Deshmukh. Sir, what condition the ferroelectric material can lose their ferroelectric nature?
Pardon?
In what condition the ferroelectric material can lose their ferroelectric nature?
There are many reasons. First thing is, ferroelectric materials have clear-cut transition. If it is a true ferroelectric to paraelectric material, ferroelectric to paraelectric behavior, you just change the temperature of the material, you will change it from ferroelectric to paraelectric. or by substituting also. You dope it, you can change your material can become paraelectric. If you are putting, for example, because for ferroelectricity, centrosymmetric, non-centrosymmetric crystal structure is required. If you are breaking that non-centrosymmetry, you can change the ferroelectric to paraelectric by substitution. But if you have a ferroelectric material, just change the temperature. You will find a temperature where the ferroelectricity loss, and that is known as the ferroelectric to paraelectric transition temperature. And you can find that from the dielectric measurement itself.
Sir, next question comes from enhancement with ferroelectric property would be useful to design high quality ferroelectric material. Is there any effect of doping with different ionic size or different structure properties?
Sir, can you repeat? I want to see actually everything. I don't know how to see you people.
Oh, okay. Sir, enhancement of ferroelectric property.
Should I stop sharing? Should I stop sharing? Then I will see all of you.
Yeah.
Okay, let me see. Yes, I think now I can see all of you. Yeah, so what is the question, sir? Can you repeat?
Enhancement in ferroelectric property is useful to design high quality ferroelectric materials. It is
yes,
there
exactly.
any effect of doping with different ionic size or different percentage of doping?
Yes, it depends on. Now I can see. Now I am happiest person. Yeah. Now I can see the questions also. Yes, definitely by choosing the suitable dopant, you can enhance the ferroelectric property. But sometimes you can kill the ferroelectric property also. So you have to do the systematic study. Sometimes you will increase the ferroelectric property, but you can reduce the transition temperature. So that depends, and you can tune it. Definitely, you can tune it.
Sir, recently you used the bus of nature communication. So I hope in coming few times you will continue submit your paper nature communication may be accepted. And you are very good luck for you.
Thank you, sir. Thank you very much for your best wishes.
Again, sir, at the Nagpur railway station, they are jumping process some piezoelectric materials that generate some electric power. This is true. Again, one of the institutes of VNIT is push the piezoelectric material in the shoes at the bottom, and during the walking, this generates the electricity and charge the mobile. This is also happening in the Nagpur.
Yes, great. I know about those charging shoes, but the biggest problem for the charging shoes is because the current produced by this piezoelectric generator are very small. But I encourage the students that go and see. I gave you the example of buzzer of your bike. That is also having the piezo material. Go in the kitchen and see how this gas lighter is working. Why that light or why that spark is not coming straight, why it is coming always on the side. I hope they will learn something new.
Sir, one more question. Near to ferroelectric, as per your talk, application of the ferroelectric material. So any device that use the ferroelectric material, which type of the material cover use this surrounding the ferroelectric material? Which type of the material used? Which type of the material used for the cover of the ferroelectric material in any device? What is the characteristic of this ferroelectric material? Cover material property.
ढोबळे सर वो रिजोनेंस आ रहा
है. I am not getting.
चालू है क्या?
अभी शुरू है. Okay. I close. Okay, I close my video. Just audio is the sir. Sir, my clear?
Yes, sir. Because I was unable to listen your question properly. That's why I keep myself unmute. So you please ask the question. I will try.
Sir, any device, just we are using the ferroelectric material for the particular application. So which type of material used for the cover this piezoelectric material in this device? What is the characteristic of this material for the cover the ferroelectric material?
Okay, sir. In which device, sir? For example, in gas lighter, we are using PZT.
Any device.
We are using PZT because that is having the large piezoelectric coefficient. Right now we are using zirconium dope lead titanate.
Just
yeah, whatever you are saying that, okay, you have developed an VIT, you are also using PZT. So now people are working on replacement of PZT.
Okay.
Okay, sir.
Thank you very much, sir.
And one more important thing is piezoelectric materials have millions of turnover because it is using not only in such devices, but it is also using in the nanoscale motor. For example, scanning tunneling microscope, atomic force microscope tips, all these are used piezoelectric sensors. Piezoelectric actuator and sensor. Even in ISRO, they are using piezoelectric sensor and actuator.
Thank you very much. Thank you for your very interesting and informative talk. And I hope from your talk so many students are motivated. Thank you very much, sir.
Thank you, sir. We are having two students from Nagpur. One Mayur, I think he worked with Professor Sumita. He is our PhD student in our department.
He joined with you. Okay. He joined with you, sir. Okay.
No, ma'am. He didn't join with me, but he's in our department. He joined with my colleague.
Okay, sir.
Thank you again for your.
You are accepting our students.
Thank you, sir. Thank you so much.
So in this session, again, it's a 3 oral. But first one is the Dr. Shubhagya Lakshmi Behra is not present. So only for the 2 oral presentation, oral 8 and oral 9. So now I am invited Mr. L. Tansanga from NIT Meghalaya. So please,
hello, sir.
Present your oral presentation on structural, electrical and ferroelectric characteristics of eco-friendly composite ceramic BIFAO 085 GD 01503. Yeah. Okay. Yeah. You can start. You have the 10 minutes, 8 minutes presentation and 2 minutes question and answer.
Okay.
Okay, you can start, sir.
Okay. Good afternoon, everyone. My name is L. Tansanga. I'm from MIT in Mizoram. My topic is structural and characteristics of open.
Just please close your video because we can't hear your audio properly. It's not clear. Your audio is
video, please, sir.
So maybe the data, just you close your video, so maybe you get higher bandwidth there. You close video, okay?
Okay, ma'am.
Your video,
close your video only.
Close your video. Hello, can you hear me? Hello?
Yes, ma'am.
Please close your video, please.
Hello?
We will try.
Yes, ma'am.
Sir, please you close your video. And start your presentation. Hello? Your sound is okay, no problem, but you close your video.
Yes, hello, sir. Video. Okay, sir. Like this.
At the down start video, you can click there.
So, sir, can you see my slide? Can you see my slide?
From where you share your slides, there is a start video option. You just click on there.
Ma'am, I want to
check your internet connection first.
So,
dear Dr. L. Tansanga, you close your video so that we are facing your sound. Okay, please close your video. At the bottom, one is the start video. Just you can click it.
Okay, now.
Voice is not clear, sir. Thank you. Yes, you can start now. Sir, please start your presentation.
Sir, actually, he is not unmute himself. He keep in mute. Due to that, we can't hear.
Yeah. He is also mute also. And video also up. No, he's unmute. Okay.
Oh,
You can
hello.
start. Start.
Okay.
Hello. Okay. My name is Etan. I am from MIT Mizoram. Today my topic is structural, electrical, and ferroelectric characteristics of eco-friendly composite ceramic, BIF 0.85, gadolinium 0.1503. Here is the introduction, motivation, experimental, result, and discussion. Motivation. Introduction part. Here is introduction. The objective of present is to develop a solid synthesis for output ferrite of high quality and reproducibility, and then to characterize structural, electrical, and ferroelectric properties of each composition. This ferrite considered one of the best multiferroid materials for advanced device application because it has ferroelectric as well as properties for room temperature. Its Curie temperature is 830 degrees centigrade and Nil temperature is 370 degrees centigrade. However, there is a main problem some high current leakage density, high tungsten loss, and structural distortion, which affects the dielectric and other electrical properties. That subsequently results limit of application in functional devices. Here are the motivation points. The development of lead-free material is driven by concerns for health, safety, environment. And bismuth ferrite was identified as a desirable lead-free candidate due to its potential devices, magnetically modulated transducers, optoelectronic devices, sensors, and so on. Therefore, in order to reduce the inherent problems and to enhance electric as well as magnetic properties, various dopants, substrates, and additives have been added to BFO. Here is the experimental procedure as shown in the figure. First, this experiment is done through solid-state reaction method. By first, we collect the high purity of the after mixing 4 hours and after calcination for 6 hours at 750 degrees centigrade. And after that, grinding again and start making pelletization. After pellets, we sintering process. We do sintering process takes around 6 to 8 hours. And after that, we get this solid compound and the characterization starts. Here is the result and discussion of this compound. X-ray diffraction analysis. The prepared sample was recorded by using a X-ray diffractometer within a bracket 20 degree to 60 degrees centigrade or 60 degree. The detailed analysis of this diffraction provided the phase formation of the sample. Here as shown in the figure, it is illustrated in the graph that most of the peaks have narrow and sharp intensities, which suggests a high crystalline nature of the sample. The reflection peaks were indexed by using Portnoy software, and it strongly satisfied the perovskite structure with an orthorhombic symmetry. SEM and EDX analysis. SEM micrograph shows most of the grains are densely packed throughout the surface without major voids. The height, difference shape, and size of the grains suggests the formation of a good quality of the sample, and the average grain size is found to be 491 nanometer. The chemical composition using EDX and the EDX pattern shows the presence of constituent elements like bismuth ferrite, bismuth, iron, and oxygen without any traces of impurities in the prepared sample. Here is the dielectric characteristics of temperature dependent. The first graph shows the temperature dependent dielectric constant, and as shown in the figure, the dielectric constant gradually increases as the temperature increases due to the electron-phonon interaction. However, the value of dielectric constant decreases with the frequency. This it may be due to the effect of charge accumulation at the grain boundaries. Peaks observed in the figure indicate presence of phase transitions in the material. Temperature dependent dielectric loss shows figure B shows the temperature dependent dielectric loss. Here we have two peaks at 310 degrees centigrade and 350 degrees centigrade, which were attributed to random dispersion of thermally influenced charge carriers and maybe due to the oxygen vacancies created during the synthesis process. The tan delta plot clearly illustrates higher value of loss factor at low frequency curves, which occurs mainly due to the presence of iron in the compound. Here is the impedance characteristics. Real part of this graph shows the real part of impedance characteristics, and the Z prime decrease with the increase of frequencies. This is the nature of the plot may be due to the release of space charge, and in the low frequency region there is a decrease in the value of Z prime with the rise in temperature, which the increase of conductivity, and the decreasing nature of Z prime at low frequency confirms the presence of a negative temperature coefficient of resistance behavior in the compound. Here is the imaginary part of impedance characteristics. This figure shows, as shown in the figure, the value of the double prime decreases with the rise of both frequency and temperature. The broadening of peak increase with the increase of temperature, which shows the existence of temperatures dependence of temperature dependent electrical process in the material. The decreasing nature of Z prime with the rise of frequency is due to the release of space charge polarization. The peak shows the presence of different types of electrical relaxation process in the material, which may arise due to hopping of electrons, oxygen voids, and etc. Here is the AC conductivity. The AC conductivity curve, the frequency-dependent AC conductivity curve shows the AC conductivity increase with the increase of frequency as well as temperature. Space charge. The increment in the conductivity value rise with the rise of temperature. This recommends the NTCR behavior sample. And figure B shows the AC conductivity with the inverse temperature. And the trend of the graph shows the increasing behavior obeys Rn, and the activation energy is also calculated by using the Arrhenius relation, and from that we can see the activation energy decrease with the increase of temperature. And at 1 kilohertz, the activation energy is 0.15 and 0.54, region 2 and region 3 means higher temperatures. And while but for 1 megahertz, the activation energy 0.40 and 0.45. Here is the ferroelectric study. The PE loop shows this. It was carried out by applying 50 hertz frequency with a potential of 15 to 30 kilovolt. Saturated loop is not achieved due to the experimental limitations, and it is observed that the Redman horizon coercive fields values are increases with the increase of the loop size, and at 30 kilohertz, 30 kilovolt per centimeter external field applied, the calculated value of remnant polarization is 0.10 microcoulomb per centimeter square, and coercive field is 19.71 kilovolt per centimeter. And enhancement in the value of remnant polarization has been observed as compared with the pure BFO in this sample. Here is the conclusion. In summary, a multifunctional compound of this BFGO5 has been successfully synthesized through this reaction method. The structure changes from rhombohedral to orthorhombic symmetry through this doping. The cell parameters, lattice volume, and average crystallite size and microstructure are intensely affected through this doping, and a significant improvement in remnant polarization has also been observed in this work. Thus, based on the significant enhancement observed in dielectric and other electrical properties of this compound, it can be considered as a promising candidate for device applications. Here are some of my references. Thank you for your kind attention.
Very good presentations. Now some questions from Shoaib Abbas. In this compound Z, you have DIFO 0.85 dB for 3. What will be the effect on if we choose any other percentage of Fe and Gd? माझं नीचे काय म्हणा Sir, yes, madam, you can ask this question by Shoaib Abbas. Madam, please you ask this question of Shoaib Abbas.
Shoaib Abbas. No.
Hello.
There is two questions.
Yes. Yes, sir. So one question is in this composite, your material, what will be effect on it if we choose any other percentage of Fe and Gd? You understand the question? Yes, sir. Yes, sir. Yes, sir.
What did you say? Please you reply.
Sir, we prepare another concentration. That can be 0.5 and 10% also, and this is 15. So 5, 10, and 15% we prepare 3 samples. Hello, sir.
Another question from Shoaib Abbas. While preparing 800 degrees centigrade is followed, what will happen if we heat it more than this temperature or less than this temperature? Why are you selecting the 800 temperature?
Because it is the temperature based on its Curie temperature, sir, of bismuth ferrite.
Okay.
So if we use another, we may not get a good product, I think.
Okay, just will try to ask by email or something. No problem. Thank you, Amrita, for your presentation. Thank you very much. Now, next presentation is Mr. Praveen Athane from Department of Physics, University. His title is the Structural Ferroelectric and Piezoelectric Properties and Electric. BA 0.97, CA 0.03, CI 0.97, and SN 0.03 electroceramics. प्रवीण भाऊ सुरू करा.
ओके सर.
करा सुरू करा.
Hello.
Yes.
Hello. The screen is visible, sir, and I am audible to you.
Yes.
Okay. Thank you, sir. Myself, Praveen Kadne from Department of Physics, Pune University. Today I am going to present a presentation entitled Structural Ferroelectric and Piezoelectric Properties of Lead 3, BA 0.97, CA 0.03, TI 0.97, SN 0.03, O3 electroceramics. And I am doing this work under the guidance of Dr. R.C. Kamble. Okay, outline of my presentations are introduction to ferroelectric and piezoelectric material, orientation of the problem, synthesis and structural analysis, dielectric properties, ferroelectric and piezoelectric properties, and finally I will conclude my presentation.
So what is BA-3? BA-3 is a promisingly piezoelectric material which having a perovskite ABO3 type of structure, and it is used for its mostly used for dielectric properties rather than its piezoelectric properties, as the piezoelectric properties of the barium titanate are inferior than other electric materials. This is the structural transition in the barium titanate, and this structural transition depends on the temperature with the different rhomboidal, orthorhombic, tetragonal, and cubic structures. So perovskite structure BA-3 having a larger A cation at the 8 corners and smaller B cations at the body centered. The oxygen atoms are at the each face of the units, and the atomic positions of atoms in the barium titanate are these. The perovskite structure depends on the structural stability we call it as tolerance factor, and is given by this formula, and this tolerance factor decides the structure of the material from the deviation from its value of 1. Then, with the structural variation in barium titanate, the polarization in the unit cell of barium titanate changes. So, in rhomboidal structure, it is along 1-1-1 direction. In orthorhombic structure, it is along 0-1-1 direction, and in tetragonal structure, it is along 0-0-1 direction. And in cubic structure, there is no presence of polarization. Okay. So, piezoelectric effect. But there are two types of piezoelectric effect. One is direct piezoelectric effect, and other is a converse piezoelectric effect. In direct piezoelectric effect, when we apply pressure on a material, then it produces an electricity. And in converse piezoelectric effect, an applied electric field generates the strain in the material, and it's having a wide range of applications in the day-to-day life, and also the electronic industries of all over the world, like igniter, microphone, pressure sensors, actuators, speakers, and clocks. So, synthesis process is based on this flowchart for the solid-state reaction in the synthesis of BCTF material, and the final sintering of this material is done at the 1350 degrees Celsius for 10 hours. So results: XRD and ACM analysis of the BCTF material. The Figure 1 shows the X-ray diffraction patterns of BCTF material, and the X-ray diffraction patterns are in good agreement with the standard JCPDF PDF 050626, and which suggests that the pure formation of tetragonal perovskite structure without trace of any secondary phase formation. This shows the splitting of 002 and 200 at near about 45 degree to theta, and which clearly indicates that the formation of, or which giving an additional evidence to the formation of tetragonal structure with the higher intensity of 200 than the 00P. With the help of X-ray diffraction pattern, the calculated lattice parameters are A is equals to 3.9904 angstrom and C is equals to 4.0369 angstrom, with the C by a ratio of 1.0116 angstrom. The theoretical density is calculated by X-ray diffraction is observed to be 6 gram per centimeter cube. Then experimental density by Archimedes principle is observed for this composition is 5.90 gram per centimeter cube. With the analogy of theoretical and experimental density, the relative density of this BCTS composition is observed 96.20%. Then the ACM micrograph shows the dense microstructure with the inhomogeneous grain distribution in the material, and having average grain size of 38 micrometer. Then the figure shows the Raman spectroscopic study of the BCTS composition with respect to Raman shift, and also with respect to the temperature, from the temperature ranging from -100 degrees Celsius to 150 degrees Celsius. The purpose behind this spectroscopy study is to analyze the structure at room temperature also, and as with the temperature changes, analyze the structure with respect to the temperature. And also, what will be the structural transition, or where will be the structural transition present in the material, is we can correlate with the temperature dependent Raman spectroscopy. To pay
if you look at this graph at minus 100 degrees Celsius, we observe V1 yellow, V1 TO, V2 yellow TO, V4 yellow, V3 TO, V3 yellow, modes of vibration in the minus 100 degrees Celsius. With respect to increasing the temperature, these modes of vibration are get vanishes. If you look at the peak around graph around minus 50 degrees Celsius, the peak of V3 yellow here, it gets disappear in this graph over here. So it is concluded that the structural transition from the rhomboidal to orthorhombic it happens at minus 50 degrees Celsius. Above increasing the temperature up to the 25 degrees Celsius, the observed V3TO peak is not observing at the plus 25 degrees Celsius. So it is the come of that there is a structural transition from orthorhombic to tetragonal structure, and from above 25 degrees Celsius, so if you look at the graph of 125 degrees Celsius, the V1 yellow peak, which is clearly observing till the 100 degrees Celsius, it gets disappear over here. And also the characteristic peak of the tetragonal structure, which is V2 yellow TO, it is observing till the 100 degrees Celsius. Both are the peaks that get disappear at the 125 degrees Celsius, and which clearly indicate that it is converted into the cubic structure. Then dielectric properties of BCTS composition. The temperature dependent dielectric properties clearly shows the three polymorphic structural transition. TRO means rhomboidal to orthorhombic, orthorhombic to tetragonal, and tetragonal to cubic structure for frequencies of 1 kHz and 10 kHz. With respect to the frequency 1 kHz and 10 kHz, the dielectric permittivity is decreases, which is observing here. So the dielectric permittivity at 1 kHz is 13,068, and for 10 kHz it is 12,930. With this clearly high permittivity than the pure BA, the dielectric loss of this material is also less than 3%, which is observing in this graph. So with this graph, I have concluded that the TRO is equals to minus 42 degrees Celsius, and TOT is equals to 20 degrees Celsius, and cubic structural transition occurs at 115 degrees Celsius. And with this high dielectric permittivity with the low dielectric loss, this material can be used for the ferroelectric capacitor applications. So ferroelectric and piezoelectric properties of BCTS composition. This shows the ferroelectric look which confirms the ferroelectric nature of the material, and giving to a remnant polarization of 5.21 microcoulomb per centimeter square, to a electric field of 2.12 kilovolt per centimeter, and maximum polarization at 12.17 microcoulomb per centimeter square. After this measurement, I have pulled the sample at room temperature for the 0.8 kilovolt for 1 hour, and the piezoelectric properties are checked, and the observed piezoelectric charge coefficient is 280 picocoulomb per Newton, which is also 80% higher than the pure barium titanate composition, and it is good significance for the practical application. Conclusion: the BCTS piezoelectric ceramic was prepared by conventional solid state reaction method. The temperature dependent dielectric measurement reveals the dielectric maximum at the Curie temperature of 115 degrees Celsius with the permittivity of 13,068 at 1 kHz. The temperature dependent Raman spectroscopy gives elaboration of the structural transition of for BCTS electroceramic. The typical ferroelectric nature was evidenced by measuring the electric field induced polarization hysteresis loop having PR 5.21 microcoulomb per centimeter, positive electric field 2.12 kilovolt per centimeter. High value of dielectric constant and piezoelectric constant D3 was observed for the BCTS composition, which can be useful for the electric piezoelectric application. Acknowledgement: I wish to give my sincere thanks to my research supervisor, Dr. R.C. Kamre. Then I would like to thank Professor S.R. Zarkar, Head Department of Physics, Savitribai Phule Pune University. Then I would like to thank to all committee members of NSLG 2021. I am also thankful to my all lab mates and research team for their fruitful discussion. Thank you.
Thank you, Kadalaji. Very nice presentation. You have one question from Shoaib Abbas. Why GTIOT is mostly explored than BaTiO3?
Hello.
Why BaTiO3 is mostly explored than CaTiO3? Is there any special about the BaTiO3?
Okay. Actually, BaTiO3 and CaTiO3 both are having a perovskite relationship, but in accordance with the CaTiO3, BaTiO3 shows stable dielectric properties than CaTiO3, and as well as these the properties of BaTiO3 can be improved or changed with the subsequent dopants like tin, then calcium, and then other with the other lead-free materials like then other lead-free materials. So with the emphasis on other these materials, BaTiO3 is still showing the stable properties with improvement in the original properties of the package. So it may be one reason behind BaTiO3 is more explorable than CaTiO3.
Thank you, Pradhane. Now,
Yes,
the first oral 7 as candidate is present, Dr. Saubhya Lakshmi Behera. So please, Dr. Behera, please present your presentation on infrastructure, dielectric and impedance studies of lead-free tungsten bronze ferroelectric oxide. Please, Dr. Behera, present your presentation.
Hello, sir. Can I?
You can close to your side. You are okay. But I can close this note.
Yeah.
Thank you, Praveen.
Yeah, thank you.
Close करा Praveen sir. Praveen sir, अभी तक close नहीं हुई तुम्हारी slides.
Yes.
Thank you. Okay, madam. You can start. This is the last presentation of this session.
Good afternoon to all. Is my screen is visible?
No, madam. Please, your screen is not visible. Please share your slide.
Yes. I'm sharing it, sir.
Okay, we are waiting, madam. Okay.
Sound is visible, sir?
Yeah, visible.
Okay. Good afternoon to all. My present topic is structure, dielectric and impedance studies of ferroelectric oxide. My plan of presentation. Hello, Shubhashri. Can you make it slideshow? Can you make? Yeah, madam. Yeah. Yeah, madam.
This is the full screen, madam. This is the last option in the bottom. At the bottom, last option.
Yeah. This one.
This is the last one. Yeah.
Yeah, you can use F5 also. F5 or this screen.
Last option or F5. Please, madam.
Okay.
Then last option you can click. Or F5 you can press.
Yes, madam. F5.
Yes, you can press the F5. मतलब नहीं होता तो वैसे करने को ना.
Okay. You proceed.
Please you do it as it is. No problem. Please you start. No problem. No.
Not visible, sir?
Yeah, visible. You can continue.
Okay. My plan of presentation includes introduction, objective and scope, selection of materials, material preparation, material characterization, and conclusion. Then what is about ferroelectric material? As it is already discussed, the ferroelectric material is a special class of dielectric material in which the spontaneous polarization exists in the absence of electric field, and they possess extremely high dielectric constant, that is from 500 to even 15,000, and they show strong nonlinear dielectric response to the external applied electric field, and they also possess high piezoelectricity, that is, the electric field can be induced by application of pressure, and also they show the pyroelectricity, that is, the spontaneous polarization is temperature dependent. Okay? So this is the characteristic of the ferroelectric material. That is, all the ferroelectric crystal mostly piezoelectric. That is, it is a special type of piezoelectric. But the reverse is not true. All the piezoelectric may not be ferroelectric, and they show non-linear dielectric system. They have permanent dipoles, so their molecular structure, their lack of center of symmetry. And all the ferroelectric materials have one or more phase transition. The structural change takes place at the Curie temperature. They change from one structure to another structure. Immediately after Curie temperature, they follow Curie-Weiss law, that is, the dielectric constant decreases with increasing temperature and they convert to paraelectric phase. And that is the more important property of the ferroelectric material, they possess hysteresis loop. The application of ferroelectric material, that is due to the dielectric property, that is pyroelectric property, piezoelectric property, electrostatic, hysteresis, and due to their phase transition. Due to each property, they are having specific application. And among them, the dielectric properties is temperature, frequency, and electric field dependent. So, the temperature and frequency dependent dielectric properties are used for storage application or for multilayer ceramic capacitor application. This is the applications of ferroelectric materials. Generally, they are used in electronic device, transducers, multilayer capacitors, microwave dielectric resistors, pyroelectric detectors. These are the applications of ferroelectric materials. Generally, the ferroelectric materials are found in different forms: single crystal, thin film, sintered polycrystalline ceramic samples. Among them, the single crystals and the thin film, they have better properties and they are having significant technological applications. But their limitation is they are having high cost, and that is the synthesis of these material is very costly. The synthesis of this material is very costly, and they are very difficult to fabricate these materials. And about the sintered polycrystalline samples, the materials have gained immense attention because of their low cost, and they can be easily fabricated into more complex shapes. Then, for ferroelectric oxides, that is the ceramic oxides, oxides of the ferroelectric oxides are a group of ferroelectrics, and they are mostly explored due to the properties. They are having structural diversity. Their property can be tailored by substituting different cations at their size, and they show stable properties under electric field or under temperature. So due to all these applications, the ceramic oxides are mostly explored in metal science today. And one of the most important groups of ferroelectric is the family of oxygen octahedral. The family of oxygen octahedral ferroelectrics have four basic structures: perovskite, tungsten bronze, single structure, and a pyroclast. Among them, the second largest group is the tungsten bronze type. Almost all the ferroelectrics are belong to the perovskite type, but the tungsten bronze is coming after the perovskite type. This is the structure of tungsten bronze oxide. Then compounds That is the chemical formula for the PB structure is A12, A24, C4, B12, B28, O30. And the A, that is the A side cation, can be divided into 2 or 3 subsides, and the B side cation can be again divided into 3 subsides. And the smallest interstate C is generally empty. So the general formula for PB structure is A6, B10, O30. And A1, A2, that is in A side, the alkali or alkaline or the rare earth atoms can be placed. And similarly in the B side, the tetrad to pentavalent, that is the transition metal ions can be fitted. For example, titanium, niobium, tantalum, vanadium and tungsten. So after being the first research group to explore the tungsten bronze ferroelectrics with A and B cations starting from mono to hexavalent cations. That is we have completed we have explored more and more number of PB structure oxides where the A and B cations are from mono to hexavalent. But the earlier work includes in the A side as lead. That is in A2 we have used lead as the ferroelectric property or the dielectric property is mostly affected by PB. So it is suited in the A2 side. In the most of work we have used PB in the A2 side, and we have also got very good results. But nowadays, so we continue our search for new PB structure oxides for new device application. Recently also ferroelectricity has been reported by our groups from niobate and tantalate. However, this lead-based ceramics exhibits compositional fluctuation due to evaporation of lead, high temperature sintering. Another thing, when the material sintered at high temperatures, the toxicity of the lead will increase. It will create environment pollution. Hence, the development of lead-free dielectric is urgent and important. That is why, so in order to answer this functional limitation, that is, we use in the H side, in A1 side alkali atom, and the lead is only replaced by the barium. That is, in order to explore a lead-free tungsten bronze oxide without compromising their property. So in this process of searching, we have synthesized and characterized and also reported 2 lead-free materials in this comparison by taking various rare earths. So that is Na2, Ba2, Y2, W2, Ti4, Md4, O30. That is a lead-free tungsten bronze niobate. It is synthesized by concentrated solid state route, and systematically we have studied its dielectric, ferroelectric and electrical properties. This is the flowchart of the solid state reaction route. It is already known to all of you. This is the experimental details. That is a solid state reaction technique, and the raw materials or precursors are taken as a carbonate oxide. The calcination temperature is chosen as 1115 degrees centigrade, and the sintering temperature is 1200 degrees centigrade. And the XRD characterization is done in the Rigaku Ultima, and the SCM measurement and the analysis of the impedance measurement is done by the instrument EOQ 3532 LCR high pressure. And the confirmation of the ferroelectric property is done by the P-loop. Then this is the structural and the microstructural property. The sharp and single diffraction peaks shows the formation of the new compound, and that is the peaks are different from the raw materials. The compound and all the peaks are indexed using Proudmold software, and the orthogonal crystal structure is chosen for the material. The units of parameters are given by A, B and C. and the average particle size or the crystallite size is calculated using scalar equation from the broadening of the peaks, and it is around 16 nanometer. The texture and nature of the micrograph confirm the polycrystalline nature of the material, and the grain size is calculated from the grain. Distribution of the nature and size of the grain size of the sample suggests that the surface is highly dense due to uniform distribution of grain with average grain size from 4 to 5 micrometers. Then there is the dielectric property, that is the important properties for the storage, or that is the important property that is done by the LCR meter. So this is the temperature variation of dielectric constant and the dielectric law at a different frequency. And all that is the dielectric constant, both the dielectric constant and the dielectric law decreases with increasing frequency, which indicates a normal behavior of dielectric, because at low frequency all the type of polarization present, they contribute to the dielectric constant. As gradually the frequency increases, the polarization increases. So due to that, as both the dielectric constant and the dielectric law is increasing the frequency, that is they gradually decreasing. They show the normal behavior of the dielectric material. And in the dielectric constant versus temperature, there are two anomalies. And these two anomalies, the first anomaly at 338 Kelvin and the second anomaly at 638. The first anomaly is at 83 Kelvin and the second one is 683.
So fast, you have only 2 minutes.
Yeah.
Madam, little fast, only 2 minutes you have only.
Okay, sir. I am concluding. So
you can
these two dielectric anomaly that is expressed, that is the presence of ferroelectric nature, that is the highest peak, that is at 380 Kelvin. It can be assumed as a ferroelectric to paraelectric phase transition, and all the transition temperature is independent of frequency, showing the relaxer behavior of the material. And this is the diffusivity analysis, that is the broadening of the dielectric peak. In order to show the order of the phase transition, this relation is used, and from the that is the value of gamma, it is between 1 to 2, which indicates the diffuse type transition in the material. And the assumed ferroelectric property in the dielectric study is confirmed by the polarization study. Though we are having, or we are getting the less value of remnant polarization, but still it confirms the ferroelectric nature of the material. Then complex impedance analysis. In order to study the electrical properties, the frequency and the temperature dependent dielectric properties is plotted. So this is a variation
from your class slide. You are on so many slides are remaining. Please come on the last slide.
Okay. So that is from the impedance study. We got that the delta decreases with increasing frequency and temperature, that is due to increasing IC conductivity. In the pole flux, we are getting the contribution from both grain and grain boundary up to 200 degrees centigrade. The contribution is from grain and above from grain boundary. And the depressed semicircle, that is the center of the semicircle is below the axis, which shows the non-divide type of relaxation. And another important result from the impedance study is thermistor characteristic value. That is, as the resistance decreases with temperature, so from that we have calculated the thermistor value, and it is having the value between 2000 to 8000. So the high value of thermistor parameter will be suitable for NPC thermistor device. So this is the conclusion. Okay, this is my reference.
Thank you, madam. Thank you. Your oral presentation under the competition, so you please maintain your time in the next time. Yeah. Thank you very much. Yeah. Thank you. There is no any question. You are already using time. So in this session, is the two talks. One is the Dr. from Sabu and Dr. Singh already well presentation by both person. I'm very happy, Dr. Sanjay and Dr. Kiran Singh sir. And I'm also thankful to all three oral presenters, Dr. Lakshmi, Dr. Mehra Madam, Dr. Andasanga, and Dr. Mr. Kadhane sir. Thank you, and I'm also thankful to convener Dr. Smita Acharya Madam for inviting me as the chair of this session. So I'm very happy to conduct this session, and I know love so many dielectric things. Thank you, Madam Smita Acharya Madam. Thank you very much for inviting me. Thank you very much, and good luck for the next session for your remaining 2 days.
Okay, thank you, sir. Thank you. Nicely, you have conducted the session. So thank you very much, patience. Okay, now this session is going to end, and next session is poster session. So we have already collected the videos of your poster presentation. So you join on the site. We are one by one. We will present your video, and all the panelists and all this observe that video. You also join here. So before start the poster session, we take a small program about the RNP Chaudhary's golden. So, if anybody wants from the participant list, anybody want to express about the RNP Chaudhary sir who have worked with RNP Chaudhary and want to express about himself, you are openly invited there. Anybody from participants, panelists, want, because it's really a golden opportunity for us. Today is the RNP Chaudhary sir birthday. He is turning his completing his golden jubilee and going in new years of his life. Okay.
Ma'am, I want to wish Professor Anand Chaudhary. Sir, very happy birthday, sir. It is very nice to interact with you in NSFD here in Bhopal. So I'm really glad to be associated with this NSFD, and happy birthday, sir. And we hope to have, we hope that this NSFD will achieve new heights. We will take it, because this time you make it possible to have the best expert from the world. It is not a national symposium. This year it is an international symposium. And I wish you again a very happy birthday, sir.
Thank you very much, sir. Thank you.
Can I talk? Dr. Ashok from NPS, or it is only for the attendance, or I don't know.
Hello.
Can I talk here?
Anybody? Ashok Kumar is joining. Yeah. Okay. Sir, please.
So let me start. Many happy returns of the day, sir. And I wish many more years we work together. We have to have a happy life. And
Smita, sound is required.
Okay, it's not coming sound. Now my sound is coming.
It's okay.
Yes, sir. You proceed, sir. It's okay.
Actually, I have. So, because maybe I want to repeat again, but many congratulations, sir. Wish you a happy birthday today. And I would like to first, from all the Ferroelectric family, I'd like to congratulate you for many more years, so that we can have a great Ferroelectric community in India. To you only, I think, both branches all over India, and I'm also one of the branches, and I have tried my best because you always prefer to have work instead of so that we have tried our best, and hope we have quickly extended worldwide also. And apart from that, I wish many more have you here, and we can have work together, and we can, make this ferroelectric community more stronger, more popular, and
अरे वो ऋतुपर्णा दाखो अनम्यूट कर.
apart from that,
थोड़ा साउंड कम आ रहा है.
sound is still coming.
Yes, sir. आपकी वॉइस क्लियर नहीं आ रही है. Maybe your mic is too far.
Still my voice is limited, or now it is okay.
और नजदीक करिए.
Sound? I don't know. From my side it is too. Whether now it is coming?
It's not clearly, sir. It's no, your voice is not clearly coming.
थोड़ा जोर से बोलिए.
Not clearly audible. Yeah, it's not clearly audible. I think what is the problem from your side, I don't know, but it's not clearly audible.
From here I can see, but you are getting my voice.
Yeah. We are getting your voice, but it's not clear.
There is a problem or whatever. Now you can hear me well.
It's okay, sir. Proceed, sir.
Okay. So only thing I wish him a long life, happy life, prosperous life, and we have tried our best in order to have our stand, so that we are at par with any international community. Those who are working in Ferroelectrics, we have tried our best to make an standard worldwide, so that we can have. And apart from that, we again wish you happy, healthy, and prosperous life, and many more time to be, so that we can have more stronger Ferroelectric community here. And whatever I am, only due to you. That is the only one line I can say for you. So this is from my side. I have this is my gratitude to you, and from behalf of all Ferroelectric family, Ferroelectric class, from all I don't know everybody. I don't know how many of us are here. So they will also wish you. But from my side, I wish you a happy and long and healthy life. For all your blessings and thank you.
So, thank you, Ashok ji, for kind well wishes, your best wishes and greetings. Thank you very much, Ashok ji, for your kindness. Thanks a lot.
Rutuparna, sir,
And
Rutuparna.
you see my friends, it's a younger friends, you can see me.
Yeah.
I have not, madam, I have not gone to the lab, but they are missing me today after a long time.
Happy birthday, sir.
Thank you very much. Thank you, Pacho. Thank you. But they have missed me today because I am sitting at home, and every year they used to celebrate my birthday in the lab. But I am today with my larger community, larger family of Ferroelectric family of India. So I am extremely happy.
Yeah. Now you are larger Ferroelectric community with you today. Yeah. Sir, can you start that song? Okay.
Hello.
Yes, sir. That song earlier it's not clearly audible, so again we are repeating your happy birthday song.
Yes. Okay.
Start.
Thank you, Ashok. Thank you, my friends. Thank you very much to all of you. Thank you.
Yeah. Because my group is highly exciting, sir, to celebrate your birthday.
They have done it. They have made it.
Yeah. So, sir, now we are going to start poster session. One by one, we are going to present the poster.
I like to say a few words on this occasion.
Okay, sir. We are.
All my children, all my friends, all best wishes, and all must be listening on the conference and the video mode and on video mode also. So today, as you can see, 75, I started my journey of my life, of academic life and personal life in 1950s. And since then, today, we are with you. And I don't know how the 75 years has gone. And my academic life of 45 years started from a school to this side, 45 years in research. And I started my research, as you remember, Edinburgh to you today with you people. Again, I don't remember, I don't recall, I don't understand how all the 45 years has gone. Or because of my students, because of my friends, because of my well-wisher, because of my teachers, I have been continuously working without any break. Actually, my family, they had always complained and they thought after retirement at the age of 60 from IIT Kharagpur, they thought possibly I will spend time with them. But I am really sad to say that I did not give much time to them. And still after retirement also continue for last 10 years in this SOA University. And still they like to keep me here with the children. And I enjoyed working with children, like starting with Ashok ji and many more. Many of my students, they have retired. Many of them, they are abroad. And some of the India also retired. Some people are going to retire. So this is my 75 years. And I have completed 75, but again I told you, I mentioned that I don't remember how it has gone. 75 years, how I have passed, and still I don't know what will happen tomorrow. I go on doing the work. So it is only because of my teachers, my friends, my research workers, collaborators, and best wishes from this IMP, Ferroelectric community, and from India and abroad. Now the last year with Smita. So I am really happy to stay here, so-called celebrate or remember or get blessing from all of you because of this Smita here. Because I don't know how she has fixed the date, because my birthday, we never celebrated the birthday on this occasion on a Ferroelectric conference. 40 years is gone. But because of you, I must thank you that you have given the opportunity to meet all the friends on this occasion. So from the heart, my very heart, I can thank you to all of you, my friends, and Ferroelectric community, again to India and abroad. Thank you, all of you. Thank you.
Thank you, sir. Thank you. So nice words. Thank you, sir. And once again, many, many happy returns of the day, sir. And every year we will get a chance to say the happy birthday. Okay. So we'll leave this meeting and we start the video. Okay, sir. Poster video, sir. Okay, sir. Thank you.
Okay. Thank you very much.
Okay. Now just start.
Yes.
Hello everyone. Then welcome you all to the 7th session of NSFD. That is poster session. We one by one announce the name of the participant, their registration number, and then start our video. So the first video is of Dr. Balgovind Tiwari and having the NSFD registration number NSFD 2021-148.
The title of the topic is a review on the ferroelectric properties of Higgs bases and its complexes. Higgs bases are the chemical compounds that have got immense importance for use as an anti-chemical to avoid fungal, viral, inflammatory, etc. functions.
Mic ले ले
In the
वहाँ से,
science of
podium से
chemistry,
mic ले ले वहाँ
biology,
से
and
बात कर।
environment, certain kind of toxic elements should be identified and coagulated for the human environment health. So there are several techniques like atomic absorption spectroscopy.
Our second participant, Dr. Bana Bihari Mohanty, and having registration number NSFD 2021-086, and his video is, we share it.
Now the next poster is of Dr. Bharti Kishore Nandakishore Patil. Her NSFD ID is NSFD 2021
Good morning to all. I am Mrs. Bharti Patil, going to present my research work on topic preparation of ZNS and its photocatalytic behavior for dye degradation.
The next presentation is from NSFD 2021074 of Dr. Bhavani. The next presentation is from Dr. Dibakar Panda, NSFD 2021-094. Before starting the next presentation, I want to announce one thing because we have asked for the presentation of only 5 minutes. So those participants who have sent us the presentation more than 5 minutes, we are only going to play the video of 5 minutes only, right? Okay. So the next participant is Dr. Gautam Vadke, and his ID is NSFD 2021-029. The next participant is Dr. Nilata Vikrant Ganvi, NSFB 2021 1552.
A warm
The next presentation is from Dr. Jasmeer B. Randhawa, NSFD 2021-116.
Very good.
Hello everyone. We are facing some technical problem. We will start our poster presentation within 5 minutes.
Our next presenter is Dr. Jasbir Randhawa. Her registration number is NSFD 2021-116, and we will start her presentation right now.
Engineering Master.
Dr. Krishna Kumar Pandey. Our next participant is Krishna Kumar Pandey. His registration number is NSFD 2021-104, and we will start his presentation right now.
One.
Our next participant is Dr. Mamta Devi. Her registration number is NSFD 2021 172, and her presentation is
The next participant is Dr. Prafulla Shirbhate, NSFT 2021-168. The next presenter is Dr. Prashant Chaudhary, NSFD 2021-078. The next presenter is Dr. Rohini Ashish Kapardi, NSFD 2021-189. The next participant is Dr. Shraddha Shirbhate. Her NSFD ID is NSFD 2021-089. The next presentation is from Dr. Shubhangi Narade. Her NSFD ID is NSFD 2021-194. The next participant is Dr. Vivek Kumar, NSFD 2021-073. The next participant is Mr. Anup Kumar Saho, NSFT 2021-093. The next presenter is Mr. Arpit Bhujraj Mende, NSFD 2021-127.
Our next presenter is Mr. Mr. Ashwani Kumar Singh. His registration ID is NSFD 2021142.
त्या काहीतरी कामाने केल्या असतील तर त्याला झालं ना.
आपके तो फिर हम वो कैसे करेंगे अनाउंस?
वो रखना मेरे टपरे टपरे वाले. हाँ. ये प्रिया ते आपले ऑरेंज वाले दे गए ना नहीं तो व्हाइट वाले हेडफोन ऑरेंज वाले दे. एक ते व्हाइट चालतात का की ऑरेंज देऊ? व्हाइटच देऊ. 30 रुपये उसका भी 5 मिनट ही बजाना. वो तुम्हारा कॉम्पिटिटर है. ठीक है.
लेकिन तब तक कोई रहेगा नहीं रहेगा, वो अकेले नहीं रहेंगे.
अपना काम अपन पूरा कर देंगे यार.
और 4-5
ऑरेंज मत ले. देखो पिक्चर देखनी है आज. ये प्रिया ने गिफ्ट दिया हुआ है, इसको भी मत ले. हाँ ये रख दिया.
पिक्चर हमारे सामने चालू करके पिक्चर देखने जाता है. पूरा म्यूट नहीं है ये.
Our next presenter is Mr. Avinash Ishwar Ingle, and his registration ID is NSFD 2021125. Our next presenter is Mr. T. Babu, and his ID is NSFT 2021072.
A warm good evening to everyone.
So our next presentee is Mr. Bala Krishnagiri, and his registration ID is NSFD 2021092. Our next presenter is Mr. Bhaskaraya and presenting ID NSFD 2021075. Hello. Hello. Our next presentation is Mr. Bhaskaraya with presenting ID NSFT 2021075. Our next presenter is Mr. Bal Govind Tiwari, with having registration ID NSFD 2021145. Our next presentation is Mr. Hare Krishna Tola with registration ID NSFD 2021088. Our next presentation is Mr. Kaustubh Mangalmurthy with registration ID NSFD 2021176. Our next presenter is Dr. Vishwajit M. Gaikwad with registration ID NSFD 202113. Our next presenter is Mr. Balakrishna Giri with registration ID NSFD 2021092. Our next presenter is Ms. Khushbu Agrawal with registration ID NSFD20211110. And our next presenter is Ms. Prabhati Naik with registration ID NSFD20211158. So today's last presentation is of Mr. T. Babu with registration ID NSFD 2021108. And from now, we all will meet tomorrow with new session at 9 a.m. after this.